Outer space holds a weapon 100 million times more powerful than an atomic bomb. One strike, and it could black out a continent. From the space age to the Stone Age, in a flash. The weapon isn't man-made. It's our sun.
It's always a question of when the next one will happen. It's not a question of will they suddenly go away.
We've been hit before. We're in its sights again. Quebec, March 13th, 1989. The city is in the grip of winter. Temperatures are below freezing. Suddenly at 2:44 a.m., a 100-ton transformer on the Montreal power grid overloads. Blackout. The city is plunged into darkness. 6 million people left powerless. Astronomer Sten Odenwald explains how the night unfolds.
All the lights went out, quite literally. It only took about 90 seconds for fully operational to complete blackout conditions.
At dawn, the thermometer reads just 8 degrees, and the power's still out. Life or death work runs on emergency generators. The blackout lasts 12 hours. But the disaster could have been much worse. If not for a few transformers in the US, millions of Americans might have lost power too.
With only a couple of more components damaged, the entire East Coast would probably have gone down as well.
But what caused the transformers to overload so violently? Why did Quebec plunge into darkness? This wasn't a terrorist attack or human error. The culprit wasn't of the Earth. It was the result of a gigantic explosion 93 million miles away on the sun. Three days before the power network collapses, astronomers at the Space Weather Prediction Center in Colorado monitor an active region on the sun, when suddenly, a giant explosion bursts from its surface. A white flash thousands of miles across and millions of degrees hot. 93 million miles later, a huge wave of radiation slams into Earth's atmosphere. Colored lights dance across the night sky from Alaska to Mexico. Quebec is hit by an invisible but immense natural phenomenon. A solar storm. An explosion of the sun so awesome, and a wave of energy so huge, it's almost impossible to measure. Space weather scientist Joe Kunches is blown away by the scale of these storms.
Billions or trillions of tons of matter is thrown off the sun at 1 million or so miles per hour. And I think it bodes towards the difference between terrestrial weather scales, where you might have wind speeds in the extreme of hundreds of miles an hour in a very strong hurricane or a tornado, to looking out at the solar wind, and the solar wind typically is 1 million miles per hour.
The solar storm that hit Quebec is the worst in living memory. But worse may strike the Earth in the future. And next time, we might not be so lucky. The sun is capable of producing storms that could black out whole continents. North America would be crippled.
Losing the electric power grid, even temporarily over an entire continent, is a major disruption to the way we operate in the 21st century.
Our lives are more complex and technologically advanced than ever before. But the freedom technology brings us could also be our downfall. Anything relying on the power grid when a solar storm strikes is vulnerable. But what causes a solar storm? How do they wreak so much havoc here on Earth? And is there any way to protect ourselves from future attacks? Scientists need to unravel the mysteries surrounding the sun and reveal the anatomy of a solar storm. The investigation begins 93 million miles away. The sun is a 900,000-mile-wide ball of gas, mainly hydrogen. It's so vast, you could fit over 1 million Earths inside it, with room to spare. All the sun's energy is generated deep within its heart, at the core. Temperatures here reach 27 million degrees, thousands of times hotter than Earth's most extreme forest fires. Every second, millions of tons of hydrogen are converted into helium. This nuclear fusion produces over 5 million tons of energy. The sun radiates more energy in 1 second than the world has used since time began. The byproduct of all this energy is vast amounts of magnetism. Huge magnetic fields loop across the surface. They bubble up from the core and punch hundreds of thousands of miles into the solar atmosphere before plunging back down again. These arcs are so vast, the Earth could fly through one, with 100,000 miles to spare on each side. On planets like the Earth, every part makes a full revolution around its axis each day. But the sun is a dynamic ball of gas. Its equator rotates in 25 days, but the poles take 35 days. The magnetic loops stretch and distort as it turns. Along each loop flow billions of tons of superheated plasma, electrically charged protons and electrons. A single loop contains the energy equivalent to 10 million volcanoes erupting at once. These loops are sometimes the first sign of an impending solar storm. Professor Paul Bellin wants to find out how these loops lead to a solar storm. So he recreates the surface of the sun in his lab.
We have the main ingredients of what goes on in the sun. We set up a magnetic field that is arched. We have a plasma there that can conduct electricity just like the plasma on the sun. And we drive an electric current along the arch just like on the sun.
With all the ingredients of the sun in place, Bellin passes an electric charge through the experiment. Bellin's work shows these arcs are unstable. They twist and stretch in all directions. When they collide, they short circuit, like crossed wires. All their energy is released in a spark, a white-hot flash. The same phenomenon we see on the sun. A solar flare.
It's a little bit like seeing a hurricane develop. You can see the precursors of something that might blow up on the sun. You have currents, magnetic fields, the currents make forces, and if they add up in the right way, you can get very powerful forces that can cause these structures to blow up.
Bellin's lab flares release only a small amount of energy. If the energy packed into a solar flare was unleashed on Earth, the explosion could level whole cities. The The shock waves would be felt on the other side of the Earth. Nearly all life would be wiped out. Far stronger than the world's nuclear arsenal.
The smallest of the flares are more than 1 million nuclear bombs going off. The largest ones are 1 million times 1 million of these bombs going off.
Dr. Carol Shriver studies the power of solar flares.
A large flare is a vast amount of energy. It has no counterpart on Earth.
One solar flare packs enough energy to power America for thousands of years. In 1997, NASA captures this image of the sun's surface the moment after a solar flare explodes. It shows a shock wave, a ripple, racing thousands of miles across the surface. It travels so fast, it could circle the Earth in less than a minute. A solar flare packs a huge punch, but it isn't responsible for Quebec's power failure. It is the first stage of a devastating onslaught. Like the flash from a gun, it's the bullet that follows which causes the damage. Behind nearly all solar flares is a gigantic cloud of radiation, and in its sights, Earth. But its first victims are in outer space. For years, space scientists have known of the threat posed by solar storms. But the sun is unpredictable, and sometimes even NASA can be taken by surprise. May 14th, 1973. America's first space station, Skylab, launches.
Moving up. Skylab has cleared the tower.
Its mission: to prove that humans can live for long periods of time in space, and to expand our view of distant planets and stars. In total, 9 astronauts visit the station. The longest stay is 84 days. But Skylab is plagued with mechanical problems. And in 1974, it is abandoned by its crew and left to await repair. But in 1979, something knocks Skylab out of space. Scientists discover that between 1974 and 79, the sun fires a barrage of solar flares toward Skylab. But it isn't the flares that bring the spacecraft down. It's what follows. Minutes behind each flare is a gigantic wave of radiation. The wave contains huge amounts of electromagnetic energy, X-rays and gamma rays straight from the surface of the sun. The wave travels at the speed of light and smashes into the Earth's upper atmosphere, which heats and expands.
Solar storms, especially solar flares, dump enormous amounts of energy into the upper atmosphere. The upper atmosphere responds by heating up from 500 degrees to 1,500 degrees, and that also causes it to expand out by up to 1,000 miles.
The swollen atmosphere envelops Skylab. The space station is suddenly surrounded by air, where once there was nothing but space. Air drag slows the satellite down, and it begins to fall out of orbit. In July 1979, Skylab crashes to Earth. Luckily, much of Skylab burned up on re-entry. Without regular boosts, thousands of satellites could suffer the same fate as Skylab. The multi-billion-dollar International Space Station is at risk.
Even the International Space Station has to worry about solar storms. It typically loses about 75 yards of altitude every day, and during solar storms, it can lose quite a bit more than that.
But the biggest threat from solar storms isn't to our technology. Radiation can kill. NASA's Neil Zapp is all too aware of the dangers faced by astronauts on all space missions.
Our major problem is that we don't have control over the situation. It's not as easy as turning something off or sending someone home or taking them out of an area. It's very difficult for us to get people out of harm's way once they're in orbit.
No one knows when the next solar storm will strike. And they travel so fast, early warning is next to impossible.
We confirm ignition and the thrusters go.
In 1972, NASA has a close call. In April, Apollo 16 lands on the moon. 8 months later, Apollo 17 touches down.
During the space between these two missions, between Apollo 16 and Apollo 17, there was this large event.
A storm breaks on the surface of the sun. 10 billion tons of radiation rains down on the moon. Unlike the Earth, the moon has no atmosphere to protect humans from the effects of radiation. If the astronauts had been here when the storm struck, they would have absorbed a potentially lethal dose of radiation.
It wasn't by planning, it wasn't intelligent planning that provided for putting the event in the dead space. It was actually a little bit of luck of the draw at that time.
But what happens when a massive solar storm is aimed straight at the Earth? We can't simply move out of the way. For all their power, these bursts of radiation are mere ripples spreading into interplanetary space. The solar storm that hit Quebec is a tsunami. March 13th, 1989. Across the Northern Hemisphere, millions witness a dazzling light show called the Aurora Borealis, the Northern Lights. These sparks are a visible sign of a clash hundreds of miles above the Earth's surface, a war between the sun and the Earth's invisible defense shield, the magnetosphere. Nicola Fox knows the shield like her own backyard.
The sun gives us everything that we need to be able to survive here on Earth, but equally it could take that all away in a split second if we didn't have the magnetosphere to protect us.
The magnetosphere completely envelops the entire planet. This invisible shield flows out from the Earth's core. It punches through the South Pole, cocoons the entire Earth, then plunges back down through the North Pole. Without the magnetosphere, all life on Earth would be vulnerable to high-energy solar radiation. These particles can penetrate living tissue and cause severe damage to cells. When the March 13th radiation cloud collides with the shield, most of the charged particles are deflected safely around the Earth and back out into space. But some radiation does leak in at the poles.
And that really churns up the whole magnetosphere, makes it go to very different configurations than it would normally be in. And in order to redress that balance, because nature always has to be balanced, the aurora are powered.
These mysterious displays of colored lights form when solar particles slam into gases in the atmosphere and cause them to glow. The more powerful the storm, the more dramatic the auroras. This high-altitude battle can cause problems for airliners. At the poles, the atmosphere is especially vulnerable to large bursts of radiation. The wave of energy causes havoc in the upper atmosphere, disrupting GPS systems and blacking out radio signals.
During intense storms, passenger aircraft have to divert to lower altitudes in order to regain communication with air traffic control.
On March 9, 1989, as the radiation from the flare arrives at Earth's upper atmosphere, the battle with the magnetosphere begins. But in Quebec, the power stays on. 4 days later, on March 13th, a second wave of radiation hits the Earth's atmosphere, and the aurora puts on an awesome show. As the northern lights dance in the sky, the lights in Quebec suddenly go out. How does a radiation cloud high in the atmosphere shut down an electricity network on Earth? To find out, NASA develops the OSO-7 satellite. It can aim a battery of UV and X-ray telescopes at the sun. The mission will give scientists their first glimpse of a monster. This white spot might not look impressive, but it's the first image ever captured of the most powerful event in our solar system. It's called a coronal mass ejection, or CME. 10 billion tons of material explodes from the atmosphere of the sun, an enormous eruption. Without Earth's magnetosphere for protection, high-energy particles from the blast could begin to strip away our atmosphere. If a solar flare is the muzzle burst from a gun, then the CME is the bullet. Scientists still don't know exactly why CMEs occur. They're formed from the sun's corona, the atmosphere that surrounds the sun and stretches millions of miles out into space. Temperatures here reach nearly 3 million degrees Fahrenheit, almost 200 times hotter than the surface.
There are magnetic turbulence and magnetic forces lower down in the solar atmosphere that cause literally the outer atmosphere to be blown out into space.
CMEs are an electrified tangle of charged particles and magnetic fields, a superheated bullet of matter from the sun. A CME looks like a solar flare, but it's 100 times more powerful.
Before we knew of CMEs, we thought that the magnetic storms that occurred on Earth were a consequence of this brightening that was seen at the sun, the flare. And as we've learned more about the sun, we've realized that it's the CME that actually causes the magnetic storm.
Roughly half the time a solar flare occurs, a CME follows, but it travels hundreds of times slower.
It is a mass of coronal material that's coming off the sun, and that travels with the solar wind that streams continuously away from the sun at about 1 million miles an hour. So it takes about 93 hours for it to get to Earth.
On March 9th, a solar flare kicks up a wave of radiation from the sun. The wave travels at the speed of light across space. It hits the Earth's atmosphere in just 8 minutes. The coronal mass ejection arrives 4 days later. This is what causes the blackout. Unlike a solar flare, a CME isn't a spray of radiation. It's a barrage.
And all of a sudden, this big addition of 1,000, 100,000 times as much energy is thrown at the Earth.
The CME creates immense electrical currents in the ionosphere. The upper atmosphere practically crackles with energy. The auroras light up the sky as far south as Texas. Rivers of charged particles flow through the atmosphere and induce powerful electrical fields 60 miles below at the Earth's surface. Suddenly, with no warning, a vast current jumps onto the power grid. The surge races through the system, and the network overloads. The lights go out in Quebec.
We're talking about thousands of components in a power grid that are affected simultaneously, and there really is no place to run and hide from the effects.
The Quebec event was rare, but not unique. So how at risk are we? And when will the next solar storm strike?
For solar storms, it's always a question of when the next one will happen. It's not a question of will they suddenly go away.
To gauge the future threat, scientists need to know how often the Earth has been hit in the past. The hottest storms in the solar system have left their mark in one of the coldest places on Earth, the Arctic Circle. Locked within layers of ice is a history of the Earth. The ice keeps a record of solar storms dating back thousands of years. To see how often the storms hit, researchers look for a chemical they leave behind: nitrate.
You can actually core the ice and measure the nitrate abundances, and you find that the spikes in the abundances match up very nicely with some of the more recent intense storms.
By scanning ice cores, scientists travel back to an age when a massive solar storm struck Earth. A huge peak in nitrate reveals a solar storm that makes the Quebec event look like a firecracker.
The most intense abundance change that we see in the ice core data occurred in September 1859. It was so intense that we call it a superstorm event. It knocked out telegraph service in North America and most of Europe, and it was also seen all the way down in Calcutta, India at the time. It was a major worldwide event seen just about everywhere.
The 1859 storm is the most powerful solar eruption to hit Earth in 500 years. It's 3 times stronger than the storm that blacked out Quebec. If it had hit today, it would probably be catastrophic.
When you think of all of the services that rely on electric power, it's rather staggering to imagine the kind of a geographic footprint that one of these storms would have.
After a superstorm, the lights don't come back on the next day.
Most of the transformers that are used by the big power grids are custom order and can take months to replace.
Imagine months without power. Transportation grinds to a halt. The economy nosedives. No running water. No sanitation. Scarce food. Rampant disease. From the space age to the Stone Age, in the blink of an eye.
A solar storm would affect the power grid in an entire continent because these kinds of storms span the entire planet. It's unlikely that in your lifetime or mine, we're going to see one of these superstorm events. After all, the ice core data was 500 years long, and there was only one of these events in 1859. But there are plenty of events that were a half as strong or even a third as strong. They are more numerous, and because of that, the long-haul effect of these things could be actually substantially worse than one major storm all at once.
It could be worse. The sun isn't the only star that produces solar storms. Astronomers peer far into the depths of space and watch stars being born and others die. A chance discovery shows just how dangerous space can be. Astrophysicist Eric Feigelson is researching deep space, looking for streams of X-rays. But what he stumbles upon blows his mind.
Instead of finding what we thought we would find, we instead found these rapidly changing X-ray sources associated with young stars. And we were quite puzzled, frankly, for some years.
The stars produce mysterious bursts of monstrous X-rays, solar flares out of this world.
So the strongest flares we've seen are 10,000 times stronger in the X-ray band than the strongest flare ever seen in the sun. When we looked at 1,000 young suns simultaneously in the Orion Nebula, we found that they're typically flaring at this level once or twice a week.
Solar storms like the one that hit Quebec can release as much energy as 1 billion atomic bombs. The star's Feigelson studies produce flares 10,000 times more powerful. The Hubble telescope catches an eruption on a star 450 light-years from Earth. This flare is so huge, if it hit a space colony, it would take out more than their power. It would take out their planet. Scientists call it a superflare. It's not just one star that creates superflares. There are regions of space where nearly all the stars are doing it. 1,500 light-years away is the Orion Nebula. It's a brilliant haze of gas and dust. In X-ray, the dust disappears, leaving only the stars. This X-ray movie was filmed over 13 days. Each tiny flash is a flare thousands of times more powerful than any produced by our sun. These stars are just like the sun, except much younger.
This cluster was formed about 1 million years ago. Now, that may sound like a long time ago, but compared to the sun, which is 4.5 billion years old, these are very, very young stars.
The Orion Nebula is where new stars are born.
They'll all become like our sun. They're just like our sun was when it was a young star.
Space scientist Gibor Basri wants to know why young stars create such huge flares.
If you take a given kind of star, say a star like the sun, there's a direct correlation between how much magnetic activity you see on that star and how fast you spin it. The slower the star spins, the less activity it has on it.
Like the sun, these stars create huge amounts of magnetic energy because their equator spins faster than their poles. The faster a star spins, the bigger the arcs, and the stronger the flares. And young stars spin very fast.
Our sun goes around about once a month. When it was very young, it went around every couple of days or a few days. So that's how much it's slowed down. And that means that the sun is now much less active than it was then.
Feigelson describes a sun we wouldn't recognize.
When the sun was a baby star at 1 million years old, it was 3 times bigger. It was a ruddy orange color. It had huge star spots that whipped around every few days, rotating much faster than it is today. And the magnetic fields, which you wouldn't see with your visible eyes, but you'd see with an X-ray telescope. The magnetic fields would be 10 times the size of the star, crackling and seething with explosions.
Some scientists think if it wasn't for the violent early sun, the Earth and all the planets in the solar system might not be here. 4.6 billion years ago, the solar system is just a cloud of gas and dust racing around the young sun. How it transforms into the solar system we see today is still a mystery.
So the disk is full of dust, and it's sort of the consistency of cigarette smoke. These are really tiny dust particles. We're really pretty puzzled about how you get from dust bunnies to asteroids. It's easy to stick snowballs together, but it's not so easy to stick sandballs together.
Basri thinks the violent young sun helps build all the planets in our solar system. Giant solar storms rip through the disk. The dust particles are forced together. Over time, they fuse and grow. The first embryonic planets are born. Eventually, the solar system is formed. And as the sun ages, it begins to slow down. If it hadn't calmed, life in the solar system might never have developed. Yet when the sun coughs, the Earth still shudders. There's little shelter from the effects of a massive solar storm. The only way to protect our electricity network is to shut it down before the storm strikes. But how do you predict a solar tantrum? Solar storms are a serious threat to our high-tech lives in the 21st century. The race is on to predict when and where the next one will strike. In September 2006, Japan launches the Hinode satellite. Its 3-year mission is to map the sun's complex magnetic fields. The information it sends back could prove key to forecasting solar storms. Hinode orbits 370 miles above Earth. Its camera peers straight into the sun's atmosphere. It returns the clearest pictures ever of the sun's surface. In December 2006, Hinode captures this groundbreaking footage. A magnetic arc snaps, and a huge flare erupts. It blasts into the solar system at more than 1 million miles an hour. Carol Shriver uses data from Hinode to generate the first computer model of a solar storm before it erupts. A detailed map of the sun's complex magnetic fields.
What drives these large solar flares is the magnetic field, and specifically its electrical currents running through the magnetic field. So each one of these strands is essentially an electrical current prefabricated in the interior of the sun, breaking through the surface and becoming visible, and then ready to power a flare.
Where the magnetic fields intertwine the closest, the currents are strongest. Shriver replicates these electrical currents in 3 dimensions.
If we tilt this, we can suddenly see that these electrical currents come up from one place, go up by something like 20,000 kilometers above the solar surface, and come down again.
The model shows a red river of energy equal to 1 billion atom bombs. When the flare erupts, it releases that energy in seconds.
The amount of energy that goes off in this flare is simply astounding. It's the equivalent of 1 million times 1 million atomic bombs going off at the same time.
If Hinode can spot these densely packed lines of magnetism before a flare explodes on the sun, scientists might be able to predict when the next solar storm will strike. Until that technology arrives, space weather forecasters use a method of analyzing the sun's activity developed almost 400 years ago. Sunspots. Sunspots form because the sun's atmosphere is hotter than its surface. The magnetic arcs block the atmosphere, making the sunspots burn cooler than the surrounding surface. 6,300 degrees versus 10,000 degrees. Sunspots come and go in an 11-year cycle of maximums and minimums. Solar minimum has few sunspots and the fewest flares. At solar maximum, 200 sunspots or more, all firing magnetic arcs. A week before the Quebec blackout, astronomers identify a group of sunspots on the eastern edge of the sun's surface. The blackout occurs during a solar maximum. The next maximum is around the corner, in 2012. The sunspot cycle tells us the gun is loaded. It doesn't tell us when or where the bullet will strike. Once the magnetic arcs cross, the trigger is pulled and a flare explodes. It reaches Earth in just 8 minutes, too fast for a warning. But the most damaging part of a solar storm is slower. A coronal mass ejection can take up to 4 days to arrive. If we know when the solar surge will hit, we can save the electricity network by shutting it down. At the Space Weather Prediction Center, scientists keep a watchful eye on the sun. They're looking for any increase in activity, including the buildup of sunspots.
Well, the forecaster today is looking at the data, trying to understand what the sun is doing right now, and then making predictions of the effects on Earth.
Solar satellite technology is young. It's observed the solar maximum only 3 times. Space weather forecasting is where Earth weather forecasting was 50 years ago.
If you were trying to predict a hurricane, if you didn't know anything about the speed of the winds and you didn't know anything about the atmospheric pressure at the eye of the storm and some of those types of things, that would be fairly comparable to where we are now in space weather.
You can see a hurricane coming, not a solar storm. Once it leaves the sun's surface, it's practically invisible. It can hold 10 billion tons of matter, but it's spread over millions of square miles. Just a handful of atoms in every cubic foot.
You couldn't see one of these storms arriving at Earth with the naked eye. They are so dilute that they are actually better than the kinds of vacuums that we can create under laboratory conditions.
Satellite instruments are sensitive enough to detect solar storms, but there's a catch. If one heads straight toward us, it's very difficult to tell how fast it's traveling. It's like the batter in a baseball game. As the ball hurtles toward the hitter, it's impossible to judge its exact speed. 3 strikes, and he's out. If scientists misjudge the speed of a solar storm, 1 strike could take us back to the Dark Ages. To help solve this blind spot, in 2006, NASA launches a 2-stage satellite called Stereo.
Stereo's great. We're going to be able to watch coronal mass ejections from perspectives that we've never been able to see before. And most importantly, it would be the one that allows us to watch the event happen along the Sun-Earth line.
After launch, the satellites separate. They use the moon's gravity to reach their orbits, flanking the Earth. The 2 near-identical satellites orbit the sun, but one of them is slightly ahead of the other. They give the first 3-dimensional stereo view of the sun. Scientists can now forecast very quickly if and when a solar storm is going to hit the planet.
It will improve the timing in particular of the forecasts that we would try to make, to mitigate the consequences of that as it went by the Earth.
NASA hopes that Stereo's information will lengthen early warning times from just a few hours to a couple of days. It could prevent blackouts like Quebec from ever happening again. One day, advanced satellite technology might even predict solar storms before they're born.
It won't be next year. It may be a few years, but it's doable now. We've been moving ahead very rapidly with less and less simplifications, with bigger and bigger resolution, more finesse in the models. And we're getting to a state that we can say that we're actually approximating what really happens on the sun.
Stereo could save our way of life from solar storms. For 2 million years, solar storms did us no harm. Less than 2 centuries ago, we harnessed electricity and got our fingers burned. Nobody knows exactly when the next solar storm will strike. Solar maximum is just 3 years away, and once again, Earth could be in the firing line. Hopefully, this time, the lights will stay on. Of all the world's drinking water, 1/5 is stored in one place, the Great Lakes. They're so big, they're like inland seas, so vast, they make their own weather. Without them, a large part of North America would be arid. They're filled with enough water to flood the continental United States 9 feet deep. But water levels are changing dramatically. To understand where the waters are going, you have to know where they came from and unlock the mysteries behind the Great Lakes. The Great Lakes deserve their name. They cover an area bigger than Utah and hold 5,500 cubic miles of fresh, drinkable water. The deepest of the 5 lakes, Lake Superior, is over 1,300 feet deep. Lake Michigan and Huron provide drinking water for over 10 million people in Chicago and Detroit. Between Lake Erie and Ontario is the mighty Niagara Falls. At its peak, over 40 million gallons flow over the falls every minute. It provides electricity to roughly 5 million homes. The Great Lakes are unique. But how did these 5 vast lakes form? What force was so powerful it reshaped solid rock and carved such deep depressions? Beneath a sea of water and silt, the lakes cover up the evidence of their origins. Yet on an island in Lake Erie, one clue is exposed. Kelly's Island sits on ancient rock. The rock is scarred by strange grooves, some more than 15 feet deep and 400 feet long. If we were to peer into the depths of the lakes, down to the bedrock, this is what we would see. Dr. Jeff Dick from Ohio University is looking for clues to how the lakes formed.
The groove that we're sitting in here provides a very interesting tidbit of information as to how the Great Lakes formed. The area that we're in, this groove, was obviously gouged out by some force.
But which force carved these lakes? One of the Earth's most dramatic sculptors is volcanism. Boiling hot magma erupts from deep within the Earth. As it cools and hardens, it can produce incredibly strange geological formations. Did volcanism do it? The rocks at Kelly's Island hold the answer. Tiny coral fossils. When rock melts, the fossil record is usually destroyed. If lava had formed the grooves, these fossils would probably have been erased. The next suspect is water. If water carved the Grand Canyon, why not the Great Lakes? But water has an alibi: fractures in the rock.
If it had been formed by running water, a stream, a river, it's more than likely that that stream or river would have taken advantage of this weakness in the rock and actually followed it, meaning that the fractures would direct where the stream flows. And in this particular case, the grooves are running almost perpendicular to them, suggesting that maybe there's another force at action here.
So if volcanism and running water didn't shape the grooves, what did? There's another suspect: ice. But how does mere ice carve stone? Where better to find out than Earth's most spectacular frozen landscape, Iceland. This is the Vatnajökull Glacier. It's the largest sheet of ice in Europe. It covers 3,200 square miles. That's more than twice the area of Rhode Island. In places, it's over 3,500 feet thick. Geologist Andy Russell knows it like his backyard.
This glacier, although it may look as if it's sort of sitting there and, fairly passively, the actual ice is always moving forward, even though the edge of the glacier may be stationary.
This time-lapse footage shows the glacier's movement speeded up hundreds of times. Behind the leading edge, the ice moves up to 3 feet per day with a heavy step. A glacier a mile thick exerts about 2,000 pounds of pressure per square inch. That's the weight of 115 cars on 1 square foot of land. For all its bulk, ice isn't as tough as it looks. To cut into solid rock and form the basins of the Great Lakes, ice needs another ingredient. Andy Russell demonstrates.
I shall take a bit of ice, which has a smooth surface, and we'll drag it across this tin foil. Really, there's very little damage to the tin foil. So we'll now move on to the dirty ice.
Dirty ice is embedded with small rocks and stones.
We can see it's got all this grit on it, and we're going to see what it does to the tin foil. The tin foil's been shredded.
That's how a glacier does damage. As it travels, the glacier picks up stones and rocks. The weight of the ice holds them against bedrock. Then the moving mass scours the land like a huge sheet of sandpaper. When the glacier finally melts, it leaves behind a vast depression filled with glacial meltwater. Normally, it's impossible to see glacial erosion in action. The process is hidden beneath a blanket of solid ice. But here in Iceland, the base of the glacier is exposed. It shows Russell just how ice grinds through solid rock and explains how ice could carve the Great Lakes.
We've got layers of ice, which you can see in here, mixed with layers of debris, or it's dirt, here and also here, and obviously this big bit of rock here, this boulder. The boulder tells us several things. All these little scratches crisscrossing, and the fact that this surface here is extremely flat tells me that that boulder's actually been at the glacier bed. It's been held in the ice, and then it's been ground against the bedrock.
This glacier is melting, and as it melts, it drops its load. Iceland is littered with thousands of dropped rocks. It's this action of rock grinding against bedrock that may have gouged out the strange grooves on Kelly's Island. But where's the proof that a giant glacier passed over the Great Lakes area? here, near the shores of Lake Ontario. Scientists call this an erratic boulder, meaning it doesn't belong here. This giant boulder is made from granite, a type of rock not found within 100 miles of this area. Like the boulders in Iceland, it was trapped inside ice for thousands of years, dragged across the bedrock, and then dropped in its new home. The glacier that moved the boulder must have been enormous. The proof again lies in the rock of Kelly's Island. From the chemical makeup of microscopic fossil shells, scientists can tell the water was once much colder. Tiny clues lead to a vast conclusion. A glacier up to 2 miles thick covered most of Canada and a large part of the US. It was called the Laurentide Ice Sheet. For over 1 million years, the enormous glacier advanced and retreated over the land, back and forth. As it did, it gouged out the 5 enormous lake basins. The ice sheet passed over the Great Lakes. But how long did it take for ice to carve through solid rock and form the basins of the Great Lakes? Geologists think that the Laurentide Ice Sheet moved across North America for over 1 million years. But how long did it take to gouge out the 5 vast lake basins? In Iceland, the Vatnajökull Glacier erodes bedrock just as the Laurentide once did in the Great Lakes. Andy Russell measures the ground-up rock washed away as sediment.
This equipment measures the cloudiness of the meltwater. The cloudiness of the water gives us a sediment transport rate in the river, and if we average that and scale it up over longer time spans, we can figure out how rapidly the catchment is eroding.
Measure the sediment produced, average it up over time, and this glacier grinds away around 1 foot of solid rock every 100 years. But did the Laurentide erode rock at the same rate? It was, after all, over 1,000 times bigger than the Vatnajökull Glacier. John Menzies has come to Mohawk Bay on the shores of Lake Erie to find out. The answer lies hidden in these cliffs. They look like mud, but they're ancient rock sediment. This was once solid bedrock. It was crushed by the Laurentide Ice Sheet and deposited here.
Based on the evidence that we're trying to sample here today, we hope that this will illustrate how the Great Lakes basins were formed and developed.
These tiny rock particles hold a secret. Menzies sets the sample in resin and slices it into thin sections. Normally, glacial erosion produces rock grains with jagged edges. These grains are nearly round.
If you look at this particular thin section, you can see this particular piece of rock, and you can see around it the effects of rotation, kind of indicative of the sediment being moved underneath the ice sheet and rolling and rotating beneath the ice. So in other words, the sediment has been tumbled and moved and rotated and sheared time and time again.
But how can a glacier produce both jagged and smooth rock grains? The explanation? Some of the ice inside the Laurentide Glacier moves faster than other areas of ice. The fast-moving ice is called an ice stream. Ice streams are like rivers of supercooled water. Water that's well below freezing, but doesn't solidify. These rivers can flow up to 3,000 feet a year, 10 times faster than the surrounding slow solid ice. Working 10 times faster, they can potentially dig 10 times deeper. More proof that the Laurentide contained fast ice lies beside Lake Ontario. This is an aerial photograph of the shoreline. It shows strange elongated hills. These are lumps of sediment called drumlins. As the glacier retreated, they were left behind. Here's how they formed.
So if we produce a blob of toothpaste, and this we take as the base of the ice, and so as the ice deforms, so does the toothpaste deform, and we produce this nice linear. You can actually see the small lineations, drumlin-like, streamlined forms that are actually being produced simply by moving one interface over another interface.
Just as fast ice leaves a trail of long, thin drumlins, it also tends to carve out long, thin lake basins. If fast ice alone carved the Great Lakes, it could have taken as little as 100,000 years. The ancient ice sheet gouged out millions of tons of rock, ground it into fine sediment, carried it away by meltwater, and flushed it out into the Atlantic Ocean, left behind 5 enormous basins. The deepest, Lake Superior, more than 1,300 feet. The Great Lakes. But when did the enormous Laurentide Glacier melt and the basins fill with life-giving fresh water? Francine McCarthy holds a clue, a 12-foot tube of mud called a sediment core. The sample was taken from the bottom of Willoughby Bog, a swamp between Lakes Erie and Ontario.
This keeps a very good record of what went on when people weren't here to keep the history.
The core is made up of mud, pollen grains, and sediment deposited in the water when the lakes formed.
We remove material for radiocarbon dating, and the dates are about 1,700 years ago here, about 7,500 years ago here, and about 9,000 years ago near the base.
The cores reveal water was present at least 9,000 years ago. But beneath the 9,000-year-old layer is one even older. It's the last layer before hitting bedrock, so it must be the first layer deposited in the water. If McCarthy can date it, she can pinpoint when fresh water arrived and reveal the age of the lakes. But to date the layer, she needs organic material.
You can see the color contrast between the very inorganic and the bog material. This is impossible to date using radiocarbon dating, conventional radiocarbon dating techniques, because you can see that there's very little organic material here.
Just rock and clay, a dead end. But why are the early lakes lifeless? To find out what the early Great Lakes looked like, we need to return to Iceland and the Vatnajökull Glacier. Here at the base of the glacier is a newly born lake. Its basin was carved by ice and filled with meltwater. This is how the Great Lakes looked tens of thousands of years ago. And like the early lakes, this place is dead.
There was virtually no life in these proglacial lakes. It's very cold, it's a very harsh environment, there's very little light, so your whole ecosystem is unable to really get kick-started.
The reason? The water's strange milky color. These lakes are loaded with ground-up bedrock, sediment washed down from the glacier. This sediment blocks out light, and without light, small organisms like algae can't survive. No plants, no food, no life. As the Vatnajökull Glacier continues to melt, more water will flood this lake and dilute the sediment. Eventually, it will settle on the bottom, just as it did over thousands of years ago in the Great Lakes. This is the pale gray layer McCarthy discovered. The mystery remains. Scientists have to find some other way to date the age of the lakes. The answer could lie hidden in one of North America's most spectacular geological formations, Niagara Falls. Niagara is the mightiest waterfall in North America and one of the Great Lakes' most awesome features. On average, 150,000 gallons pour over every minute, enough to fill over 60 Olympic-sized swimming pools. Niagara holds the answer to a prehistoric mystery. When did the ice retreat and the Great Lakes fill with water? John Menzies has come to investigate. It's the first time he's gotten this close to the falls.
It's just utterly incredible. You see the volume of water that's coming over per second. All the water from the central part of North America is flowing right over here as we stand. Fantastic.
It's possible to date the arrival of the water in the lakes because Niagara behaves very strangely. The falls are moving. Every year, they take one step back, 12 full inches toward Lake Erie. The reason for this movement is the rock. The falls are built on 2 layers of rock. At the top of the falls is a hard layer of limestone, known as cap rock. Underneath is a softer layer.
This is a piece of Queenston shale, which is the weaker rock from underneath the cap rock for this area of regional geology. And in fact, it's very, very easily to break, as you can see. Bingo.
The weak shale at the base of the falls is relentlessly pounded at up to 70 miles per hour. The constant hammering erodes the shale below and undermines the cap rock above.
The cap rock gets left like a cantilever effect, and then it simply breaks off, and it breaks off every so often, fairly dramatically. In fact, if we look at the falls, there's a huge rock that's actually fallen off in the last 100 years. In a sense, you can look at Niagara Falls as being, if you like, an ongoing process of destruction. Perpetual destruction, perpetual change.
The destruction means that the falls act like a giant timepiece, an enormous clock that allows geologists to date the age of Niagara and the lakes themselves. Until 100 years ago, the falls eroded 3 to 4 feet a year. As water was diverted for hydroelectric power, the erosion rate has fallen, but the falls are still eroding roughly half an inch a month.
Eventually, given time, the hotels, the casinos and so forth are going to be left behind in the track of the falls as the falls retreats to the south and leaves this touristic area in isolation.
If the falls continue to erode at this rate, in about 50,000 years, the falls will reach the base of Lake Erie itself. As the falls retreat, they carve a giant canyon, the Niagara Gorge. 3 miles downstream from Niagara, geologist Francine McCarthy can date the Great Lakes by searching for the fall's birthplace. The secret is hidden not in rocks, but in clamshells.
Well, that's perfect. We can identify that to species. It's definitely the kind of thing we want to radiocarbon date back at the lab.
This species of mollusk lives in Lake Erie. It was carried downriver and over the falls. The surging water wedged the mollusk into cracks at the base, where it died. The falls moved on. The shell remained. By carbon dating shells like this, McCarthy can prove Niagara Falls roared over this exact spot 7,000 years ago.
The water level would have had to have covered this area in order to deposit the little aquatic clams in the crannies where we find them.
Further proof can be seen in the strange rocks scattered around this whole area. These holes were cut into the rock by the constant pounding of water over the falls. But this isn't Niagara's birthplace. The further McCarthy walks from the falls, the further back in time she travels, and the older the shells she discovers. By analyzing shells found all along the gorge, McCarthy reveals the life cycle of the lakes. From Niagara's spectacular location today to their location in 1678, when the first written account was made. Downstream to the Whirlpool Rapids, 5,500 years ago. Through Niagara Glen, where McCarthy's shells reveal their location 7,000 years ago. To Queenston, 10,500 years ago. And finally, 7 miles downriver from the falls, where a natural ridge called the Niagara Escarpment cuts across the land. Scientists discover the oldest shells yet.
The Niagara Falls are 12,600 years old. They've been operating since water started melting from the Laurentide ice sheet.
And if Niagara Falls is 12,600 years old, then the Laurentide Glacier must have retreated at least 12,600 years ago, exposing the 2 lower lakes, Erie and Michigan. The mystery is solved. Like Niagara, the Great Lakes have continued to evolve over the millennia. But some changes happened much more dramatically than anyone imagined. Today, rainfall on Lake Superior takes 204 years to travel through all the other lakes before it reaches the Atlantic Ocean, more than 2,000 miles away. The Great Lakes flow east, and always have, or so geologists thought. Scientists studying fossils in the Gulf of Mexico uncover surprising species. It forces them to reevaluate what they thought about the Great Lakes. Scientists analyzing 14,000-year-old shells discover the water in the Gulf of Mexico must have been less salty than today. But why? Only one source of fresh water was vast enough to dilute the Gulf: the Laurentide Glacier. Fossil records suggest the meltwater drained south along the Mississippi River to the Gulf. But then, nearly 13,000 years ago, some titanic force diverted the flow from south to east. The question is, what force was powerful enough to divert the Great Lakes? "13,000 years ago, some unknown force diverted the flow of meltwater from the Laurentide Glacier. Geologist Alan West searches for answers on the shore of Lake Michigan.
This is a visual line that's actually where our greatest interest lies. The Great Lakes really began right at this line in the sediment.
West finds tiny specks the size of sesame seeds. They're made of carbon. West believes they're all that remains of a vast forest, incinerated at sizzling temperatures. But the most important clue lies inside each grain, a dazzling secret.
These small black dots, they're almost pure carbon, and when we check them with an electron microscope, we find that they contain millions and millions of diamonds.
Each diamond is 1,000 times smaller than a pinhead. They're known as impact diamonds. They form under intense pressure. But what created them? Something big hit this area at great speed. It packed a huge punch. Alan dumps a sample over a magnet. Incredibly, it contains metal.
Definitely magnetic grains in there. You can see them coming out.
The magnetic grains are iridium. Iridium is extremely rare on Earth, but common in rocks from space. West's theory is 12,900 years ago, a massive comet strikes Earth and showers the region with iridium. Wildfires sweep across the area and destroy all vegetation. The shock wave breaks up part of the Laurentide Glacier. Billions of gallons of water are released.
It's well known that when these meltwater outburst floods occurred, they're very, very abrasive. They can change the shape of valleys, they can scour bedrock, so it's entirely possible that they dug the Great Lakes deeper or at least removed sediments that were already there.
Thousands of tons of rock, soil, and debris are flushed south. Like a giant plug, it blocks the Mississippi. The water backs up. Lake Ontario swells and bursts its low eastern bank, and the St. Lawrence Channel opens up.
All the evidence shows that the Gulf of St. Lawrence opened up and water went to the east, but stopped going to the south.
West believes it all happened in just a few months. Since then, the lakes have drained east into the Atlantic Ocean. The new direction allowed small settlements to become the great cities of Montreal and Quebec. Rarely does the course of history change so suddenly and so dramatically. Yet the evidence is circumstantial. If a comet hit, where's the crater? In 1999, on the bottom of Lake Ontario, geologists discovered a crater half a mile wide. It's still undated. West believes it might be a fragment of the comet that diverted the water. No other craters have been found, but West isn't surprised. The comet could have done its damage and simply melted away, because comets are mostly ice.
This is the perfect crime, the ice bullet. Shoot someone with an ice bullet, and you can't tell who did it. Earth got hit by an ice bullet, actually thousands of them, and so the evidence is minimal.
As the last ice age ends, all 5 Great Lake basins are slowly revealed and filled with fresh water. But there's one huge difference between these early lakes and the ones we see today. They aren't linked. To unite them will take a force of nature more powerful than a comet. Today, the Great Lakes are connected via a network of rivers and channels, a 2,000-mile water system. This wasn't always the case. The upper lakes, Superior, Michigan, and Huron, weren't always connected to the 2 lower lakes, Erie and Ontario. Francine McCarthy is trying to find out how they joined.
We've taken some samples all along the shoreline of Lake Ontario and Lake Erie, and we're going to look under a microscope at small seeds and pollen to find out the age of the samples and what kind of environment they were deposited in.
5 miles inland from Lake Erie, McCarthy discovers a tiny clue: wild rice. This is incredibly strange. Wild rice doesn't grow inland.
Wild rice needs to have sort of agitated, well-oxygenated water in order to be happy. The fact that there was a lot of wild rice indicates that the water level in Lake Erie was higher than it is today.
Lake Erie must have been much bigger and more turbulent.
The wild rice date of 4,230 years tells us that water levels rose quickly, instantaneously, in both the Erie and Ontario basins.
But why? McCarthy has a theory. Over 4,200 years ago, Lake Huron swelled and burst its southern bank. A torrent of water pushed south. Lake Erie suddenly expanded, and wild rice took root in its disturbed waters. The St. Clair River opened, and the lakes joined.
That's when we begin to see the truly modern conditions. Since 4,200 years ago, there's never been any other way for water to flow out of the upper lakes but through the St. Clair River into Lake Erie, over the falls, and into Lake Ontario.
But why did Huron swell and flood south? The mystery deepened when scientists noticed something strange happening in the Great Lakes. In each lake, the water level in the north is falling, but in the south, it's rising. What mysterious force is behind these strange phenomena? Professor Doug Hunter and divers Luke Clyburn and Kathy Trax are plunging into the lake's past to find evidence of ancient water levels. They start their investigation in Lake Huron's southwest corner, in the harbor town of Lexington. They need evidence to show whether this imbalance in water level is a recent phenomenon or if it's been going on for millennia.
Today, we're going to put divers in the water, and as we dive down, we're looking to see if we can find something that will show that this is where the lake levels were some thousands of years ago.
Lake Huron is over 700 feet deep in places. But the area the team are interested in is only 40 feet deep.
Right now, we're about 2.5 miles east of Lexington Harbor. Underneath us, in 40 feet of water, is an area where we suspect there may be some interesting finds that would give us some insight into the Great Lakes history.
This section of the lake bed has never been surveyed. The team scour every inch for evidence of past water levels. They're looking for something out of place, some clue to this strange mystery. "40 minutes into the dive, the team finds several large pieces of wood. From this wood alone, they can't tell if trees once grew here or if it's just debris thrown from a boat. They need evidence like this. A tree trunk. It's still rooted in the lake bed. These stumps have never been seen before. This proves that trees once grew in this exact spot. A true discovery.
There's wood.
Boy, that was a great dive. You could see whole trees falling over, and they just went out into the sand and down.
But once we found the tree stumps, and you could see the roots of the tree stumps running down, it had to be shoreline.
This part of Lake Huron was once a forest of cedar and pine. Today, you have to dive 40 feet to reach the trees. But once you could have walked here and not even gotten your feet wet. When could you have strolled through the trees? These stumps have to be carbon dated. but samples from other locations in the lake have already told their age.
We discovered that the most recent one was 6,400 years before present. The oldest one was about 7,900 years before present. So it's quite a long range, quite a large range of dates.
6,500 years ago, Lake Huron was a fraction of the size it is today. A forest flourished on its southern end. "1,500 years later, water crept south. The southern end was swamped and the forest drowned. The St. Clair River opened, and Lake Huron joined to Lake Erie. The overflow thundered along the Niagara River and tumbled over the falls. And all 5 lakes joined. But what caused this dramatic transformation? And is it still taking place today? Mike Kramer from the Geologic Survey of Canada is investigating a strange anomaly. Why water levels in the Great Lakes are dropping in the north and rising in the south. Kramer works on a remote spit of land next to Lake Ontario. It's not the water level he's monitoring. What looks like a garden shed actually holds state-of-the-art GPS technology.
We're using a GPS receiver to monitor the motion of the structure every 30 seconds. The antenna is bolted down to the floor and runs up through the roof. It's very stable.
In other words, Kramer is studying whether the shed is rising or falling. This GPS receiver picks up signals from satellites orbiting the Earth. The equipment is so sensitive, it can detect movement down to the millimeter. As a result, Kramer can determine the exact elevation of the shed, and thus the land it sits on. His findings are astounding. The Great Lakes region is rising 1 inch per decade in the north and sinking nearly 1 inch per decade in the south. This part of North America is tilting, and the pivot point runs straight through the Great Lakes. The tilt is imperceptible to us, but it affects the lake's water level.
We have a bowl of water representing a lake, this end being the north, this end being the south. And if we can imagine, as the land tilts, the water levels are rising in the south and falling in the north. It appears as though the water level is falling, and actually it's the land that's rising.
The changing land levels are tiny, but over time, all those inches add up. Ultimately, tilting is what drowned a forest. But what force is powerful enough to tilt a major part of the North American continent? Scientists think it's the opposite of the force that compressed it. Earth's surface can actually be squashed if the weight is heavy enough. Few forces are capable of compressing the crust. One is ice. The Laurentide Glacier weighed around 10 million billion tons. Once it reached a certain thickness, the glacier depressed the crust 1 foot for every 3 feet of ice. It left a dent up to a half a mile deep.
About 20,000 years ago, the ice had covered most of Canada, and the great weight of that ice had depressed the crust substantially. And as the ice retreated and melted, the land underneath it then began to rebound.
Rebound began as the ice melted tens of thousands of years ago and continues to this day, about 1/10 of an inch per year. The ice sheet was much thicker in the north than it was in the south. At its thickest, it compressed the Earth the most. So when the weight was removed, the Earth rebounded more in the north. This imbalance causes much of North America to tilt. Combined with a warming climate and less rainfall, rebound is changing the outline of the Great Lakes. If water levels continue to drop in the north, vital transport routes will shrink. Industry, hydroelectric power stations, and millions of people could be affected. Eventually, the crust will rebound to roughly the position it was before the Laurentide Glacier advanced over it, and the water will find its level. But until it does, the future of the Great Lakes will be as dynamic as their past. A split second, the Big Bang, and the whole universe was born.
In the blink of an eye, literally, so much can happen that it would blow your mind.
How did we get here? And what is the universe made of?
The secret of creation, the secret of everything is locked in that first second.
Technology stands on the brink of revealing what happened in the most important second of all time. In the beginning, there is nothing. No matter, no energy, not even empty space, because space itself doesn't exist. No time passes, because there's no such thing as time. From nowhere appears a fireball smaller than an atom. 10 trillion times hotter than the core of the sun. Everything that will become the universe explodes from a point millions of times smaller than a pinprick. Time begins. In 1 second, the blueprint for the entire cosmos is written. How it happened is the biggest mystery of all. Professor Lawrence Krauss has devoted his career to studying the first second after the Big Bang.
If we want to really understand our place in the universe, we have to go back to the very beginning and understand how it all came together.
Looking back to the instant of creation is a new idea. The theory of the Big Bang is widely accepted, but the concept is less than a century old.
But one of the things we have to put in perspective is how recent our understanding of the universe is. 80 years ago, the conventional wisdom in science was that the universe was static and eternal, had been around forever.
But this changes in 1929. At California's Mount Wilson Observatory, Edwin Hubble studies the light from galaxies. He observes that the farther the galaxy, the longer the wavelength of light it emits. Light waves stretch the more they travel, and stretching changes their wavelength. The same principle applies to sound waves. As a train approaches, the whistle's pitch rises. When it passes, the pitch lowers. As the train recedes, each sound wave has to travel farther than the last to reach your ear. The sound waves stretch, lowering the pitch. Something similar happens with light waves. If a galaxy is moving away from us, its light waves stretch, becoming longer and redder. It's called red shifting.
When we look at visible light, there's red at one end of the spectrum and blue at the other. Red radiation is the long wavelength radiation of visible light, whereas blue radiation is the short wavelengths. And as we look at the universe, we see the radiation from distant stars literally stretching so that the light gets redder. And the farther away we look, the redder the light is.
Galaxies around us have shifted to this red light.
We look out in all directions at distant galaxies, they're all moving away from us.
Nearly all galaxies are receding at 1,000,000 miles an hour. If galaxies are speeding away from each other, at some point, they must have all been together. The universe is expanding outward from a single point. It's the first evidence that the universe had a beginning. Hubble's findings lead to a radical concept: the Big Bang Theory. Scientists believe that in the first second after the Big Bang, the building blocks were created for every star and planet in the cosmos. To prove it, they first need a new way to tell time.
We are thinking of fractions of time smaller than we think about in any other area of human activity, and smaller fractions of time than a race car or a sprinter or anything else. And what we've learned is that more can happen in a fraction of a second, in a blink of an eye, than you can imagine. It would just blow your mind.
Hours, minutes, and seconds are the basis of modern life. But events after the Big Bang happen in fragments of time far smaller than a second. To analyze what happens, scientists use a new measure of time called Planck time. 1 Planck time equals 10 to the minus 43 seconds. That's a decimal point, 42 zeros, and then a 1. It's an unimaginably small amount of time. Yet in this first tiny beat of Planck time, something happens that shapes the next 13.7 billion years. Out of the fireball, the 4 fundamental forces of nature form. Those forces underpin everything around us. Gravity is the reason stars and planets form. It rules the moon and tides and keeps us on the ground. Electromagnetism lights our cities, connects our phones, and runs our computers. And the 2 nuclear forces, strong and weak, bind the particles that make up our bodies and power the furnace of our sun. We're here because in the first second after the Big Bang, the 4 forces are created. Without them, the universe would be a featureless fog of radiation.
If there were no forces, nothing would happen. There'd be no television. There'd be no sports. There'd be no love, no hate, no human tragedy, all the things that make life worth living.
But in the first beat of Planck time, the 4 forces are still rolled into a single superforce. Gravity, nuclear, and electromagnetic forces have not yet divided. Physicist Michio Kaku studies how the forces split apart.
I like to think of it as a crystal, a beautiful symmetrical crystal, all the forces unified in their elegant simplicity at the beginning of time.
As our cosmic clock takes one more tick of Planck time, the tiny fireball universe expands. The 4 forces start to break apart. It's like rapidly cooling a super hot crystal. Cracks form.
It began to shatter into 4 pieces. The first piece to break off was gravity. Then the nuclear forces began to split off. And finally, we have this fragmented jewel of what used to be the superforce.
Those 4 fragments are still at work. Gravity keeps Earth in orbit. Nuclear forces make sunshine. And electromagnetic radiation, the light that bathes our planet. We're just fractions of a second into our journey, and already the foundations of our world are forming. The fireball universe. Still smaller than an atom, and 1,000 trillion degrees. To discover how the universe expands, scientists use telescopes so powerful they can see the past. When astrophysicist David Spergel looks up, he sees history.
As we look out in space, we look back in time. Light travels at a finite speed. So the light we see from the sun takes about 8 minutes to get here. We see the sun not as it is, but as it was 8 minutes ago. We look out the night sky, we see the nearby stars. They might be 10 or 20 light years away. We see them as they were 10 or 20 years ago.
The Big Bang was so powerful and so hot, remnants of that heat still survive. The heat began as super-hot X-ray radiation. As it stretched and cooled, it became visible light, shifting from blue to red, then becoming microwaves, and finally radio waves. This faint radiation shines down on Earth all the time. It's called cosmic microwave background radiation, or CMB.
The cosmic microwave background is the echo of creation itself. It's the embers, the afterglow of the original shock wave that created the universe. If we had microwave eyes that could see microwave radiation, then every night we would see the Big Bang coming out. Looking at the heavens, we would actually see an explosion.
More than 13 billion years later, we have a way to see this cosmic glow with the naked eye.
You take your TV set, switch it between channels. A couple percent of the static that you see on your TV screen is radiation from the Big Bang.
This cosmic radiation is a direct connection to the Big Bang. It also reveals the universe entered a new phase, less than a trillionth of a second after its creation. Cosmic radiation is the key to discovering what happens next. A few beats of Planck time tick by on our cosmic clock, and the fireball universe is transformed. One instant, the universe is billions of times smaller than an atom. The next, it inflates to the size of a baseball, growing more in this moment than in all the 13.7 billion years to come. Scientists call this rapid expansion inflation. And the evidence survives in the cosmic radiation left over from the Big Bang. Like static on your television, this cosmic radiation seems so constant and so even, it presents scientists with a puzzle.
When we measure the cosmic microwave background in that direction, its temperature is identical to its temperature in that direction. It's the same everywhere.
The only explanation is the universe inflates countless times faster than the speed of light. Inflation expands the fireball universe evenly, like a balloon blowing up, with a phenomenal breath of energy.
I try and imagine compressing a spring. I push it closer and closer and closer together so it's smaller and smaller and smaller, and I've stored a tremendous amount of energy in that spring, and when I let it go, it bursts out. And that stored energy drove an exponential expansion of space.
But if the entire universe is uniform from the first second after the Big Bang onward, how did the galaxies form? Planets and stars begin as clusters of particles. Over time, these particles of matter clump together under the force of gravity to form a dense mass. Earth began as a ball of particles that clumped together through friction and gravity. The sun that sustains life on Earth started out as a cloud of gas and dust. How did these clusters form in the first place? The early universe should be lumpy, not even. To link the formation of stars and planets all the way back to the first second after the Big Bang, NASA scientists like David Spergel developed the Wilkinson Microwave Anisotropy Probe, or WMAP, a satellite mission to measure the temperature of cosmic radiation in more detail than ever before.
While this radiation is everywhere, it's very faint. And to observe it in great detail across the whole sky, you want to get away from the Earth and any interfering sources of radiation.
7, igniters armed, green board, 5, 4...
NASA launches the probe in 2001.
Main engine start and liftoff of the Delta II rocket with the MAP spacecraft, exploring the past and future of our universe.
It could produce the best ever snapshot of the universe in its first second.
The launch was incredibly exciting, tense, an exciting moment to see it go up and then realize it was working.
WMAP sits 1 million miles from Earth. It's so sensitive, it can measure the temperature of cosmic radiation within 1/millionth of a degree. For 5 years, WMAP analyzes the sky in minute detail.
It sits there with the Earth and Sun always behind it, staring out into space. The satellite's spinning very rapidly. It covers about 1/3 of the sky every hour, spinning and making maps of the leftover radiation.
WMAP tracks the Earth as it orbits the Sun and scans the temperature of the whole sky. It generates detailed temperature maps like this one, and it reveals something remarkable. The blue and red patches on this map of the entire sky are tiny ripples in temperature.
The little blue regions represent regions that are a few tens of thousands of degrees colder. Red regions are a little bit hotter, so you're seeing tiny variations in temperature across the sky.
WMAP looks back over 13 billion years. As the universe evolves, these tiny ripples develop into clusters of particles that get bigger and bigger under the force of gravity, becoming just dense enough to trigger stars and galaxies to form.
I mean, it really was what I think we all dream of when we go into science. Looking at things that no one's looked at before, learning really exciting things about fundamental questions. Questions like, what's the universe made of? What happened in its first moments?
This is a map of how the universe looked in the first second after the Big Bang. The template for today's vast cosmos.
When the picture of the cosmic microwave background radiation first came out, the press said, "Ah, the face of God." Well, let's be real. It's not the face of God. What it really is a baby picture of the infant universe. So the discovery of the cosmic microwave background radiation ranks as one of the greatest discoveries in all of science.
Less than 1/trillionth of a second after the Big Bang, the fireball universe rapidly expands. Now an ultra-hot globe big enough to sit in the palm of your hand, the universe is seething with energy and radiation. But as the palm-sized universe expands and cools, something new starts to form. Only a fraction of a second after the Big Bang, and the destiny of the universe is already mapped out. The sun burns because of forces forged more than 13 billion years ago. The stars and planets form from the way the universe rapidly expands. Science can trace everything we see today back to the first second of creation. But we're here because of what happens in the next few beats of Planck time. The universe is flooded with the building blocks of matter. So far on our cosmic clock, the early universe is nothing but energy. How did pure energy turn into matter? Everything around you is made of matter. What you're sitting on, the air you breathe, the whole planet is made of matter, and matter is made of atoms. And in the first second after the Big Bang, the ingredients for atoms are created. How matter appeared mystified scientists, until 1905, when Albert Einstein comes up with our most famous equation. E equals mc squared. Einstein's equation tells us that energy, E, and mass, m, are different forms of the same thing. Matter and energy are interchangeable. Some scientists later used this equation to create the most destructive weapon in history, the atomic bomb. It offers a clue to what happened in the first second. In a nuclear explosion, particles of matter are ripped apart to produce an enormous amount of energy. During the Big Bang, the exact opposite happens. An enormous amount of energy turns into matter. Einstein's equation prompts a conclusion. As the baby universe expands and cools, the pure energy of the Big Bang converts into the particles of matter that make us. We're only a fragment of a second into our journey. The first particles of matter appear. The universe is 1,000,000 times hotter than at the core of the sun, still far too hot for particles of matter to bond and form atoms. Scientists face a puzzle. What is this early state of matter like? And how does it become the protons and neutrons that form every atom in the universe?
Atoms were impossible. Think of putting an ice cube in a steam bath. The ice cube would melt immediately. You cannot have ice cubes in a steam bath.
You can see the proof in a block of ice. When water is cold enough, it's a solid. Warm it, and you get a liquid. Heat liquid water, and it boils away into a gas, water vapor. Superheat the gas, and the energy pumped in rips the atoms apart. Likewise, the universe in the first second is so hot, only the building blocks of atoms can exist.
If you were to journey into the early seconds of the universe, literally you would disintegrate. You would literally fall apart, and even the debris, the nuclei of your bodies, they too would fly apart into subatomic particles. There would be nothing left of your body.
There's only one way to see these super hot building blocks of matter in the first second after the Big Bang. Scientists must recreate conditions of the Big Bang itself.
The inside of a star is measured in tens of millions of degrees, but the Big Bang was measured in trillions upon trillions of degrees. So we have no way to simulate the instant of creation other than with a particle accelerator. By slamming protons into other protons, we can create temperatures not seen since the beginning of the universe itself. So particle accelerators are the only game in town when you talk about simulating Genesis.
This is Brookhaven National Laboratory in Long Island, home to the Relativistic Heavy Ion Collider, or RHIC, a 2.5-mile ring designed to smash the nuclei of gold atoms at nearly the speed of light.
With the particle accelerator, you slam subatomic particles together. As a consequence, we get a tremendous shower of debris, and then we want to make sense out of it. We want to know what's inside that collision.
The energy of the collision is colossal. On a small scale, it reproduces the embryonic universe in the first second. How? By ripping nuclei into the protons and neutrons they're made from. The energy is even enough to rip the protons and neutrons apart. Inside, scientists discover the building blocks of matter, tiny particles called quarks. But they're so small and move so fast, they're hard to track. If scientists can figure out how quarks behave, they'll unlock the secret of matter itself. What they find could revolutionize medicine and relaunch the space program. The project starts in 2000. Colliding nuclei creates a chaotic spray of particles. It takes 5 years to analyze the data. The results come in 2005. They're shocking.
We were expecting to find a gas when we slammed gold nuclei into each other. So the shock was, it wasn't a gas at all. We found that it's more like a liquid. So this came quite a shock, because now when we begin to simulate the early universe, we have to get rid of this mental picture of a gas of subatomic particles. Now we know it's more like a liquid, literally like a soup.
When matter first appears in the universe, the quarks are so dense and so energized that the entire universe is like a liquid. The universe went from a glowing ball of energy to quark soup in less than a blink of an eye. The liquid universe is hot, dense, and violent. Flooded with tiny particles in constant vigorous interaction. As our cosmic clock reaches a millionth of a second, the universe continues to expand and cool. It grows from the size of a baseball to the size of our solar system. Matter has materialized from pure energy. Without matter, none of us would be here. And in that first second, that very nearly happens. Something comes close to destroying all matter in the universe. Armageddon is brewing. A split second after the Big Bang, and the universe is flooded with the building blocks of atoms. These tiny particles of matter must survive in a battleground. Everything around us is made of matter formed from the energy released by the Big Bang. Every molecule, every atom, every quark. How we end up with a universe that consists of so much matter is one of our biggest questions. The particle accelerator may reveal the answer. When the first second is recreated, two types of matter are produced in equal parts. One is the type of matter we see around us. The other is its opposite, antimatter. Dr. Tara Shears explains they're two sides of the same coin.
This apple is made of matter. We know that every matter particle in the universe has an antimatter partner that was created in the Big Bang. Now, antimatter looks similar to normal matter, but not quite. In fact, it looks like the mirror reflection of matter. So an anti-apple looks like this.
If the universe was made of antimatter, it would essentially look identical to how it looks today. You and I would be made of antimatter, and anti-lovers would sit in anti-cars looking up at an anti-moon at night, making anti-love, and it would be largely the same.
But matter and antimatter are mortal enemies. They can't coexist.
When we have a matter particle meeting an antimatter particle of the same type, Then they annihilate, they explode together, they destroy each other. All the energy that the matter and antimatter particle have goes into one large explosion of huge, tremendous energy.
Fractions of a second after the Big Bang and the future of the universe is at stake, matter and antimatter are locked in a battle to the death. A millionth of a second after the Big Bang, and a battle rages. When matter and antimatter clash, the result is explosive. Just one apple-sized clump of matter hitting its antimatter equivalent would release as much energy as a 10-megaton nuclear bomb.
If you could go back to the really early universe just after the Big Bang, you'd find yourself in this seething mass of matter and antimatter annihilating each other. You'd find yourself in the middle of this cosmic battle between both sides, caught in the crossfire, if you like.
With all the particles in a super-dense liquid state, matter and antimatter quickly meet and destroy each other. Since they're created in equal numbers, and every matter particle that hits an antiparticle is annihilated, all matter should be destroyed as soon as it's created.
All the matter would have eventually found the antimatter and they would have annihilated, producing pure radiation. And we'd now have a universe. I was going to say we'd now be living in a universe of pure radiation, but we wouldn't be living in such a universe because we wouldn't be here. There'd be nothing but radiation.
But the universe is full of matter. How did it defeat antimatter? It's one of science's great mysteries. One theory is that antimatter is less stable and decays more quickly, creating a tiny imbalance between matter and antimatter. This tiny imbalance eventually allows matter to overwhelm antimatter. Whatever the truth, something happens just after the Big Bang that tips the balance in favor of matter.
And the whole battle stopped at that point. And what was left was a very small amount of matter. And it's that small amount of matter that makes the universe that we live in now. That means that we're the leftovers of this battle. We're the dregs. We're what's left when everybody else had finished.
The dregs go on to form everything around us. From the ground beneath our feet to the most distant galaxy. As the cosmic clock nears the end of the first second, nature's four forces have split off from the single superforce. The winner of the matter and antimatter war has been decided, and the subtle ripples in temperature that stretch across the universe mean that over the next billion years, gravity gathers clumps of matter to form galaxies. But one mystery remains, and it's a big one. We know how the building blocks of matter form, but we don't know what gives everything in the universe substance. We know so much about the first second, but a piece of the puzzle is missing. What gives everything in the universe mass? Mass makes it tough to get something moving, and makes it hard to stop. When we're pulled down to Earth, gravity is acting on our mass. On the Moon, gravity is weaker, so astronauts move slower, but their mass is the same as back on Earth. Even if an object weighs nothing, it still has mass. Something must have been created in the first second to give particles mass, but scientists haven't found it.
We have this hole. We have this missing piece. The centerpiece of this whole picture is what happened during that first second of creation. If you know that, then you can, quote, read the mind of God, as Albert Einstein used to say.
Mass is the very backbone of life.
If there were no mass, the universe would consist entirely of radiation, and nothing could bind together to form objects like you or I, or any of the things that appears to make the universe interesting. It would be a diffuse universe full of radiation, but very, very boring.
Discover how mass develops in the first second, and you uncover the root of life. If scientists can't find what gives particles their mass, that first second will remain an enigma. Our journey is almost finished, but a piece of the puzzle is missing, and it stumped scientists for decades. Then in 1964, at Britain's University of Edinburgh, physicist Peter Higgs comes up with a groundbreaking theory. He suggests an invisible force field sweeps across the universe in the first second, giving particles their mass. It's become known as the Higgs field. When particles interact with it, they gain mass.
For example, if I take a car and that's run out of gas and I push it on a road, eventually I can push it and I can move it along. But if it runs into the mud, if I try and push it, it will suddenly seem heavier. I can't push it as hard. It'll act as if it's heavier. Well, we think that particles have mass for a similar reason. There's this Higgs field, and some particles interact with it more strongly than others. And the particles that interact with it less strongly are easier to push, and therefore behave as if they're lighter. The particles that interact with it more strongly are harder to move and act as if they're heavier.
Like mud, the Higgs field sticks to everything. When particles enter the field, they gain mass. The more contact with the field, the more mass they gain. Scientists believe the Higgs field is carried by its own special particle. Journalists call it the God particle. Scientists call it the Higgs boson. They think identifying this particle could reveal how we got here. The math is good, but no particle accelerator was powerful enough to find the Higgs boson. Until now. Deep beneath the countryside in Geneva, Switzerland, is mankind's most expensive experiment, the Large Hadron Collider, or LHC. The world's biggest particle accelerator and the best shot at finding the missing Higgs.
We've got to see if the Higgs particle really exists. And that's why we have to build these mammoth accelerators, to see if we can understand the mechanism responsible for the existence of everything we think of as solid and heavy in the universe today.
It cost $10 billion, took 14 years to build, and involves the work of 7,000 scientists. This year, they switch it on. On a small scale, it will recreate conditions last seen over 13.7 billion years ago. An explosion so powerful, it will echo the Big Bang itself. If it works, scientists like David Evans could solve the last mysteries of matter.
Because we're pushing the frontiers of science, we have to also push the frontiers of technology. It is, as well as probably the biggest machine in the world, it is certainly the most complex machine in the world.
Over 300 feet underground runs a 16-mile circular pipe. Inside, two beams of protons, thinner than a human hair, are accelerated to almost the speed of light, 186,000 miles per second. The LHC will smash particles together 7 times harder than any other accelerator. 300 trillion protons fly around the pipe in opposite directions and collide in the heart of enormous detectors. Lawrence Krauss inspects one of these detectors each the size of a 5-story building.
Here we are at what's been aptly described as being one of the Gothic cathedrals of the 21st century. This monstrous structure made of thousands of tons of steel, more iron than in the Eiffel Tower, with tens of thousands of miles of wire. All of this designed by thousands of physicists from hundreds of countries, speaking dozens of different languages, with the precision of perhaps a millionth of an inch, just to detect what happens inside there.
The LHC uses 4 of these giant detectors along the beam pipe. The one they hope will find the Higgs is called Atlas. Atlas is half the length of a football field and weighs as much as a nuclear sub. It can detect 1 billion collisions per second. When the protons collide, the impact is so titanic, in a split second, it will recreate matter as it was just after the Big Bang. A shower of fundamental particles, like quarks. Somewhere in the debris, they hope to find the elusive Higgs. But finding one particle in this firestorm is like finding a speck of gold on a beach. The Higgs is so tiny and so short-lived, the detector won't see it directly. Instead, they hope to capture the trail it leaves behind, using the most high-tech cameras in the world.
When you look at a Skyrider, you see this gigantic plume of smoke, but where's the airplane? You never see the airplane. The airplane is too small to be seen. That's how we use detectors. Detectors cannot pick up the particle itself, but it can pick up the trail left over by the subatomic particle, and looking at the trail, we can determine what kind of particle it was and how fast it was moving.
The LHC will generate more data than any other instrument on the planet.
In a single second, the amount of information that's coming out of the collisions at the LHC that will be handled by these detectors is greater than the amount of information in all the libraries in all the countries in the world.
That data may hold the secret of mass, the missing piece in the universe's first second, and the doorway to the science of the future. To process all this information, the LHC uses the world's largest network of supercomputers. Even so, the search may take years to complete, but it's worth the wait. If it succeeds, the LHC could launch a new era in science. If it fails to find the Higgs and reveal how matter gets its mass, it will leave a hole in the riddle of the first second. New theories will have to be written, and more powerful experiments built.
Hey, I'm a realist. I realize that perhaps we'll find nothing. That could create a crisis in physics. It could stagnate all of physics if all of a sudden our machines are not powerful enough to unveil the next act, the next curtain, where we look at the next stage of matter and energy.
One thing they know, the LHC will take scientists closer to the Big Bang than ever before. It will reach back 13.7 billion years to recreate the very first second of the universe, the greatest second. Our cosmic clock takes its final beat of Planck time. The universe is 1 full second old. It's about 1,000 times the size of our solar system and flooded with particles of matter, the raw material of everything around us. The universe is cool enough for the sea of quarks to bunch in threes, forming protons and neutrons. In the saga of the universe, this first chapter set the course of history.
The first second of the universe was an incredibly exciting and important time. During that first second, all the matter in the universe was made. All of the neutrons and protons were made. All the key components to make the universe today, we think were already in place. And then everything just evolved forward.
In the next few minutes, the universe cools enough for protons and neutrons to form the first atomic nucleus. 300,000 years later appears the first atom. In hundreds of millions of years, matter clumps to form the first stars. And in 1 billion years, galaxies like the Milky Way. More than 9 billion years after the Big Bang, Earth is born. One Big Bang, one single second. The genesis of everything.
By the time you've got to the end of 1 second, the rest of cosmic history is prescribed, including, ultimately, the future of the universe.
More than 12 billion years after the Big Bang, humans evolve. A species with the intellect to ask, how did we get here? And what is the universe made of? This year, science moves closer to discovering the answer. And the secret will lie in the first epic second. Of all the planets we know, ours is unique. The only one with water. We take it for granted, but without this magic liquid, life couldn't exist. Where our water comes from is one of science's greatest mysteries. From deep inside the Earth to the far reaches of space, the search begins for the source of our water. Earth is the only planet in the solar system with liquid water. 330 million cubic miles of it. It covers over 70% of the planet. It even makes up about 60% of our bodies. We know a lot about water, except where it comes from.
When we think about where Earth's water came from, it's not that simple, because we think that all the building blocks of Earth were probably completely dry.
If Earth forms without water, then where do our oceans come from?
It's a bit like a crime scene. The crime occurred a long time ago and the evidence has been tampered with. So it's very much like being a detective. You've got to look back in time to try and understand what was going on 4.5 billion years ago. It's a hard problem.
For the first time, scientists from different disciplines are working together to find the origin of Earth's water. The answer has the most amazing implications.
We know of no organism that does not require liquid water to live. And therefore, when we ask, how did a planet acquire its water? In essence, we're hinting at the question of what makes a planet able to support life.
In order to unravel this mystery, we must go back in time and look for clues at the birth of the solar system. 4.6 billion years ago, our sun is a newborn star, surrounded by a vast disk of gas and dust. Over millions of years, this disk of matter condenses to form the planets. Far from the sun, it's so cold, planets like Jupiter form with icy cores. Closer to the sun, it's more than 1,000 degrees hotter than it is today. Earth forms from substances that condense at high temperatures, like rock and iron. It's too hot for water. Earth is bone dry. For scientists, one possibility is that water was delivered by comets. From the frozen wastes of our outer solar system, they're mostly ice. Toby Owen has been studying comets for over 40 years.
As soon as people figured out that comets had a huge amount of ice in them, then it seemed reasonable that comets striking the Earth would have brought that ice with them, and so that ice could have melted and produced the oceans.
For 600 million years, the early Earth is bombarded by hundreds of millions of icy comets.
Comets are very primitive bodies. That's what makes them so especially interesting. The ice in comets is ice that has been untouched since the solar system formed.
So if comets brought all of Earth's water, then the water we drink, wash, and swim in fact, the water that makes up our bodies, is older than the planet itself and is from the edge of the solar system. But the evidence is still circumstantial.
We need some clues to discover how the Earth got water. We need some clues in the water on the Earth that we can relate to other things, like comets, to see if we can decide what brought the water in.
Luckily, water contains the perfect clues. To the naked eye, water looks the same, but there are subtle differences depending on where it comes from. All water molecules are made of 1 part oxygen and 2 parts hydrogen. But the hydrogen comes in 2 forms. The bulk of hydrogen in water is normal or light, but a tiny fraction, the blue bits, are heavy hydrogen. The ratio of heavy to light tells scientists where the water comes from.
You and I, and all the animals, and all the trees, and all the oceans, and all the lakes, and the rivers on the Earth have the same ratio of heavy hydrogen to light hydrogen. That's our water. That's the water of the Earth. So the question is, what is that ratio like in the kinds of objects that could bring the water to the Earth?
To find the ratio of heavy to light hydrogen in the water on a comet, scientists need to get a sample. Easier said than done.
One of the things that made people so interested in comets is that they're completely different from anything else in the sky. Suddenly, from nowhere, this huge bright object appears and moves through the sky and then disappears again.
Because astronomers never know when they'll show up, most comets are out of reach.
You'd have to keep a spacecraft in your garage, something like that, ready to go at any minute when one of those comets appears.
But one comet has a special place in astronomers' hearts. It's not the biggest or the brightest, but it is predictable.
Halley's Comet is special because it's a big comet, and still it is one whose orbit we know. So that means we can predict when it's coming back to the Earth. We can make that prediction very well.
In 1986, Halley was once again within reach, close enough to grab a sample. For Dr. Carey Liss, just seeing Halley's Comet was the chance of a lifetime.
I actually was excited about Halley's Comet, and at 1 in the morning, we were out there looking out in the sky, and I remember to this day we saw Halley's Comet really nicely. And that was very inspirational to me.
Because scientists knew where Halley would be, they could build a space probe for a rendezvous. The probe Giotto was designed to fly through Halley's tail.
One of the most exciting things that Halley gave us was not just here's a comet, here's what a comet looks like, here's the structure, but we could start doing chemistry. We could start understanding the composition of the comet.
Finally, scientists can analyze comet water and discover if it's the same as the water on Earth. On March 13th, 1986, after traveling for 8 months, Giotto enters the tail of Halley's Comet. Then a crisis. Giotto hits a large particle of dust, traveling at 42 miles per second. Communications with the probe are intermittent.
There was a tense moment there when people thought the whole thing might be lost.
32 minutes later, communications are restored. The probe samples the water vapor in Halley's tail and sends the data back to mission control. Astronomers are about to find out if the water on a comet is the same as the water on Earth. But when the results come back, the mystery only deepens.
And what we discovered, to our surprise, was that the hydrogen in the cometary water was about twice as massive as the hydrogen in water on the Earth.
With twice as much heavy hydrogen, the water on Halley's comet is not the same as the water on Earth. While it looks, tastes, and behaves just like Earth's water, to scientists, this difference is crucial. It can only mean one thing. Comets can't have brought all of Earth's water.
Well, that's a big, exciting result. It kind of defeats this lovely idea that comets brought all the water to the Earth.
In terms of did comets bring water to the Earth, it was a revolution and a change. And that's pretty exciting.
For years, scientists thought that comets were the source of all the Earth's water. But the evidence now makes this impossible.
So that was a very exciting result because it meant that you had to have some other source of water to produce the oceans that we see. And now we were going to have to go through the excitement of trying to figure out what really happened.
In 2002, a chance discovery suggests the answer might be closer to home. When the Earth first forms 4.5 billion years ago, it's too hot to form with water. But the planet has water now. If it wasn't delivered by comets, then has it been here all along? To find out where the water comes from, Professor Stephen Moyges is looking for clues to when it first appears. As a geologist, he uncovers the planet's past by looking at its rocks. But the past has a big hole. It's called the Hadean, or Dark Period, because nobody knows anything about it.
The problem of the first 500 million years of Earth history for geologists has always been that you have a nightmare scenario where you don't have any rocks or minerals to investigate.
It's thought early Earth is a fireball of molten rock, but with no evidence from this time, it's just a theory. Then in 2002, Moyges makes an earth-shaking discovery: the oldest mineral sample ever found on our planet, a crystal of zircon. Locked inside these tiny grains is a vital clue. Chemical analysis of zircon crystals reveals whether they formed in the presence of water. Over 7 years, Moyges finds and dates nearly 100,000 crystals of zircon. One stands alone.
The oldest one that we've found so far is 4.38 billion years old. Now, I'd like that to sink in.
When this crystal was made, the Earth was just 180 million years old. If this line represents the age of the Earth, then the dinosaurs died out here. Rewind about 4 billion years to the end of the Dark Period. The zircon crystal was formed here.
We're talking about time spans that are beyond comprehension. So for instance, in this rock here, there are zircon crystals that are 1/3 of the age of the universe. So these things have been around for almost as long as the Earth has been a planet. Talk about time capsules.
Analysis shows this 4.4 billion-year-old zircon crystal forms in liquid water. Rather than a dry planet, the crystal reveals that early Earth already has water on its surface.
When we made the discovery, that was very, very exciting because it wasn't fulfilling a hunch, it was true discovery. We didn't know what we would find.
For years, scientists thought that planet Earth forms dry. Moiges's discovery means that theory is wrong. Professor Mike Drake is searching for a new theory about how the early Earth forms wet.
Now, zircons tell you for sure when liquid water had to be present, and that's at about 4.4 billion years ago. And all of a sudden, we don't know where it came from. We've suddenly got a major problem. We have to seriously consider the possibility that water was present in the building blocks of the planet as it formed.
But how could water exist in the building blocks if the blocks were boiling hot? The answer requires another step back in time.
I finally went back to what the system looked like 4.5 billion years ago before there were any planets, and realized we had these fine grains of dust embedded in a sea of hydrogen and helium and oxygen, and some of the hydrogen and oxygen reacted to make water. So we basically had dust surrounded by water.
Over millions of years, the dust and gas condenses to form the planets in the solar system. Far from the sun, Jupiter and Saturn form with icy cores. But ice isn't the only way planets can lock in water. Further in, where it's too hot for ice, water can be locked into rocks, as this mineral demonstrates.
If you look at it, it looks really dry. If you touch it with your fingers, it's really dry.
But heat unlocks its secret.
And now you can start to see it's really boiling up into little balls of water. There's a huge amount of water coming off of this mineral. So a perfectly dry-looking mineral can contain a huge amount of water.
When the solar system first forms, the massive cloud of gas and dust traps the heat of the young sun. Where Earth forms, it's well over 1,000 degrees Fahrenheit. Too hot for such water-bearing rocks to form and build the planet. Yet soon after its creation, Earth manages to get water. Drake asks himself a new question. What if the early Earth traps water another way? A way nobody ever imagined.
One day I was drinking a nice cold drink, and I looked at the glass, and it had condensation on the outside of it, like this one does. You can see the water vapor on the inside if I run my finger around it. And I wondered if the same kind of process could have occurred in the disk around the sun 4.5 billion years ago. Could water have condensed out onto grains, much like it has onto this cold glass?
It's completely different to water-bearing rocks. If water vapor sticks to the grains of dust that build the planet, they could be the source of the oceans. An entirely new way for planets to form with water. He tests the theory with one of the main ingredients of planet Earth.
The green mineral in this rock is olivine, and olivine is the most abundant mineral that you find in the rocky planets. It's also the mineral that was abundant in the disk around the young sun 4.5 billion years ago.
He wonders if all the grains of olivine that form the planet have water stuck to them. He uses a computer to calculate the interaction between olivine grains and water vapor in the very early solar system. Water molecules stick to the olivine crystals.
So 30 grams of olivine allows me to absorb about 0.3 milliliters of water.
But can you capture enough water to fill the oceans? Drake has to scale up his calculations. How much water could stick to an Earth-sized pile of olivine grains?
Frankly, when we started these calculations, we didn't have a clue about how much water we could absorb. We were actually astonished when we discovered we could get 10 times the amount of water that's currently in the Earth's oceans.
Professor Drake believes as the early Earth forms, it already has billions and billions of gallons of water. Water that sticks to the trillions of grains of dust that build the planet.
It's really exciting to have come up with a new solution to one of the most fascinating and important questions that humans face, and that is, why do we have any water? Because without water, we cannot exist.
But Drake's theory is new, and not everybody's buying it. It has a flaw even he can't explain. The type of water. Our water has a signature. The ratio of heavy to light hydrogen in the Earth's water tells you where it comes from. The source of Earth's water should have a matching signature. But the water that condenses directly from the disk of gas and dust around our young sun is very different. It would look and taste the same as Earth's water, but it would have 6 times less heavy hydrogen.
Now, I don't mean to pretend that we've got the entire answer yet, and until we can show we can get the right ratio of heavy to light hydrogen, we cannot be certain that this process is responsible for the Earth's oceans.
If Earth's water doesn't come from the building blocks that form the planet, and it doesn't come from comets, where does it come from? Professor Alessandro Morbidelli has developed his own theory.
All of a sudden, everything fits together. And you feel you understand the piece of your past that nobody was there to observe.
Are the origins of Earth's water finally about to be revealed? The origin of Earth's water is one of the biggest mysteries in science today. Scientists are looking for a match. There must be somewhere in space that has the same kind of water as Earth. The answer may be locked inside this lump of rock and metal. Few people know more about these meteorites than Gary Huss.
Well, I grew up in the basement of a meteorite museum my grandfather had in Arizona. And so I'd go up and look around at the meteorites, and by the time I was 2, I knew all of their names. Once you get bit by a bug like that, you can't get rid of it.
While comets are made of ice and dust and come from the cold fringes of the solar system, a meteorite comes from somewhere else. Orbiting the sun between Mars and Jupiter are millions of lumps of rock and metal called asteroids. Some 200 miles across, weighing millions of tons. Leftovers from the formation of the planets. Sometimes asteroids collide, and fragments fall to Earth as meteorites. But what can they tell us about the origin of Earth's water?
The initial idea 100 years ago was that you had a major planet and it broke up and everything was dry and hot.
Looking at meteorites under a microscope reveals a different picture.
As we learn more about meteorites, it turns out that some of them are actually quite wet, a few % water.
This is a slice of a meteorite, known as a carbonaceous chondrite. The bulk of it, the black stuff, is a mineral with water locked inside. This fragment of rock was once part of an asteroid that formed 200 million miles away. It reveals that at this distance from the sun, asteroids formed with water locked inside.
There's water in the asteroid belt, and it's apparently always been there. We just didn't know how to recognize it.
Is there any water in the asteroid belt identical to water on Earth? To find out, Professor Huss measures the ratio of heavy to light hydrogen in the water-bearing meteorites. He can do this with an ion microprobe.
We were actually quite fortunate to get one of the very first of this newest generation of ion microprobe.
The machine fires a beam of charged particles at the meteorite. This expels all the hydrogen atoms in the water. The heavy hydrogen and normal hydrogen are then separated so he can measure the ratio between them. What Dr. Huss finds looks like a crucial piece of the puzzle. The ratio of heavy to light hydrogen in the water in asteroids varies. But some have exactly the same ratio as the water on Earth. It looks like scientists have finally found where Earth's water comes from.
So then the question is, how do the two things from different parts of the solar system end up with the same kind of water?
Chemistry can't solve the conundrum. But mathematician Alessandro Morbidelli has a radical theory that could explain how water from the asteroid belt ended up on Earth.
The idea was driven really by measurements, by the fact that the water on Earth is so similar to the water that we get from meteorites that come from the asteroid belt.
Morbidelli took a revolutionary look at an old subject, how the planets in our solar system were built. Before, scientists looked at the formation of the 4 planets closest to the Sun. They studied how matter near the Sun condensed into bigger bodies, eventually forming the planets Mercury, Mars, Venus, and Earth. Morbidelli has done something radically different. He's the first scientist to look at the formation of all 8 planets in the solar system as a whole. From Mercury, closest to the Sun, to Neptune, 80 times farther out.
The solar system is entirely interconnected, and we cannot study the formation of a portion of the solar system neglecting the other regions of the same system.
You can't study the planets in isolation because they're all linked by one force.
The only force that matters is actually gravity. So these things are relatively simple. We don't need to invoke strange physics or strange forces or dark matter.
As the planets grow, they interact because of gravity. Morbidelli recreates this interaction with a computer model, giving him a ringside seat at the birth of the solar system. About 1 million years after the birth of the Sun, the disk of gas and dust in the inner solar system condenses to form about 50 mini-planets. During the next stage, these mini-planets collide and form bigger planets. This demonstration shows what happens. The oranges represent mini-planets near the Sun. It's too hot for them to form with water trapped inside. As you move out, it gets colder. 230 million miles from the Sun, it's cool enough for mini-planets to form with water-bearing rocks. Green vegetables represent mini-planets with water.
The Earth eventually will have to form in this region, so in a region which is very hot, where nominally there should be no water.
If you look at the mini-planets close to the Sun, Earth forms from local material.
The mini-planets orbit around the Sun on trajectories which are almost parallel, like this.
Mini-planets collide to form the Earth. It forms from dry material.
But in this case, the Earth, because it formed from mini-planets which were dry, will also be very dry.
Luckily for us, this is not what happened, so we need to revise our model.
Because Morbidelli looks at the solar system as a whole, the whole scenario changes. Enter a new player, Jupiter. Jupiter is the biggest planet in the solar system and one of the first to reach full size. It's 300 times more massive than Earth. And in the early days of the solar system, it's starting to throw its weight around. Represented by this silver ball, Jupiter's massive gravity disrupts the orbits of the mini-planets.
Now, the mini-planets, in particular those farther out, have a more irregular motion, and in this way, the mini planets can mix with each other.
Earth now forms wet. Look at the formation of all 8 planets at once, and Earth forms from a mix of mini-planets, some dry, some wet. This model explains how Earth came to have similar water to that found in the asteroid belt.
All of a sudden, everything fits together, and you feel you understand a piece of your past that nobody was there to observe. These moments are fantastic. There are just a few moments like that in a career of a scientist, but even if it happens once every few years, those moments are so exciting that they are worth years of work.
Morbidelli's idea is now the leading theory of how Earth got its water. But it's not the whole story.
For the moment, it is the best answer that we have, but as we say, the devil is in the details. There are certainly some details we don't understand, so we need to keep working until we understand all of them.
The question is, what happens to the water on Earth during the continuing collisions with mini-planets the size of the Moon and Mars?
The energy of this collision is so high that it's capable of melting the entire Earth. In addition, it actually vaporizes some fraction of the Earth's rock.
If these collisions vaporize rock, how can the water survive? The origin of Earth's water remains unclear. Scientists have theories that can get the water to Earth, but can they keep it here? The final stage of Earth's formation is a series of cataclysmic collisions. Can water survive the process? The answer is in the night sky. Robin Canup has been working on the formation of the Moon for 13 years.
I think people are particularly fascinated by our moon because it's been our companion throughout all of human history and throughout all of the Earth's history. Every human that has lived has gazed upon the same moon.
The Moon was formed by a collision between the early Earth and a mini-planet.
The leading idea for how the moon formed is known as the giant impact theory. Just as the Earth was finishing its formation, the Earth experienced a collision with another planet-sized object, something that was smaller than the Earth, but still comparable to the current planet Mars in its size. So this was an enormous collision.
The last of several giant collisions between mini-planets that form the Earth. Why does this collision result in a dry moon and not a bigger Earth? Robin has developed a computer model to find out. The key turns out to be the angle of impact.
When this collision first comes in, it's at an oblique angle. The impacting planet is sheared apart into this long arm of debris that then wraps around the Earth to form a disk.
In no more than the span of a human lifetime, the disk of debris condenses and forms the Moon. So why isn't the Moon wet?
If you distribute that rock out into a disk around the Earth so that the disk is very spread out and there's a lot of surface area over which that rock can lose its water, then the water will tend to evaporate and be lost.
The model explains why the Moon is dry, but it doesn't explain what happens to the water on Earth.
The moon-forming impact is an event of such a scale that it's almost difficult to comprehend. If you've ever visited a volcano and seen the molten lava coming out of the Earth, that's what we mean by molten rock. That would have been the coolest material on the Earth after this impact. If you continue to heat that material even more, it will eventually actually vaporize. The moon-forming impact was energetic enough to do both.
These cataclysmic impacts should have driven off any water on Earth. The impact occurred about 4.5 billion years ago. And as this is the last cataclysmic collision that planet Earth suffers, the date is vital. Professor Moiges' zircons reveals Earth has water 4.4 billion years ago, very soon after the collision that formed the Moon. If the collision had blasted Earth's water into space, where did the water in the zircons come from?
Since water was present here in liquid form and abundantly very early on and soon after the moon forming event, it means that either the water was delivered very rapidly right after the moon formed, which I think is highly unlikely, or water was already present on or within the Earth before the giant impact that resulted in the formation of the moon.
So the Earth's water survives this last cataclysmic process of planet formation. But how? Professor Drake thinks the water has been here from the start. He has a theory about how it survives.
So the collision of a Mars-sized object with the Earth is an incredibly violent event. It'll melt the Earth. Now, the obvious question is, if the Earth went through such a violent event, how did it manage to keep its water? Most people think that if you heat something up, you boil all the water off, but that's not actually true. Any water that was in the Earth will be dissolved into that molten rock. That molten rock or magma is literally a sponge for water. You can dissolve vast amounts of water in liquid rock.
The early Earth is a giant fireball of molten rock. Dissolved inside are billions of gallons of water. But how does this rock become our blue planet?
This red-hot molten Earth is going to have lots of water in it, and that water's got to go somewhere when the planet cools down.
The rocks in this Arizona desert reveal what happens as the cooling rocks solidify.
A rock that crystallizes deep inside the planet will have the water kept in the minerals that crystallize. Here we have some micas. This happens to be a granite. And that water will be kept in the planet for 4.5 billion years.
Rocks that solidify deep in molten lava can hold water. But lava near the surface forms a different type of rock.
Any rock close to the surface, this one, for example, right here, you can see the holes in it, is going to lose its water. It's going to make little bubbles, which is what these holes are. Now imagine that there was rock like this all over the planet crystallizing. Water gets out into the atmosphere. Just look at the mountain range behind me and imagine the amount of hot, steamy water that could be coming out of these rocks as they crystallized.
All over the planet, water vapor escapes from the cooling rock. Earth's atmosphere is dense with steam. 100 million years after the impact that formed the moon, Earth has cooled enough to form a crust.
And you'll have boiling hot rain coming down onto the surface of the planet, running down in rivers, and eventually making the oceans.
But the story is still missing a chapter. Many scientists believe Earth has more than one source of water. Where did all of Earth's water come from? According to the leading theory, water arrived when mini-planets from farther out in the solar system collided with the early Earth. But scientists suspect this isn't the whole story.
I personally think there's more than one way to get the water to the Earth.
Like comets. Analysis of comets shows they couldn't be the source of all our water.
We can be pretty sure that comets must have brought in some of the water because we know comets must have hit the Earth. But the question is, how much? What is the fraction that they contributed?
The solar system may have furnished another source of water.
We've been hit by comets and asteroids, and some of the water may have come from there. But for me, it's a no-brainer. At least some, if not most of Earth's water had to come from absorption of water under grains before the planet ever formed.
But did these different sources bring enough water to Earth to support life? It's now impossible to work out how much of Earth's water comes from which source, because the water has been mixing for over 4 billion years. And over all that time, Earth's water has not only mixed, but changed.
The Earth's oceans basically have gone through a lot of processes since the Earth formed. There's rain and snow, and all of these things have caused the composition of the water to change a little bit.
By how much the water has changed, nobody knows. But there's a place where we might find out. A volcanic island chain in the middle of the Pacific. On the Big Island, Hawaii, Dr. Gary Huss is searching for the oldest water on Earth.
The Hawaiian Islands volcano is basically what's known as a hot spot.
A place where lava steadily oozes from the Earth.
The rocks that we're standing on in the Hawaiian Islands come from the very deepest part of the mantle of the Earth, thousands of miles below the surface. And it provides us a sample of material we could never get any other way.
When he looks at water locked in rocks drilled on Hawaii, Huss is actually looking at water from the middle of the Earth. Water unchanged since day one.
If you want to look at what the composition of the water on Earth is at the time that the Earth formed, this is the only place you can look.
Can Huss find evidence that there's primordial water deep inside the planet?
Oh, it's one of these guys? Oh, that's neat.
His approach is unprecedented, and early results suggest he might be onto something.
Well, this is good. This is a great sample for your purpose.
When we first found the hints, we definitely got excited about it. It does look like the water from deep in the Earth is different from the oceans, and it's different significantly.
So different, it could be primordial water, untouched since the birth of the planet. This research could ultimately deliver extraordinary answers to the question of the origin of Earth's water. And Hawaii isn't the only test site. The team is also sampling water from another hotspot, Iceland.
If we can nail this down for, say, the Hawaiian volcano, and then we can go to the Iceland hotspot and we get a different answer. Not only now do we have differences between the deep water and the surface water, we've got differences between a volcano on this side of the Earth and a volcano on that side of the Earth. There may be evidence for more than one source at this point.
One day, deep inside the planet, they may find reservoirs of primordial water different from each other. Such a discovery would mean one thing. Our water must have different origins. The implications are profound. For years, astronomers have been working toward one goal: scouring the skies in search of another planet like Earth. A rocky planet, just the right size and just the right temperature for liquid water and life.
We know now of 250 other systems that have planets in them, and we haven't found an Earth yet.
Billions of systems are yet to be explored, so the numbers are on your side if you're looking for another Earth.
We have 100 billion stars in our galaxy. Of them, we think about 10%, so 1 in 10 is a sun-like star. And we think that maybe 1 in 10 of those stars has planets. So that's about 1 billion stars in our own galaxy we think would have an Earth-like planet in it. Now, whether it has water on it is a different story.
Do any Earth-like planets out there have water? Could any support life? Today's telescopes can't answer that question, but computer models can. Dr. Sean Raymond has devised one.
We take our cues from observers. So with telescopes, people go out and find giant planets orbiting other stars. Then we take the orbits of those giant planets and try to figure out, in that system, could you still form a planet like Earth?
Raymond's computer model shows as planetary systems form around stars, some Earth-like planets end up with water.
We're modeling the formation of a planetary system here. All this red stuff is dry, the blue stuff is wet.
He starts with lots of mini-planets. Far from their sun, the blue ones have water. Closer in, where it's hotter, the red ones form dry. As the planets form, they start to cool. Like Earth, any planet warm enough to have water must orbit in the dry zone.
This guy right here is going to end up being a pretty good Earth analog.
The model shows how wet mini-planets from further out are pulled in to collide with a mini-planet in the dry zone, like Earth.
And there you just saw it turn from red to yellow to green. That's water delivery happening right there. And by the end of this particular simulation, it's very wet.
The result is a planet in just the right place for water, another Earth. Using the model, Raymond can calculate what's needed to form other Earths and how many there might be.
And we say, what if things were a little bit different, like we think they are around this other star? How would that affect the formation of planets like Earth, and how would it affect water delivery to those planets?
If Earth's water was delivered in more than one way, via comets, and with water as one of its initial ingredients, suddenly, the chances of finding an Earth-like planet with liquid water have just shot up. So too have the chances of finding alien life.
This is a big deal because are we alone in the universe, right? No one knows for sure. Everyone's excited about life on other planets. And what we're doing is one step towards trying to find life on those planets. It's really cool. I mean, it's very exciting.
And because scientists now think planets can get water more than one way, they're more confident than ever about the answer.
When people ask me if there's life out there, I say yes. And is there life like we know it, with a rocky planet where water has been brought to it? I think the answer again would be yes.
So by finding out how Earth got its water, we can find out how likely it is that out there somewhere, maybe millions of light years away, there are other alien forms of life. This is nature at her worst. Shredding buildings, drowning cities, killing thousands.
The hurricane is the most deadly and powerful system or phenomenon you're going to find on this planet.
They're the largest storms on Earth. How they gain such power is a puzzle with missing pieces. Scientists follow the life cycle of these killer storms, from birth to death, to solve the mystery. They are one step closer to parting the clouds, to reveal the anatomy of a hurricane. Hurricanes, nature's fury. A single strike can cost billions. Every year, hurricanes claim lives around the world, and they're becoming more powerful.
You have this whole devil's brew of things going on in a hurricane. Incredibly high wind, waves crashing on shore, intense thunderstorms. It's just an incredibly scary blend of things happening all at once.
Scientists struggle to predict where a hurricane will strike and how powerful it will become. Only by studying it from cradle to grave can scientists learn how it functions and perhaps forecast where and when it will hit. This is the story of science against nature at its most furious. Lives depend on the outcome. Over 80 hurricanes form each year around the world. Of those that form in the Atlantic, roughly 1/3 will strike America. The names are familiar: Andrew, Wilma, and Katrina. The future will bring new tragedies. And the race is on to understand how hurricanes work. Chris Lancy from the National Hurricane Center is trying to crack the hurricane code.
One of the primary goals of the Hurricane Research Division right now is to better understand the life cycle of hurricanes at their infancy, at their beginnings, the genesis, and to maturity, and then to the decay.
Ignition. The search for answers starts thousands of miles above the Earth. Satellites allow researchers to spy on a weather system born far out of sight of land. Images taken 22,000 miles above Earth reveal the genesis of the storm. 85% of major Atlantic hurricanes actually start in one of the hottest, driest places on Earth, Africa. In summer, the vast Sahara heats the air above it. As the air warms, it rises, climbing over 2 miles. The warm air pushes the existing weather patterns higher, forming an atmospheric disturbance. Scientists call this the African Easterly Wave. It travels west across Africa at about 500 miles a day. Converging winds on the east side of the wave trigger the development of thunderstorms, the seeds of our hurricane. Over the warm waters of the Atlantic, the thunder cells grow and merge. Atmospheric pressure within the weather system drops. Winds rush in to fill the gap and grow in strength. When they reach 23 miles per hour, meteorologists call it a tropical depression. Computers at the National Hurricane Center track every growing storm. Getting information as early as possible is crucial.
If we can't forecast, the genesis or beginning, we're going to be behind the curve in forecasting the rest of the formation of the storm itself.
Satellite data is vital, but it's not enough. They need to see inside the storm. That's the job of Jim McFadden, hurricane hunter.
You have to know what's going on in the storm full time. And the only way to get the information like the highest wind speeds, the lowest pressure in the center of the storm, is to actually put a plane into it.
The hurricane hunter's workhorse is the Lockheed WP-3D Orion turboprop aircraft, packed with scientific instruments and radars. They load data-collecting probes and fly out to meet fledgling hurricanes 5,000 feet above the waters of the Atlantic Ocean. The thunderstorms within the depression group together. Atmospheric pressure keeps dropping, causing wind speeds to increase. When they hit 39 miles per hour, the depression gets reclassified. It's now a tropical storm. The storm pulls in air over such vast distances, the air streams actually curve. Greg Holland explains how the thunderclouds begin to spin.
It steals some of the rotation from the Earth system to actually give it that turning. It's an effect we call a Coriolis force.
The direction of the storm's spin depends on whether it forms in the top half of the Earth or the bottom. In the northern hemisphere, the Coriolis effect pulls winds to the right and makes the storm spin counterclockwise. In the southern hemisphere, the wind is pulled to the left, which makes the storm rotate clockwise.
If there was no Coriolis, the hurricanes probably wouldn't spin up because the low pressures would be filled and that would be the end of the storm.
Rotation alone can't turn a tropical storm into a hurricane. Up to 28 tropical storms form each year in the Atlantic. On average, only 6 become hurricanes.
You have to have a few kind of key ingredients. You can almost say it's like a hurricane recipe for things to begin. One of which is you need a bit of spin to get things going. Another key ingredient is you need thunderstorm activity. Hurricanes are fueled by the thunderstorms. And the third key ingredient is you need a warm ocean. You need waters at least 80 degrees Fahrenheit for enough energy to be available for those thunderstorms.
The warm waters of the Atlantic Ocean act as fuel for the growing storm.
It's sort of like you go down to the tank and fill up your car. You put a certain amount of energy, if you like, into the car, and then you can drive at a certain distance.
As the surface water temperature of the tropical Atlantic rises, trillions of energy-bearing water vapor molecules evaporate into the atmosphere. They rise higher, they cool, and condense into clouds. This process releases heat, which warms the air around it, pushing the clouds even higher. Now the storm towers 10 miles high. The air within is no longer warmer than the surrounding atmosphere, so it stops rising. The system flattens out to form an anvil cloud. There's still one thing that could stop the storm from becoming a hurricane. High-speed, high-altitude winds. These can shear off the top of the storm, destroying its structure and the flow of energy within it.
You need what's called a minimum of wind shear. And wind shear is just the changing winds with height, the difference between just above the ocean and about 8 miles up. If that wind difference is about 20 miles per hour or greater, hurricanes don't form.
In the growing tropical storm, the wind shear is low and it continues to gain strength. As the winds hit 74 miles per hour, it gets a new name. This is now a hurricane. It has the potential to become the most destructive weather system on the planet. The hurricane is 200 miles across and heading straight for land.
Whether you're flying into it by aircraft or watching from space from our satellites, then it's approaching its most beautiful stage. So people like seeing them to some degree, but we also realize the horrible problems that hurricanes can cause.
McFadden's hurricane hunter team have to fly into these killer storms. With data from the eye of a hurricane, scientists can estimate how powerful the storm might become. The center of the storm is still hundreds of miles away when the hurricane hunters hit the first rain bands. These are fierce clusters of thunderstorms that spiral out from the center. They form as water vapor evaporating from the ocean rises into rain-bearing clouds.
We usually pick our way through the rain band so that we avoid most of the severe turbulence in a rain band, and then on towards the eye wall.
The eye wall is a dense wall of cloud around the hurricane's eye. It's where the weather is most extreme. Here, winds can reach 200 miles per hour. The rain is torrential.
It's where a lot of the upward transport of moisture, the conversion into clouds, and the heating occurs to get the cyclone going. So this, if you like, is the pistons of the heat engine of the hurricane.
The hurricane hunters make it through the eye wall. Inside, a circle of calm weather up to 40 miles across. The eye is the heart of the storm, the pivot the hurricane rotates around. At the center of the eye, the air is relatively still. No rain, blue skies.
When we fly into hurricanes, you don't see much, and you're going through the eye wall. It gets very dark, and then all of a sudden, the plane goes smooth, and we're in the eye, the calm part. And you're blinded for a second because the sunlight is so intense, and your eyes finally get used to what's going on. You look around, and you're in this, it kind of looks like a gigantic bowl. It's like a 40-mile wide football stadium, just what a hurricane looks like.
McFadden's mission is to drop a probe into the heart of the storm.
This is one of our GPS drop-ons, and it's proved to be probably one of the most important tools for collecting data in hurricanes that we've had over the last 10 years.
The probe parachutes down through the eye and measures the hurricane's temperature and humidity twice a second. Built-in GPS gives data on wind speeds and direction. But the most important reading is atmospheric pressure. As the hurricane grows, the pressure at its center drops. The area of low pressure sucks in more warm, moist air. If the hurricane hunters can get a pressure reading from the eye, meteorologists can estimate how powerful the storm may become and how long it may last. They also monitor the size and shape of the eye. As the storm gathers strength, the eye can contract, making the winds even stronger. In 2005, Hurricane Wilma did just that.
What this is a loop of the satellite imagery. And so this gives you a sense of the evolution of the whole life cycle of Hurricane Wilma. And you'll see the development of the eye, very tiny eye. When you get a pinhole eye, a very tiny eye, that's often indicative of a very small inner core. And in general, as the eye and eye wall gets smaller, you tend to have faster winds, stronger winds. It's analogous to an ice skater. As she brings her arms in and she's rotating, she spins faster.
Scientists classify the hurricane's strength according to its highest sustained wind speed, taken over a 1-minute period at 33 feet. Category 1, wind speed 74 to 95 miles per hour. Category 2, wind speed 96 to 110 miles per hour. Structural damage to roofs. Category 3, up to 130 miles per hour. Many buildings irreparable. Category 4, winds up to 155 miles per hour. It smashes solid walls. Category 5, the deadliest. Large-scale destruction and widespread flooding. Little can survive a Category 5 hurricane. In the Atlantic, the approaching hurricane is still a Category 1. Ahead lie 2,000 miles of warm water, fuel for a thirsty storm. The battle now is to predict how powerful it will become and where it will strike. A killer hurricane stalks the Atlantic. 8 days ago, it was just a cluster of thunderclouds off Africa. Now, it's a Category 2, over 200 miles across, winds near 100 miles per hour, and rising. In less than 48 hours, it will hit America. But where?
Nowhere is safe on the Gulf Coast or the East Coast of the United States. And the more we can understand of the dynamics of these storms, the more we can understand what exacerbates the impacts, the better it is for everybody.
It's vital for meteorologists to understand why hurricanes take a particular path. If they can better predict where these killer storms will hit land, they can broadcast more accurate warnings and save lives.
Now, how a hurricane moves is due to a number of different factors, of which there are two main ones. The first is that it acts just like a cork in a stream. It is actually blown along by the large-scale atmospheric winds in which it's embedded. Then the other major component is that they actually use up a little bit of the Earth's rotational effect to allow themselves to push themselves along.
To predict where the hurricane will strike, meteorologists need information about the weather systems that surround it. The trade winds, a prevailing pattern of winds found in the tropics near the Earth's equator, push the hurricane west at speeds of up to 20 miles per hour. But before the storm makes landfall, it must negotiate a region of high pressure off America, known as the Bermuda High. This high-pressure dome moves across the Atlantic and creates winds that spin clockwise. Depending on its size and position, it can steer a hurricane harmlessly into the Atlantic or straight into land.
It's the changes in the wind flow that are important. Whilst however the wind is in one direction, It's great for forecasting because it makes it really easy. It's when they're at that change state that it becomes very, very difficult.
Meteorologists have recorded the paths, frequency, and intensity of Atlantic hurricanes. Where and how a hurricane strikes can appear random. Scientists use computer models to try to establish patterns to better predict where and how powerfully it will hit land. Joe Sion works to improve the data that inputs into these models.
What models are doing are trying to, as closely as they can, simulate exactly what Mother Nature is doing. And once we get to the point where we say, you know, we have done that, we have improved the model's representation of nature, what will result is improved forecasts going forward.
Over the last 20 years, computer models have made huge advances. Faster, more powerful processors, better weather data, and greater knowledge of hurricane anatomy allow meteorologists to make better forecasts. Robert Rogers and his team at the Hurricane Research Division play a key part in piecing together this puzzle.
The track forecasts have improved significantly, but our intensity forecasts have essentially remained constant. They've not improved or improved very little over that time. So we have our work cut out for us, and that's really what we're focusing on now.
Scientists now have a much clearer idea of where a hurricane will strike. Estimating how powerful it will become is tougher. The hurricane tracks 500 miles south of Bermuda. It's now just 36 hours from landfall. It's already a powerful storm. If it hits an ocean current or eddy where the water is even warmer, it could rapidly intensify. The warmer the water, the more powerful the storm.
And it's sort of like you put a bit of turbocharge into your car. Suddenly it's got more fuel, suddenly it can actually start accelerating its intensity, and away it goes.
It's what meteorologists fear most, a storm that gets a kick of energy.
From a forecasting standpoint, that's kind of the nightmare scenario. So whereas, people went to bed one night expecting maybe a Cat 1 to make landfall, they might wake up the next morning and looking at a Category 3 or Category 4.
Scientists don't know why some hurricanes rev up and others don't. The answer may lie in a part of the hurricane called the boundary layer. It's the region at sea level where the hurricane draws its energy, where sea and air interact.
So if we want to really get a good handle on intensity change, we have to understand how the energy is transferred out of the ocean.
Sion is part of a team trying to unravel what happens at the boundary layer. To bring back the data, scientists must skim over waves up to 3 stories high and fly straight into one of the most dangerous places on Earth. The hurricane is 36 hours from hitting America. Winds near its eye blow 115 miles per hour. It's 300 miles wide and still growing. Question is, will it get a jolt of power? Some scientists believe the answer lies in the boundary layer. It's here the storm draws heat from the sea as fuel. Scientists need to refine their understanding of the exchange of energy that happens here and how wind speed, friction, humidity, and air and sea temperature affect how the hurricane intensifies. Until recently, scientists lacked reliable data from the boundary layer. September 2003. As part of an experiment called Sea Blast, hurricane hunter planes flew straight into the deadly boundary zone of Hurricane Isabel.
Sea Blast itself was to look at the dynamics of the boundary layer in a hurricane. We were willing to fly down to 200 feet as long as we can maintain visual contact with the surface.
Below, a churning mass of 40-foot waves. Around them, wind eddies that could swat them out of the sky.
When you're flying that low, you can see every single wave. And some of these 30 or 40-foot waves look visually like they're about to touch the plane.
They flew so low, sea spray drenched the plane.
We noticed that the windshield was turning white while we were flying at 200 feet in a hurricane. We didn't realize, though, that all that salt was coating the engines.
One of the engines had a problem, and we had to secure it, turn it off.
They regained power just in time and limped back to base. Their data gave scientists fresh insight into how wind speed affects the amount of energy entering the storm. As a result, new data was fed into computer models. Data from the boundary layer will improve the accuracy of forecasts. But data from these missions isn't enough. And Operation Sea Blast proved flying through the boundary layer is too risky. How to get more data without risking lives? Don't send people, send a probe.
What you're looking at here is the Mark III aircraft. It's an Aerosonde Corporation aircraft. That we think that this is a very compact aircraft that can do a lot of things and measures what we needed to measure.
Sion's team loaded the Aerosonde with instruments to measure meteorological conditions within storms. It headed toward the hurricane's strongest winds, piloted via satellite.
Only 100 miles since our turn.
In 2005, they flew into Tropical Storm Ophelia.
We rode it up and down, and the aircraft survived that. And this is the first time we've really been able to look at data like this.
The Aerosonde can fly into the deadliest parts of the hurricane and stay there up to 12 hours.
The only thing I can compare it to is what I saw on TV with these Mission to Mars, where the group of scientists send something out and you see them cheering when it finally gets on the surface of Mars. You just feel just a great sense of accomplishment. And for me, it goes beyond that too, because I know what we're doing is really, we're trying to help people. We're trying to save lives.
Scientists hope that in the future, Aerosondes will regularly fly into the hurricane's boundary layer and send back constant data. This will improve their understanding of how storms intensify and help them spot the warning signs. The better the forecasts, the more lives saved. 24 hours from landfall, the hurricane has strengthened to Category 5, a 350-mile-wide heat engine. It converts the warmth of the sea into winds over 155 miles per hour. Inside the storm, rising water vapor and churning seas mean the hurricane picks up 2 billion tons of seawater every 24 hours. The rains inside the storm are torrential. The path is set. Hurricane historian Jay Barnes knows what happens next.
Here we have a hurricane about to strike land. We know what is going to happen because we've seen it happen before. A powerful storm, very, very large in diameter, going to affect hundreds of miles of coastline.
A hurricane's biggest killer is water. Not rain, but a wall of water called a storm surge. 90% of all hurricane deaths are from drowning. Oceanographer Stephen Begg watches the Atlantic for the first signs of the surge.
Storm surge is not something that's been seen by very many people, and even fewer survivors, so that it's hard to describe to people.
Forecasters monitor the hurricane closely. From the wind, Ivar Van Heerden picks up clues about the size of the surge.
The stronger the winds, the more water you blow towards the shore, the more surge you're going to see.
As the first part of the eye wall hits the coast, winds accelerate. The surge reaches its peak.
The surge intensifies as the eye gets close because the strongest winds are around the eye. So you then, under the influence of the stronger winds blowing the water landwards, piling it up on top of what's already been piled there, and that's when you get the intensification.
The highest winds blow on the right side of the storm. If the right side strikes first, the surge will be worse. That's because the hurricane is not only spinning counterclockwise, but is being driven by winds across the sea. On one side, spin adds to forward motion. On the other, it subtracts. A storm spinning 90 miles per hour and moving forward at 10 will have winds of 100 on the right side and 80 on the left. The higher the winds, the higher the surge. August 2005. A Category 1 hurricane struck Florida, then transformed into a 400-mile-wide killer in the Gulf of Mexico. It was set to strike the Gulf Coast, right-hand side first. The hurricane's name, Katrina. Professor Van Heerden watches the path that Katrina is taking.
We started to suspect that Katrina potentially could hit New Orleans even before it made landfall in Florida. And the reason being the weather patterns were such. The Bermuda High had moved a little bit to the west, that the wind currents would be bringing anything that entered the Gulf of Mexico into Louisiana. The curvature was there. And of course that proved true.
At 6:10 a.m. on the 29th of August, Hurricane Katrina hit the coasts of Louisiana and Mississippi. In the midst of the carnage is storm photographer Mike Tice.
The storm surge was coming up to Highway 90, and by 8 o'clock, it was already coming to the front steps of the hotel. When the storm surge started to get around 12 to 15 feet, it made it into the first floor of the hotel, and a car comes floating through the hotel lobby. I saw it coming ahead of time in the parking lot. It perfectly came in, so it came directly through the front glass doors, crashed into them, and the horn started honking, the lights started flashing. It was echoing inside this lobby. Of course, all the power's out. It's pitch dark in there. And it is one of the most horrifying, scary things I've ever seen in my life. It was straight out of a scary movie, and I don't think I could ever have imagined I would ever witness something like that in my life.
The highest storm surge ever seen in America sweeps across the entire region.
This rise of sea level in some areas estimated over 27 feet. And if you can imagine the beachfront like we're standing here today, a 27-foot elevation of the surface of the ocean, with waves, battering waves on top of that, it's quite destructive. And that's what caused the tremendous destruction we saw along the Mississippi coast.
The surge built along the Mississippi Delta. In New Orleans, the levees burst. A city drowned.
We knew that we were going to be dealing with very high death rate. 10 years of research, looking at lots of other floods all over the world, just cannot prepare you to see miles after miles of subdivision and only the roofs are visible. And of course, on the roofs, people frantically waving for help.
Over 1,500 people died. A tragic testament to the power of storm surge. Now it's the turn of the hurricane's eye to hit land. The storm passes over its own havoc. For 1 hour, the rain stops. Clear skies and sunshine break through. What was destroyed in just hours will take years to rebuild. And still, we have seen only part of the hurricane's deadly arsenal. more damage is coming. The hurricane is only half over. Its other lethal weapon returns for a second attack. Wind. Ten days ago, this storm was a cluster of thunderclouds off Africa. Now it's a hurricane at the height of its destructive powers. The storm surge caused terrible devastation. Winds cause even more. As the eye passes over, the other side of its wall hits, and the winds switch direction. At first, this helps. Floodwaters are pushed back out to sea as quickly as they came.
As soon as the eye goes by, the winds start blowing from the opposite direction and it starts blowing the water offshore, so that you get the very rapid set down.
As the deluge of water drains away, the hurricane begins to move further inland. Its strongest winds, over 155 miles per hour. The eye wall.
The winds are toppling power lines and knocking down trees, blowing the roofs off of homes and smashing windows. It really is a scene of chaos as the most powerful part of the storm strikes the coast. That's when you see the greatest intensity of impact.
Low pressure pulls air in toward the center of the storm as wind. The closer to the eye, the faster the winds. Some of the inrushing air gets pulled into strong updrafts, and centrifugal force generated by the hurricane's spin pushes some air away from the eye. Most rams into the eye wall, creating a spinning tube of wind and cloud. Bob Henson studies the architecture of this force.
So in a mature hurricane, you've got this complex dance, and it's a very symmetric and beautiful thing, actually.
This delicate balance of forces shapes the speed and direction of the hurricane's internal wind.
So what you really have in a hurricane is wind parcels rotating around the center of the hurricane, like the nickel is here, but spinning faster and faster as it nears the center and tries to rise up, and then finally does rise through the very center of the hurricane, as we're seeing right here. That's what actually happens in a hurricane.
A hurricane's strongest winds are just above the ocean and close to the eye wall. Away from the center, winds slowly weaken. Yet even 60 miles from the core, it gusts well over 100 miles per hour. The damage can be colossal. At the University of Florida, scientists are working with engineers to design hurricane-proof homes. The first challenge for Forest Masters is to test buildings under realistic hurricane conditions.
So we're trying to understand how does the whole building perform, in concert to resist these extreme loads.
To test how a building will perform, Masters measures hurricanes at work. His team deploys hurricane-proof towers, loaded with equipment, to measure the winds 33 feet up.
It's incredibly dangerous deploying this kind of instrumentation in the path of a landfalling hurricane. We don't have a lot of time. We wait to the last possible minute to be certain that we know where the storm is going to go.
The data lets Masters map the wind itself. His results confirm the winds change radically once the storm moves off the ocean and hits land. Buildings and even the ground itself cause friction and reduce average wind speed. But as winds are forced over obstacles, gusts become more intense. These turbulent blasts of air can turn a home into matchsticks in minutes. Masters feeds data from the towers into a hurricane simulator. He aims to recreate a Category 3 storm to test how a window performs. This machine really blows. 8 5-foot-tall industrial fans, powered by 4 vast engines, produce the winds. A 5,000-gallon water tank cools this vast machine and provides the rain.
We're taking that turbulence data and we're trying to replicate that at sufficient scale to immerse a low-rise building. And that allows us to look at the performance of all the different parts of the building, such as the windows, doors, and roof cover systems.
The simulator mimics the gusts and driving rain of a typical hurricane. If the hurricane can get inside doors and windows, the difference in pressure can tear the house down. This window is being hit by Category 3 force winds. So far, it's impervious. Piece by piece, the team tests windows, tiles, studying the ways in which hurricanes expose flaws in design and assembly.
Ultimately, if we can make better buildings, stronger buildings, perhaps we can modify our evacuation policies so that people can stay in their homes longer, or in a higher and more intense events.
As the hurricane travels inland, the value of this type of research is obvious. Buildings with any weakness are ripped to shreds.
My house has just launched a whole bunch of missiles into the air, which is going to damage your house. Your house is going to launch a bunch more missiles into the air, which is going to damage the next house down. And suddenly we have this mass of flying debris that is doing an enormous amount of damage.
The storm moves 15 miles inland every hour. The further it moves away from the ocean, the weaker it gets. Winds drop by half every 7 hours. The hurricane is dying, but it's not dead yet. The hurricane hits land as a full-blown Category 5 storm, a blast of destructive energy. It creates vast floods and devastates coastal towns and cities. But as it leaves the ocean behind, it loses power. A hurricane needs fuel.
When a strong hurricane makes landfall, you see some changes to the characteristics. The structure starts breaking down.
Really, over just a few hours, the death warrant has been written.
The energy source was heat from the warm ocean. Dry land lacks the fuel to keep it going, and the storm's heat engine stalls. The hurricane releases more energy than it gains. Its internal structure, the inflow and outflow of air, disintegrates.
If you're going to write an autopsy of a hurricane that makes land, it probably would say death by lack of warm water, because once the hurricane has moved off the ocean, it's lost that source of heat that sustains it.
Near ground level, the inflowing and outflowing wind meets friction from land, trees, and buildings. The low-level winds die. With no energy coming in, the storm's air circulation falters.
In addition, the winds start to feel the trees and the houses, which impact a lot of friction, and it slowly but surely spins down.
It's like a car running full throttle on an ounce of gas. In one day, a Category 4 hurricane can shrink to a mere breeze. If the hurricane hits mountains, it will die even faster. But sometimes, the storm is thrown a lifeline.
Sometimes a hurricane may briefly re-intensify, and this is a process that's rare and not well understood, but if it passes over very moist land or a marshy area or so forth, it may get a little pulse of energy, and if other conditions are favorable, you might get a brief spin of it.
August 24th, 1992 at 5:30 a.m. Andrew slammed into Florida as a Category 5 storm. After landfall, its winds faded. It limped across Florida for 4 hours, passing over the Everglades. Warm, shallow water temporarily nourished the storm and allowed Andrew to make the deep waters in the Gulf of Mexico. Andrew revived and became a Category 4 storm. It pounded Louisiana. It took another 24 hours for Andrew to die, this time for good. The death of a hurricane marks the beginning of its autopsy by the scientists.
We do an evaluation of the storm itself, the whole life cycle from birth to maturity to decay, and try to summarize that as well as the impacts on people.
Scientists have improved their track prediction by 50% in the last 20 years. Huge advances are being made in forecasting just how strong a storm will become. But they may have to factor in a new twist. What will be the impact of rising global temperatures?
We've had a lot of Category 5s just within the last few years. So there's been a lot of discussion and a lot of questions about are we seeing an impact from global warming on this hurricane or that hurricane?
Climatologists combed through more than a century of records. They found that average ocean temperatures in the tropics have risen by 1 degree Fahrenheit. Hurricanes get their energy from warm water. Logic suggests stronger hurricanes. In 2008, the United States Climate Change Science Program announced their conclusion. It points to an increase in hurricane intensity or strength.
It is very likely that the oceans have warmed up due to climate change. It is very likely that we will see, and indeed are seeing now, increases in rainfall in hurricanes because of this, and increases in the maximum intensity.
For now, meteorologists concentrate on the present. Their work continues to reveal new aspects of the birth, life, and death of the deadliest weather system on planet Earth.
We've reached the point where our meteorologists are doing a super job of telling us where they are, where they're going, and what to expect. Well, one of the things that we can all expect is that they're going to keep coming.
Science has shown us the anatomy of a killer. We can't prevent them, but we can learn to predict them. With each new piece of the puzzle, science saves more lives. The power of a hurricane is awesome. They're striking earlier than ever before.
I realized that this was going to be a historic event.
They're getting stronger.
Is there anybody else in there with you? Do you need help? Is there anybody else down here?
And they're striking places they've never been.
If you're living north of Tornado Alley, sometime in the future, tornadoes will start showing up on your doorstep.
Tornadoes are changing. The events of one tragic day will tell us why. A terrifying glimpse of the future that holds the key to saving lives. February 5th, 2008. Super Tuesday. Out across the Central Plains, a storm is brewing. This will be no ordinary storm. As cold, dry weather streams in from the Rockies, unseasonal warm air forces its way north from the Gulf. Where they meet, history will be made. No one expects to see this kind of weather in winter. The first sign of trouble arrives late in the morning. Massive thunderstorms are forming in a line over Texas.
My initial thoughts were I need to get the word out. It's obvious that we are dealing with a major storm system that will produce widespread dangerous weather and that people are at risk.
And by mid-afternoon, the system is beginning to develop the most powerful storms of all, supercells. One hour later, the situation on the ground goes critical. The start of a trail of death and destruction that sees 87 killer tornadoes drop from the skies over Mississippi, Alabama, Arkansas, Kentucky, and Tennessee, wreaking more than $500 million of damage. "57 people will perish. One of the worst tornado outbreaks ever recorded. But the implications are far worse. Scientists looking at Super Tuesday see a dark future. Stronger, more destructive tornadoes striking outside the traditional tornado season. Striking in places they have rarely been seen before. Tornadoes are changing. So what exactly is happening? The answers lie in the rubble of Super Tuesday. Solving the mystery of this devastating outbreak is a matter of life and death. The investigators start with the biggest mystery of all. How does a tornado form? From here, they can work backwards and figure out what was different about the storms that gave birth to the tornadoes of Super Tuesday. What they know for sure is that tornadoes form in storms like no others. Hurricanes take days to develop, cover thousands of square miles, and follow a discernible path. They begin life in Tornado Alley, stretching from Texas through Oklahoma, right up to Iowa and Nebraska. Vast and flat, and caught in an atmospheric crossfire between north and south. The weather here has all the right ingredients for twisters, and spring is traditionally tornado season. As winter turns to spring, polar air from the Rockies spills across the plains. It sets off on a collision course with warm, moist air heading north from the Gulf of Mexico. The stage is set. Warm air is light and wants to rise. Cool air is heavy and wants to sink. When the two air masses collide, they begin to spin. Tornado expert Robin Tanamachi has a simple way to demonstrate what happens next.
What we have right now is a very unstable arrangement. You can see we've got this very dense, heavy water up in the upper chamber, and the lower chamber is filled with air, which is much less dense than the water. And the air wants to go up into the upper chamber, the water wants to come down.
Scale this instability up a few thousand times, and you get vast thunderclouds called supercells, the birthplace of tornadoes. Compared to regular thunderstorms, they can span 20 miles across and tower twice the height of Mount Everest. Supercells are the most ferocious of all thunderstorms. But the energy in the storm needs an outlet. The cold air wants to sink, and the warm air wants to rise. In order to restore the balance and release the energy, another ingredient needs to be introduced.
You can see some of the air bubbles are kind of traveling up into the upper chamber, but this is a pretty inefficient way to restore the balance to this unbalanced system. And so what I'm going to do is impart a little bit of vorticity to the system by sloshing it around a bit so that now it spins. And now we have a vortex that's formed in the middle, so that now the air is flowing upwards through the center of that vortex into the upper chamber, and the water is flowing downwards into the lower chamber, so that this is a much more efficient way for the system to go back into balance.
The imbalance allows the warm and cold air to mix by spinning them together. It's the fastest way for the heavy air to sink down. This spinning is known as wind shear. This is the second vital ingredient for tornadoes.
So relatively weak winds at the surface, topped by stronger winds aloft, create this roll, and that is shear.
So they know how supercells are created. But why a supercell creates a twister is the last great weather mystery. It seems clues may lie in the spinning motion itself.
Many researchers who've studied them have sometimes called them accidents of nature because it seems so elusive to figure out what actually went together to cause the tornado at the ground. We know how to get a lot of spin in a thunderstorm, but there are definitely some more complex things going on near the ground. We can have spin taking place on small enough scales that we really aren't able to measure it.
Only one supercell in 4 gives birth to a tornado. So what makes that one so special?
We do not know yet what the mysterious missing ingredient is. We think we know what it takes to get a tornado, but there's something mysterious that we still don't understand that determines, sometimes a tornado will touch the ground, sometimes it won't.
But when it does, the results can be devastating. Once the funnel touches down, it starts feeding on an inflow of warm, moist air at ground level. This warm air is called updraft. Low pressure inside the vortex creates a vacuum, and the warm, high-pressure air around it rushes in. Once inside the funnel, the warm air shoots upward, trying to restore the balance, all the time sucking in more and more warm air from the ground. The warm air is the fuel that gives it the energy to move forward. Its funnel sucks up debris as it tracks along the ground. You not only see it coming, you hear it.
Oh, no, don't go! Jesus Christ!
There have been descriptions of tornadoes that vary from a roar like a freight train, depending on how fast the tornado is moving. If they're inside of a house, they may report that it makes a very high whistling sound, say if it's coming through cracks in windows or something like that.
Yes, a large destructive tornado. There's a large tornado moving through the south side of Atkins.
On Super Tuesday, one of the worst tornadoes ever seen in Arkansas rips through the state, traveling a record 122 miles. Across 7 counties, it leaves 13 people dead. 100 homes in the little town of Atkins are torn apart. But what makes this tornado so unique is that it happens at the wrong time of year. Powerful tornadoes like this very rarely strike in winter, yet Super Tuesday sees 87 of them. Investigators now turn their attention from the tornadoes to the storms that made them. The answers they are about to uncover will bring them one step closer to understanding why tornadoes are going to get worse. On the 5th of February, 2008, a devastating tornado outbreak claims 57 lives and leaves experts baffled. 87 powerful tornadoes striking in winter is rare.
Once I sat back and realized it was only the 5th of February, then I realized that this was going to be a historic event.
Freak weather? Or is a pattern emerging? To find out, scientists rework the events leading up to Super Tuesday. One day earlier, and meteorologists at the Storm Prediction Center notice a dangerous wind pattern, one that usually occurs in spring. They are surprised to see warm winds moving north, cool winds heading south. When they meet in Tornado Alley, the chances of tornado formation will be high. Yet tornado season is still 2 months off. Why are these two spring air masses meeting in winter? The answer is found in a strange ocean current 1,000 miles away in the Pacific. Joe Schaefer, the director of the Storm Prediction Center in Oklahoma, wanted to find out what caused winter tornado outbreaks.
Super Tuesday was in February. To the general public, it probably did come as rather a surprise that you're having this strong activity in February.
He begins by looking for a bigger pattern.
Newest ones are white, the oldest one.
Could the arrival of spring weather in winter be anything to do with La Niña, a vast ocean cooling event in the eastern Pacific? It's a long shot, but he knows it causes extreme weather in the most unlikely places.
There has to be some clues to what Mother Nature is really going to do.
There are always larger patterns at work. The El Niño and La Niña cycle are one of the biggest. The cycle affects vast ocean currents, which govern the warming and cooling of the oceans. The El Niño current drives east, carrying the warm waters of the tropics to the west coast of the Americas. As it does, it warms the atmosphere above it. El Niño lasts about a year. The cycle then reverses and the temperatures drop. This reversal is called La Niña. This current carries cooler seas and cooler air above. The cooler seas of a La Niña year are famous for influencing the increased strength of Atlantic hurricanes. But no one had yet proven a link to tornadoes.
We just looked at the number of tornadoes all across the country and tried to see if there was a relationship between the tornadoes and whether you were in a El Niño, La Niña, which is the opposite, or a neutral pattern, which is neither one. So we looked at those and found absolutely nothing.
Other meteorologists were also searching for a link. But weather systems are some of the most intricate patterns known to science.
People would find one thing, these people would find different conclusions. I more or less had come to the conclusion that there wasn't any link on the thing.
He couldn't believe Super Tuesday was a random event. He was convinced that there was a relationship between events like Super Tuesday and La Niña.
You always have the hope that there's some seed out there of truth, or I never would have looked at it in the first place if I really didn't think someplace in my core that there had to be some kind of relationship.
One day, Joe and his grad student have a brainstorm. Instead of counting each tornado in each year, they look only at outbreaks, days with 6 tornadoes or more. For the years they study, they find twice as many outbreaks occur in a La Nina year than they do in an El Nino year. This doesn't yet explain why the Super Tuesday outbreak occurs in winter. So they refine their search. They begin to focus only on winter tornado outbreaks. They discover that during a La Nina year, winter tornado outbreaks are likely to be more severe. 2008 was a La Nina year. The implications are enormous. Conclusive proof that the winter outbreak on Super Tuesday is caused by the La Nina effect. It's an incredible breakthrough. The mystery of how deadly winter tornado outbreaks can happen is now solved. They realize that La Nina strengthens the cool winds from the northwest, which intensifies wind shear and creates more violent tornadoes. The breakthrough is a milestone in tornado research.
Science is such that if you can actually see the relationship and prove that it exists, then you've made a contribution.
A contribution that may help forecasters save lives in the future. But the mysteries behind the Super Tuesday outbreak are far from solved. We know why it happened in winter, but what scientists now need to find out is why are they so unusually powerful? Forecaster Greg Carbon and his team are the first to spot where the trouble is brewing.
The first watches that were issued across Arkansas were to get the word out that dangerous weather is on the way. Despite the forewarning, despite the watches, and even the tornado warnings that were issued during the event, we still had loss of life.
Nothing can prepare them for the destructive power of the tornadoes they are about to see. Super Tuesday, February 5th, 2008. At 5 p.m., a giant tornado descends on Arkansas. 7 counties lie in its path. The power of this monster is about to take everyone by surprise. Using a system called the Enhanced Fujita Scale, scientists classify the strength of a twister between EF0 and EF5. EF0 can break branches from a tree, and EF2 can lift a roof off. Anything above that is rare. The vortex in an EF5 can reach 300 miles an hour, the fastest known winds on our planet. With wind speeds around 200 miles an hour, the Arkansas tornado is an EF4. And it isn't the only one. Another EF4 tornado touches down in Jackson, Tennessee, 300 miles away. It shreds Union University. Across Tennessee, 1,000 houses destroyed. 32 people killed. Debris is found 70 miles from where it was lifted. Super Tuesday's 5 EF4 twisters reveal an alarming trend. Stronger tornadoes lasting for longer. In a matter of hours, they clocked up more than a quarter of the average annual death toll. To understand why they are so destructive, scientists need to know, where is their energy coming from? Is it also connected to the powerful ocean current during La Nina? If so, how? The first clue lies 30,000 feet above the Great Plains. An invisible force traveling at 300 miles an hour is steering the storms and spinning them faster. A ribbon of wind called the jet stream. It speeds through the highest part of the sky, called the troposphere. The jet stream forms where cool air from the North Pole meets warm air from the equator. As the Earth spins, it sends the air shooting west to east at the point where the two air masses join. As polar air and Gulf air meet, the warm air is sucked up through the thunderstorms and into the troposphere, where it crashes into the jet stream. As the jet stream shoots across the United States and over the tops of the storms, it sucks on these updrafts, spinning up the storm. Just as a gust of wind across a chimney will strengthen a fire, the jet stream strengthens storms. On Super Tuesday, it's winding them up and steering them across the plains.
Here you come, Ryan. I've got the analysis, and it looks like we're starting to see moisture increase across this area and Q coming up. The watches were up. We knew that this potential existed downstream from Arkansas off to the east. It's not that the cells in Arkansas moved directly into parts of Tennessee or across the Mississippi Valley. We now had new development occurring in parts of Mississippi and Tennessee. And that new development quickly acquired supercell characteristics. And the event began to unfold quite rapidly during the evening hours.
By 5:25 that day, the jet stream hurtling across the Midwest was powering up one thundercloud after another. As the monster storms advance on Tornado Alley, some 20 million people are in their sights. When scientists look closer at the events that unfolded on Super Tuesday, they find a compelling piece of evidence that links the strength of the jet stream and the destructive force of the tornadoes to the Pacific Ocean current, La Nina. Because what Dr. Schaefer also discovers is that La Nina not only makes winter tornadoes more likely, it also makes them more powerful. During La Nina, cooler temperatures in the eastern Pacific create stronger easterly winds that make the jet stream flow faster. A faster jet stream spawns stronger tornadoes. They spin faster and track on the ground for longer. The result is more destruction. With such high speeds, the debris a powerful tornado carries can turn into missiles. A stalk of straw can fly fast enough to pierce a telephone pole.
Just hit us. It just blew all the glass out and swooped us up in the air, and the next thing I know, we were flipping and flying and landed over here.
Super Tuesday 2008 was one of the worst tornado outbreaks ever. But could tragedy have been prevented? Doug Forsyth at the National Severe Storms Lab in Oklahoma has just set up a new kind of early warning radar station using technology developed by the military. Phased array radar. Traditional radar starts scanning at the bottom of a storm. By the time it gets to the top, the bottom has changed. Too slow to catch every detail of a tornado forming. But phased array radar uses multiple beams that scan in rapid succession.
To improve our lead times, we need to scan faster. With a phased array, if I can do that in less than a minute, then on the second minute, I'm already issuing the warning. So I've already increased my lead time by about four minutes. We're now getting about 13-minute lead time, which is a pretty good lead time, but we'd really like to extend that.
Phased array radar is a 2-for-1 gift. It could be the tool that leads researchers to cracking tornado genesis. And it gives forecasters more time to issue warnings. On Super Tuesday, this could have saved lives. Robin Tanamachi's team now includes a truck with phased array radar. Instead of waiting for storms to hit Doug's radar station, they can go and seek them out.
We in our radar research group feel like we're on the cutting edge using this brand new phased array technology. You get a more detailed picture of the evolution of the storm. You can watch it evolve in much greater detail.
But so far this season, that elusive tornado formation has escaped them. But buried in the data, they have discovered something just as important.
When you get a new data set and you bring it into the computer model and you start studying it, it's kind of like drinking from a fire hose. Your mind just goes off trying to think of all kinds of different things that you can do with this data set and different ways that you can analyze it and visualize it.
After feeding data from a recent storm into the software, Forsyth noticed strange patterns.
We're seeing changes go on in the storm that we've never seen before. There's some waves moving through the storm that I don't think the meteorologists knew existed, because you can't see them when you're taking snapshots between 4 and 6 minutes. You just don't see those things happening.
The brown mass is the storm. The new elements the radar reveals might just be the trigger for the tornadoes, like these waves that seem to ripple through the supercell.
Actually starting to see some new activity in storms that we've never seen before.
If they can detect the waves long enough before a twister is born, they could gain life-saving minutes.
We're going to have to do some research and see what really is happening. I think we'll put it together over the next few years and make some headway into making better warnings and at least understanding possibly this tornado genesis.
Early warnings will save lives. Buried in the rubble of Super Tuesday lies another life-saving clue. Over 1,000 homes are destroyed on Super Tuesday. Research into new building design shows these losses could be avoided. It has also led to some exciting new insights into what happens within the tornadoes themselves. Investigators combing through the rubble of Super Tuesday discover a frightening truth. Tornadoes are getting more powerful. Is there anything we can do to protect ourselves? The first time wind engineer Partha Sarkar from Iowa State University surveyed the wreckage from a tornado, he was determined to do something about it.
You may survive a tornado, but your entire life is turned upside down because your whole house is gone, whole neighborhood is gone. And that's what bothers me. If you see the cars which have taken a hit from F5, you see it twisted beyond recognition, you know, people are no match for that kind of wind.
On Super Tuesday in Tennessee alone, over 500 homes are destroyed. The cost to rebuild runs into hundreds of millions. Sarkar thinks we can prevent the damage these new, more powerful tornadoes will bring.
We can do something about it. We can design these houses to at least not get completely destroyed. If it's partially destroyed, we can rebuild it. It's completely destroyed and it's gone.
In order to figure out how to protect a building, he has to know exactly what the winds are doing inside a powerful tornado. To do that, he has to make himself one. He contacts tornado expert Bill Gallus.
It was probably a phone call I'll never forget. Partha wanted to design the first wind tunnel that would create a moving tornado, and wanted to discuss what ways might we use to create a moving tornado simulator.
This is the result of their collaboration. A twister in a can, 18 feet across and 11 feet high, suspended over a model target. The largest and most realistic tornado simulator ever constructed. It can recreate the same kind of tornadoes that struck on Super Tuesday, from EF1 to the more powerful EF5. It's the only simulator that can accurately measure how the wind loads of a moving tornado affect different kinds of structures.
Once they had the large simulator done and had to throw on the power switch, I think there were a lot of people waiting there and scared to death at what would happen.
In the past, wind tunnel research simulated only straight-line wind. This machine reveals how the circular wind of a tornado can literally pull the roof off a house like a corkscrew. New building design will now incorporate ways to prevent this.
Every time I switch on the tornado, I feel good about it.
But this is not the only insight the machine revealed. In order for the simulator to create a tornado, they add a significant amount of downdraft. Could this be one of the elusive ingredients needed to form a real tornado? The team looked closer. Downdraft is a fast current of air passing down through the center of a rotating storm. We don't yet know how downdraft is created, only that it concentrates the storm's rotation by drawing it inward. Downdraft seems to create enough spin to produce a tornado.
It's possible that tornadoes are created in many different ways, but it seems that this particular idea of getting a downdraft that descends toward the ground almost in the shape of a circle should be something that really does lead to tornadoes.
And if tornadoes are getting more powerful, the simulator could tell us more about how they form and what the winds are capable of. But right now, scientists have a more urgent mystery to solve. It seems something else is happening to tornadoes. They're not only getting more powerful, they're not only striking outside tornado season, they're now striking outside Tornado Alley. Forecasters need to understand why. 7:15 p.m. on Super Tuesday, and Arkansas is reeling from 7 tornadoes. Tennessee is now under attack, and more storms are brewing. The team at the Storm Prediction Center can only watch.
There is a feeling of helplessness, really, at that point, because you see the violent weather unfolding. You know that there's most likely a tornado on the ground. You know that there are communities at risk. But you also know you've done just about everything you can do.
As the monster system rampages across the Upper South, it holds one more deadly surprise. Against the odds, one thundercloud crosses the Tennessee state line, moving outside Tornado Alley into Kentucky. On average, Kentucky sees 10 small tornadoes a year, mostly in the spring. It's about to be struck by 24 powerful twisters in a single night. Winter outbreaks usually occur farther south, in Arkansas and Texas, where tornadoes can feed on warmer air. What's causing them to strike so far north? This phenomenally rare event will lead them to the most chilling discovery yet. Super twisters on course for Chicago. The Super Tuesday tornado outbreak has shown that more powerful tornadoes are now striking outside their usual season. The culprit is La Nina. Its cooling effect at sea speeds up the jet stream winds over land, making winter storms spin even faster. The perfect conditions for tornadoes. But there's one last mystery. Why are tornadoes now striking further north, outside of Tornado Alley? Again, the clues lie in the events of that tragic day. 7:35 p.m. Super Tuesday.
Hey, we can see the contact point on that one. He's close. There's contact on the ground. There's debris.
Kentucky is about to be terrorized by the first of 24 twisters. A state usually considered too far north to see this many. At the Storm Prediction Center, Greg Carbon can do nothing.
When I went home that evening, I had no idea that there were already 14 fatalities. I knew we had deadly tornadoes. I knew that the day before, but the actual numbers and the actual accounts were yet to be known.
As the Super Tuesday tornadoes trespass into new territory, pushing the death toll higher, the storm too is dying. As a tornado feeds on the warm, moist inflow at ground level, the downdraft that created it keeps descending. As the cold downdraft collects at the base of the tornado, it wraps itself around the vortex and begins to cut off its warm air supply. The tornado is slowly strangled by the very force that gave it life. As the last twister retreats, the Super Tuesday storms finally run out of energy. The imbalance that created them is gone, and equilibrium is restored. But what caused the tornadoes to cross state lines? What gave them the power to move so far north, into places they are least expected? At the Carnegie Institution at Stanford in California, climate scientist Ken Caldera may have stumbled across the answer. Caldera is studying the jet stream in the hope of harnessing its power.
If we could somehow tap into this energy, it would be really incredible resource for civilization.
Caldera set out to develop an atlas showing the best places to launch wind turbines into the jet stream. As he charted the position of the jet stream from year to year, he noticed something alarming. Over the last 2 decades, the jet stream has been shifting north. As it moves, it takes severe storms along with it. This would explain why Kentucky got struck on Super Tuesday.
The jet streams act as storm tracks that guide storms and also affect where storms are created. And so where tornadoes used to be something that was primarily of the southern areas, now we're seeing tornadoes further and further north.
But what pushes the jet stream north? For the answer, Caldera looks south. For the last 2 decades, temperatures around the equator have steadily risen. The jet stream is the boundary between tropical air and polar air. As the warm air mass around the equator expands, the polar air mass contracts. As a result, the jet stream is pushed further north. What are the odds that global warming caused Kentucky's freak outbreak?
You could think of weather as a chaotic system, a little bit like rolling dice. In the natural climate, we're rolling the dice, and every once in a while it comes up snake eyes, double ones. And you could think of climate change as loading the dice, where you should expect more snake eyes, more storms like this occurring further to the north as global warming continues. If you're living north of Tornado Alley, but you don't get any tornadoes now, you should be worried that sometime in the future, tornadoes will start showing up on your doorstep.
The jet stream is moving north over 1 mile per year. Before long, Chicago could mark the center of Tornado Alley. Scientists calculate that if a big twister tore through the city of Chicago, it could do $40 billion worth of damage and potentially kill 45,000 people. Understanding what caused the tragic events of Super Tuesday 2008 has enabled science to predict that there is worse to come. The groundbreaking discoveries about La Niña and the jet stream will go down in meteorological history.
The key, I think, for us is to not get frustrated, but to learn from these experiences and to take from them a better understanding in trying to help predict significant events in the future.
One of those significant events could be the ultimate nightmare. A super twister slamming Chicago. But by the time it strikes, we may be ready by cracking the mystery of how tornadoes form, buying enough time to warn victims of danger, and designing buildings to withstand the worst. Science could be the silver lining inside the darkest cloud. Planet Earth. 4.5 billion years of evolution. It's all going to end. Titanic forces are already at work that will destroy the world as we know it. Scientific investigators take us on an epic journey into the future of the Earth, where apocalypses will wipe out all life and destroy our planet. This is the countdown to the end of the world. Seven and a half billion years from now, Earth will be consumed by fire and vaporized. But by then, it will be unrecognizable, a lifeless alien world. Long before its final moment, our planet could be struck by no less than 7 great catastrophes. One by one, they will turn the jungles into deserts, reshape the continents, and boil away the oceans. Other disasters will destroy the atmosphere, annihilate the animals, and destroy every plant. These are just the catastrophes we can predict. And what of mankind? We could be the first to go. This is the story of the death of the Earth. The first threat to life on Earth comes from the heavens. Right now, a lump of rock and metal, 6 miles wide, traveling at 17 miles per second, could be headed our way. It could strike next week, next month, or next year. But whenever it does, there will be little we can do. We would have very little warning before that threat turns into an asteroid impact. Earth has always been in the firing line.
It could happen tomorrow. It could be 100 million years from now. But it's not a matter of if, it's when.
300 million miles out from the sun, beyond Mars, is the asteroid belt, the rubble of a planet that never formed. 750,000 massive lumps of rock, more than ½ a mile across. It's an inexhaustible source of planetary ammunition that gets knocked out of the belt and sent spinning across space. NASA astronomer Professor Don Brownlee knows a lot about asteroids. The record of the devastation they bring is hard to miss.
Just look at the moon in the night. You see it's covered with craters, huge craters. Impacts that happen to all the planets that have happened for billions of years throughout our history. So this will happen.
It already has. 65 million years ago, an asteroid 6 miles wide slams into the Earth. The impact throws up millions of tons of rock thousands of feet into the air, fusing sand into glass in a split second. This one impact wipes out the dinosaurs, a species that had endured for 160 million years. So what are the odds of this kind of asteroid strike happening today? Using the visible impact record on the Moon and planets like Mars and Mercury, Brownlee has come up with an answer.
The frequency of impact of a 10-kilometer object from space, a comet or an asteroid, of the kind that wiped out the dinosaurs 65 million years ago, is on the average about 1 every 100 million years.
When it strikes, it instantly vaporizes every living thing for miles around. The sheer force of the impact buckles and cracks the Earth's crust, creating powerful earthquakes. The force of the winds whips up waves, pushing powerful tsunamis onto the land. Within a few days, the dust cloud blocks the sun, plunging the planet into freezing darkness. An endless winter that would last for more than a year. Hidden within the dust is something far worse. A sudden overdose of nitric oxide destroys 85% of the ozone layer. As the dust finally settles, the lack of ozone allows damaging ultraviolet rays to reach the surface, harming billions of people and killing plants and animals with lethal doses of radiation. By the end of that first year, at least 70% of all life would have been destroyed. Those that live underground or hibernate stand a better chance. This is what killed the dinosaurs, and one day, the same thing could happen to us. Not knowing when the next asteroid will strike makes planning difficult and worrying pointless. There is worse to come. Even if we could plan for the next catastrophe, it won't make any difference. Ice sheets several miles deep, pushing down from the poles, will be unstoppable. A global ice age is coming. How do we know? It has happened before, and one of the first clues was pulled from the La Brea tar pits. To find an ice-loving woolly mammoth was a big surprise. To find it in the heat of California was a mystery. Could California have once been covered in ice? Could it happen again? To find out, scientists need a record of changes in the climate, stretching back tens of thousands of years. It turns up in the layers of sediment at the bottom of the ocean. Marine geologist Professor Peter Domenical is searching for clues to Earth's frozen past.
Deep sea sediments are really unique archives of past climate change because the sediments in the ocean accumulate very continuously and very slowly over time. So they present us with this kind of history book of past climate change.
These tiny chunks of rock in the sediment hold the answer to the USA's frozen past and to its future. Deposited 10,000 years ago, how they got here is astonishing.
Icebergs carry all these rocks and they hold them inside the iceberg and then they melt. As the iceberg melts, it drops its load. And that's how we find these big pebbles out in the middle of the ocean.
Icebergs once floated off the coast. As the bergs melted, the rocks they carried from the north sank to the seafloor. 10,000 years ago, much of North America is in the grip of an ice age. But what causes a big freeze? The answer isn't found beneath the geologists' feet, but over their heads, in outer space. The Earth orbits the Sun in an ellipse that gradually changes shape over time. The tilt of the Earth to the Sun also changes. Calculations suggested that the interaction of these changes could flip the climate from warm to cold and back again. It's called the Milankovitch cycle, after the man who discovered it. His orbital calculations showed that the Earth flipped from ice age to warmth 10,000 years ago, the exact age of the sediments Domenical has found.
It was shocking when the evidence came out that there was this very close correspondence between the astronomical calculations and then really the geologic record. People were just blown away.
But what about the future? The orbital effect is called the Milankovitch cycle because it happens over and over again.
We're well on our way, actually, into the next ice age. Something most people don't really fully appreciate. Climate was significantly warmer 5,000 and 10,000 years ago, and then we've been gradually headed into this much cooler climate.
Domenical believes the Earth will be plunged into another global ice age within 30,000 years. If the last one is anything to go by, the next will be worse. Because in the last ice age, there were just 5 million humans. Now, there are 6 billion. Could we all survive? Ice sheets 2 miles thick could cover the land. Cities like London and New York may be buried beneath thousands of feet of ice. Global sea levels could drop 400 feet as water is locked up in ice. Freezing temperatures might last 100,000 years. The food chain collapses. Plants die as they are smothered by ice. Herbivores can no longer find food and die out. As civilization collapses and food and shelter become scarce, our base survival instincts kick in. Dr. Erwin Redlener at Columbia University is an expert in how humans react to catastrophic events. The bad news is, many won't make it.
The major challenges will be to how to keep ourselves from killing each other because of a natural event like a new ice age. Enormous migrations of people trying to escape from the extreme conditions have the potential of causing a tremendous amount of deadly competition for resources, for food, for water, for power.
Billions of people could perish as vast areas of available land are swallowed by ice. But many humans will survive the big freeze in belts of green, north and south of the equator. Here, agriculture will continue, but not enough to support the billions who will now begin a battle to control it.
I think we are hardwired on a genetic DNA level to seek survival at almost any cost. And I think there's pretty good examples of that. People who were prisoners of war, and people lost in hostile environments.
In a few green areas, humans will survive, but the population will be greatly reduced. Civilization as we know it will change forever. And the next ice age is unlikely to be the last. The great ice sheets will continue to advance and retreat, devastating life and civilizations. 250 million years in the future, it gets worse. Life will face an even greater threat and be pushed to the very brink of extinction. The seas will die and the land will become desert. "250 million years in the future, having survived ice ages and perhaps even asteroid strikes, there now comes an even greater threat. The surface of the planet is completely unrecognizable. Life is being pushed to the brink of extinction. This terrifying vision of the future is caused by the same powerful forces that shape the Earth today.
Plate tectonics was one of the two major scientific advances of the 20th century. It allowed us to get an understanding that the Earth is really much more dynamic than we ever suspected.
It reveals that the Earth's surface is made up of a series of massive continental plates that are in constant motion. Where they collide, huge mountains are driven up and massive volcanoes pour out liquid rock. It shapes the face of our planet. Armed with this new information, the geological record opened up like a book, revealing that 250 million years ago, all the continents were united to form a single supercontinent we call Pangaea. This was a hot, brutal world ruled by dinosaurs. Could future movement of the tectonic plates transform the Earth once again into a single vast landmass?
We now know how the plates are moving far more accurately than ever before, and so it became tempting to look into how this might develop if we projected these motions a few million years into the future.
According to Livermore's model, 250 million years in the future, a new supercontinent will form. Africa plows into the Middle East as Antarctica and Australia fuse together. One vast landmass surrounded by a giant ocean.
We end up with a supercontinent which is primarily in the northern hemisphere and a southern hemisphere which is mainly ocean. This will give us a range of habitats within the supercontinent quite different from anything that we see at the present time.
With much of the land hundreds or thousands of miles from the ocean, rainfall becomes non-existent. No plants grow, and as the land absorbs the heat, temperatures soar. It turns to desert.
If we were looking down on the future supercontinent, what we are likely to see is something really rather like the interior of Australia.
250 million years in the future, this new world will be mostly desert, covering over half of the land, so hot and dry that few plants or animals survive. 80% of the species we see today could be wiped out. Those that do survive will have to adapt to less water, less food, and rising heat. Our distant descendants might try to take refuge in the coastal regions. But even here, there's no escaping the dangers of this new world.
Around the edges here, we're probably going to see continuing volcanism, continuing earthquakes.
The tectonic forces that pushed the supercontinent together are still at work. Now they begin to buckle and split the land at its weakest points. The result is massive earthquakes. Lava exploits these new cracks and bursts out, forming chains of volcanoes. Molten rock spreads over thousands of miles, incinerating every living thing in its path. Life on the land will be tough beyond our imagination, causing mass extinctions. But this is nothing compared with the devastation facing life in the new superocean. In 250 million years, a single supercontinent will dominate the face of planet Earth. It has happened before. By exploring what happened back then, we now know that this single landmass could have a devastating effect on the oceans in the future. A lethal dose of carbon dioxide may cause a mass extinction, which could wipe out 96% of life in the sea. But where will this killer carbon dioxide come from? The biggest natural CO2 producers on the planet are well known, and the supercontinent of the future will have plenty of them. Volcanoes. To understand how the carbon dioxide from volcanoes leads to mass extinction in the oceans, Dr. James Barry has been studying what happens to one particular creature called a brachiopod during similar events.
Oceans became much more acid due to all the CO2 that was released by volcanic action over 100,000 years. And that increased acidity of the ocean has caused not only brachiopods, but many other types of animal life to go extinct.
Dr. Barry is trying to understand exactly what happens when carbon dioxide levels suddenly shoot up. Among the first to feel it are shellfish.
These brachiopods are a curiosity. They're one of the earliest sort of real animal life forms that evolved on this planet. 400 million years ago, they were one of the most dominant forms of life on the planet. But they went from 30,000 species down to about 300. They're the poster child for how to go extinct.
Brachiopods had survived everything the Earth could throw at them for hundreds of millions of years. Yet it was volcanic eruptions on land that wiped out 99% of brachiopod species in the sea. Barry's research reveals how. Brachiopods are highly sensitive to carbon dioxide levels. The excess CO2 from volcanoes dissolves in the water, making it acidic.
Once it enters the ocean, it combines and reacts with seawater to form carbonic acid. And that changes the balance of chemistry in the ocean.
As the sea becomes more acidic, the brachiopods die out. In 250 million years, the hard shells of all marine invertebrates dissolve in the acidic water. As their inhabitants die, a big link in the food chain collapses. Their predators starve, and the lack of food goes right to the top of the chain. At the same time as the food chain is collapsing, another brutal consequence of a single supercontinent will be reaching its endgame. 80% of marine species live close to the coastline. With all the land locked up, there's less coast to go around. Competition for the prime real estate gets fierce. The coastline of the future supercontinent could be 70% less than it is today. So the next supercontinent will be deadly. In 250 million years, an arid desert on land and an acid ocean means a mass extinction that will make the death of the dinosaurs look like a sideshow. But amazingly, some plants, some animals will survive. Those that can adapt. Creatures like snakes and spiders that thrive in the heat. Low hardy bushes and types of cacti may be able to evolve. Life will endure for 1 billion years to come. It's only then that the final extinction of life on our planet begins. The end of all life on land. 1 billion years in the future, the world is going to get hotter. All stars, like our sun, go through a cycle of life and death. Today the sun is middle-aged, but in 1 billion years, it will be that much closer to death. As it burns through the remainder of its fuel, internal processes will cause it to expand, bringing its surface ever closer to the Earth. The temperature will soar. It is now 86 degrees and climbing. For mankind, another 18 degrees higher, and we will have reached our physical limit. Blood thickens, strokes and organ failure follows. Sometime in the next 1 billion years, humanity will cease to function. At this point, we will have disappeared forever from the face of the Earth. But other kinds of life will be able to survive. Here at the California Academy of Sciences, Professor Lynn Rothschild searches the history of past extinctions for examples of what creatures might be able to survive in a world twice as hot as today.
What I'm holding here is an ammonite, and these were extremely successful group of invertebrates. They were wonderful predators, and they went extinct at the end of the Cretaceous. Not their fault. They were wonderful at the time, but they went.
As the sun expands and the world heats up, it all comes down to luck. If you happen just by chance to be better suited to the new world, you'll make it. If not, it's just bad luck. And in the brutally hot future Earth, we already have a fair idea who's going to be lucky.
We see animals like scorpions, like we have here, spiders, maybe some snakes that come out at night. And these are so well adapted to living in these hot, dry environments because they prevent water loss. They do everything they can to keep water inside their bodies. They stay nocturnal.
Only the most extreme adaptations can survive. But as conditions become worse, life on land heads toward its final moments. It begins with the plants. Atmospheric scientist Professor James Casting is one of only a few people in the world to have figured out what happens to the plants in 1 billion years from now. He's discovered that a drastic fall in CO2 will wipe most of them out.
CO2 will drop by a factor of 1/2. That will wipe out 95% of the plants on Earth.
Geological processes are at work today that absorb carbon dioxide and dump it in deep ocean sediments. But like all chemical processes, the higher the temperature, the faster it works. Supercharged by the hot Earth 1 billion years from now, it wipes carbon dioxide from the atmosphere.
It will drop down below the level required to sustain plant life. And that's the fundamental food source on Earth. I mean, carbon dioxide is the food of life. It's what makes photosynthesis work. And with CO2 gone, it's a very different world.
Deprived of CO2, plant life suffocates and dies. The last remnants of our green Earth turns brown and dead. One vast desert covers the land.
It's really hard to imagine a future without any plants. I guess the best way to imagine it is to go up into the desert. In a way, it's a very beautiful environment, but it is very barren, and it doesn't seem like home.
Without plants, the food chain collapses. The plant eaters starve, and their predators follow. Animals, insects, reptiles, and mammals. For life on land, everyone's luck has finally run out. There is only now one place on the entire planet that does continue to support life: the oceans.
If you think about why life both originated in the ocean and probably will be forced back into the ocean in the future, it's because the ocean is far more stable than land. If you go out into the desert in the middle of any continent here, the summers are sweltering and the winters are frozen. During that same yearly cycle, the temperature right offshore here nearly stays the same year-round.
But a billion years in the future, as the dying sun swells and the temperatures rise, the oceans begin to evaporate. As the water level drops, they become more and more salty. To understand what the oceans of the future will be like, Professor Rothschild has come to these salt ponds outside San Francisco, where seawater is evaporated to produce salt.
What happens here, and you'd imagine would happen on the Earth, is that as the concentration of salt goes up, 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 many of the organisms that we're familiar with, fish and kelp and algae and manta rays and so on, drop out.
It is the end for life in the oceans as we know it. Whales, dolphins, jellyfish, coral reefs, pretty much everything. All gone, unable to survive in the increasing saltiness of the water.
And at some point, you're left with brine flies, a few little worms, and some of the microbes that you see here. And at the very highest salt concentrations, about 10 times the salinity of the ocean, you only end up with organisms called halophile.
It is the halophiles, tiny organisms that thrive in high salt environments, that give the water its red color. This color is no accident.
Now, during the summer, we tend to get tanned. I've been in the pool, I look a little tanner than I would in the winter. Well, these organisms also have to protect themselves from a very strong sun, ultraviolet radiation. And so instead of tanning, they tend to produce a lot of red pigments, carotenoids. These are the same kind of compounds that you see in tomatoes and carrots and so on. And this orangey red pigment helps protect these organisms from the very high sunlight.
With a blazing sun filling the sky and temperatures rising, only these incredible survivors called extremophiles can take it. 1.2 billion years from now, all other life is gone.
As the Earth becomes a very hostile place, we're back to having a world that's only populated by microbes, very much the way it was during the early evolution of life on Earth.
Extremophiles clinging on at the ragged edge of survival in the last remnants of the ocean. The final hammer blow that will end all life is now just around the corner. 1.2 billion years from now, plants and animals have been wiped from the surface of the Earth. Only microbial extremophiles survive in a rapidly evaporating, increasingly salty ocean. For the oceans, time has finally run out. The brightness of the expanding sun boosts average global temperatures to a blistering 100 degrees, nearly double than today. Professor James Casting is investigating the devastating effect this has on the oceans of the future.
Well, we think that the Earth will start to lose its oceans when the sun gets about 10% brighter than it is today.
His findings confirm evidence gathered by Apollo astronauts in 1972. Hydrogen is escaping from the Earth. Water is made up of 1 part oxygen and 2 parts hydrogen. So what the astronauts were seeing was the infinitesimal loss of the oceans into space. Today, this amount is nothing serious, but 1.2 billion years in the future, when the temperature is 100 degrees, the process goes into overdrive. Faster evaporation now saturates the air with water. As this water rises to the top of the atmosphere, ultraviolet light from the sun splits it into its 2 component parts, oxygen and hydrogen. The hydrogen is so light, it floats off into space, lost forever. What casting discovered was that from full to empty, the whole process of losing our oceans could take less than 200 million years. Without water, life cannot exist. So to find out when this will happen, he had to look at a planet not unlike the Earth that lost its oceans in the same way.
Well, I got interested in the future of Earth's oceans by working not on Earth, but on Venus.
Physically, Venus is almost a twin of our planet. And billions of years ago, it might have been even more similar.
May well have had liquid water on its surface at one time, just as the Earth does now. But it was too close to the sun. It lost that water by what we call a runaway greenhouse. It's likely, in my opinion, that Earth will follow the path of Venus at some point in the future.
Studying Venus helped casting estimate when we will start to lose our oceans. The answer came as a shock.
Well, up until we had worked on this problem, many scientists thought that the Earth would retain its oceans for at least another 3 or 4 billion years. But we were able to show that bad things start to happen much earlier than that. The oceans could be lost in 1.2 billion years.
With the water gone, dry salt crusts like these are all that will remain of the Earth's magnificent oceans. Is this the end for life? Incredibly, a new discovery has shown that even without water, basic life forms can survive. But for how long?
Although we'd known that organisms could live in very high salt, we knew that they could also be trapped in solid salt. But what we didn't know is that while they're in the solid salt, it's more than them being in suspended animation, that they are actually still metabolically active. They're still breathing and eating and excreting and doing all the sorts of things they need to do, but at a very, very, very slow rate. So that was really an astounding discovery for us.
In 1.4 billion years, with the oceans finally gone, extremophiles will survive in the solid salt, but just barely.
These organisms will be able to survive a good deal longer in a salt crust like this, even in the absence of water. They won't be able to survive forever like that, but it'll buy them a little time.
Perhaps another few million years. In that time, their main protection will be the red color that acts as a sunblock. While they live, they will transform the way our planet looks from space.
People always think of the Earth as this beautiful blue planet, you know, the pale blue dot in the sky. But the fact is, for almost half of Earth's future history, it will be a Barbie planet. It will be covered with pink salt.
This is the Earth 1.4 billion years from now. The extremophiles cling on in an increasingly desperate fight, but the rising temperatures as the sun brightens eventually defeat them. By 1.6 billion years into the future, the temperature has climbed to 224 degrees, far above the boiling point of water. Life finally loses the battle. The last remaining extremophile dies.
There are several poignant moments in geologic history. The Earth losing its oceans will be the most poignant of all, because that really will be the end of life as we know it. And unless we've figured out how to colonize other planets, then life will come to an end. It's a pretty sobering thought.
The time of the pink Earth passes. Our planet is reduced to a brown, featureless world. Unless we have found a foothold on another, this is the end of life in our universe. For the next 6 billion years, our dead world orbits the dying sun. Only an astronomer can see this far into the future, to the Earth's final moment of existence. Dr. Robert Smith from the University of Sussex has unraveled the Earth's ultimate fate. But his journey of discovery has taken some unexpected twists and turns. The process begins as the dying sun continues to swell in size.
The sun getting bigger will have severe consequences for the Earth, because we predict that the sun will get at least 200 times its present size.
All stars go through a cycle of life and death. Astronomers know this because they can see stars that represent every stage of life that our sun will go through. In 7 billion years, our sun will be close to death. The sun is now 1,000 times brighter, 200 times its present size, and still growing. The heat literally dissolves the face of the Earth, wiping away the last of its uniqueness.
As the sun gets bigger, the mountains will start to melt, and instead of having high mountains and deep ocean depths, everything will flow into a uniform sphere, be featureless, and very, very hot.
Earth's surface is now melting in 2,500-degree heat. The surface runs with liquid metal. Our planet is utterly unrecognizable, a totally alien world. The end is now close. But Dr. Smith's calculations revealed a last-minute escape might just be possible. $7.5 billion years in the future. The mountains and oceans have been erased from the Earth's surface. The temperature is over 2,500 degrees. It has been lifeless for 6 billion years. Now the Earth itself is about to die. At the heart of the dying sun, helium is reaching a critical stage. It's becoming so dense, its atoms so crowded, that the core is becoming explosively unstable. It now takes on its final form, a red giant, 256 times bigger than it is now. It fills the sky.
First of all, you would see the size of the sun beginning to increase. It would get redder, it would get brighter. At the moment, we're used to seeing it about the size of the full moon. Then it would get bigger and bigger, it would fill more and more of the sky, till eventually when it become a red giant, it would probably fill something like half the sky.
As the sun burns up the last of its fuel, it expands outwards. Now almost 200 million miles in diameter and swallowing everything in its path. Is this the fate of planet Earth? When Dr. Smith first tried to find out, the figures showed that as the sun gets bigger, it loses its gravitational grip on the Earth. The chain is broken, and our planet drifts off into space, potentially escaping a fiery death. It seemed that Smith had saved the planet.
It was a good feeling that we'd saved the Earth, and indeed some of the newspaper headlines said exactly that.
But then one of Smith's colleagues took another look and produced new calculations about the red giant. These seemed to suggest a radically different picture.
When we came to look at the calculations again, we realized that we'd missed something out. We realized that there was a missing effect which we had to take into account, and that's to do with tides.
What they hadn't taken into account are the tidal effects of the Earth on the Sun. The Earth's gravity will create a tidal bulge on the surface of the Sun, in much the same way as the Moon affects the rise of the ocean tides on Earth today. This bulge, in turn, creates a drag on the Earth, pulling it back towards the Sun. Smith set to work using the new data to find out just what would happen now.
We didn't know what to expect when we first put in this additional effect. We hoped that even when we put in the tides, the Earth would still escape.
Smith announced a very different set of results. The news was bad. The tidal effect chains the Earth to the Sun.
When we came to look at this problem again and put in the extra effects and realized that the Earth would in fact not survive, we decided to call our paper Doomsday.
The surface of the Earth is now nearly 2,500 degrees, hot enough to melt metal. The outer fringes of the Sun reach out to engulf the Earth.
We try to imagine what it would look like to see the Earth disappearing. Just be like an asteroid crushing through this Earth's atmosphere. It will burn up completely. It will vaporize, it will disappear, it will become part of the Sun, and it will be as if it has never been.
12 billion years of planetary history ends. The death of planet Earth, engulfed in flame, vaporized by the Sun, reduced to atoms.
Sort of dust to dust. But it's not such a bad fate, because those atoms, your dog's atoms, your car's atoms, they go out into space, and what do? They end up forming new stars, new planets, and maybe even new people.
It's a cruel act of fate that life-giving stars will one day go bad. Big changes are coming. By understanding how Earth worked in the past and how it works today, science is beginning to understand what the future may bring. The death of the Earth is already laid out in front of us. It's written into its geological past, and literally into the stars above us. Jupiter. Vast, mysterious. The largest planet in the solar system. Made almost entirely of gas, this violent world of 400-mile-an-hour winds and storms twice the size of Earth may also be the blueprint for how planets are formed. And on one of Jupiter's 4 largest moons may lie the answer to the most important question of all. Beneath these vast ice sheets, mankind could finally discover if alien life exists. Cutting-edge space missions are unlocking the secrets of this enigmatic giant, Jupiter. In the last 50 years, space missions have revealed worlds we never could have imagined. From the mountains of Mars to the methane lakes of Saturn. Yet one planet captures our imagination more than any other. The greatest of them all, Jupiter. Most of what we know about Jupiter comes from one mission, Galileo, launched aboard the Space Shuttle Atlantis in 1989. each new discovery it makes deepens our understanding of Jupiter and its moons. It may also uncover evidence of how the solar system itself was formed. "11 times bigger than the Earth, yet probably without a solid surface. Jupiter is a ball of gas and liquid 90,000 miles across, with lightning superbolts 1,000 times more powerful than the strongest strikes on Earth, and a ring system like Saturn's, but too faint for our telescopes to see. The Great Red Spot, a single vast storm with 250-mile-an-hour winds, so huge it could swallow the Earth 3 times over. 63 moons orbit this giant. Galileo will study 4 of them: Io, Europa, Ganymede, and Callisto.
Each of which would be a beautiful target for a space mission in and of itself.
Scientists expect dead and lifeless worlds 500 million miles from the Sun. Io, Jupiter's closest moon, is slightly larger than Earth's own moon. But Io is far from lifeless. Huge plumes of sulfur dioxide reach hundreds of miles into space.
Very peculiar surface with reds and yellows. Someone nicknamed it the pizza moon.
Ganymede, the largest moon, is a world of scars and frozen slush. And Europa, most mysterious of all. Its icy surface may hide a liquid ocean below. Where there's water, there could be life. A new generation of probes are set to explore the mysteries of the Jovian system. Juno, Europa Explorer, and the underwater probe, Endurance. 3 missions, 1 goal, to at last reveal the secrets of these alien worlds. Before Galileo, previous missions could only look from afar. In the 1970s and early 80s, Pioneer and Voyager gave us tantalizing glimpses of Jupiter and its moons, but they raised more questions than they answered. How did Jupiter form? What powers its vast storms? And why are its moons so geologically active? Before these questions can be answered, the team have to overcome a simple problem. Galileo is unable to carry enough fuel to reach its destination. NASA engineers need another way to get to Jupiter.
And they came up with a brilliant solution. We wouldn't go to Jupiter at all. We'd start by going to Venus.
By flying close to Venus and then Earth, using a gravitational slingshot method, Galileo steals some energy from the planets to accelerate itself toward its final destination, Jupiter. When Galileo arrives after a journey of 6 years, a small subprobe will detach and plunge into the depths of Jupiter's atmosphere. It will have less than an hour to analyze its surroundings before being crushed by the extreme pressure. Everyone expects Galileo to beam back extraordinary information. As the spacecraft nears the end of its journey, it coincides with a massive comet on a collision course with Jupiter. Galileo is in an ideal position to watch. It could find clues to one of the most important questions about Jupiter's history. How was it made? Up until now, scientists believe that Jupiter is made from the leftovers from the birth of the Sun, a primordial planet frozen in time. If so, the Sun and Jupiter will have very similar chemical compositions. The comet's impact will stir up chemicals from below the surface, enabling the team to analyze them and see if the theory holds true. They are about to get more than they bargained for.
I just couldn't believe that we were going to get a chance to see one body in the solar system smash into another one.
we had an up-close and personal view of this unique event.
The comet's name is Shoemaker-Levy 9, or SL9. David Levy is part of the team that first discovers it.
This was going to be the first time that a comet collided with a planet, the first time in recorded history. And we had no idea what we were going to learn from it.
The day arrives. On mountaintops and in space, more telescopes are trained on the same part of the sky than ever before. Some scientists believe Jupiter's thick atmosphere will simply swallow the comet without a trace. Others hope the impact will dredge up matter from deep inside the planet, giving us vital clues to its composition.
We were talking about the largest, biggest planet in the solar system being hit by a tiny comet. Most scientists thought it would be a fizzle. Boy, were we lucky.
As the comet approaches, Jupiter's massive gravity tears it to pieces. Now, 20 separate fragments will strike the planet, some a mile or more across. Astronomers across the globe are about to witness something amazing.
Yeah, that's it.
One by one, the fragments hit. The largest releases as much energy as 300 million atomic bombs. A fireball shoots 2,000 miles above the top of Jupiter's clouds. Each fragment produces a separate impact cloud, visible as dark black bruises in Jupiter's southern hemisphere. They're the size of the Earth.
The first thing we saw with each impact was either the plume of dust and gas, as seen by either Galileo or the Hubble Space Telescope. The next thing we saw was the formation of the large jet black cloud all over Jupiter's southern hemisphere.
But the real surprise doesn't come from the clouds. It comes from the shock waves the impacts send through the upper atmosphere. There's only one explanation, and to astronomers, it's a revelation.
When Shoemaker-Levy 9 crashed into Jupiter, it's sort of like a rock going into a pool. It sent out waves, and the speed of the waves depends on the amount of water in the atmosphere. And the speed was faster than we thought, and so we inferred that there was more water than we had expected. You can sort of see it here. You can see the ripples spreading out. And it was the speed at which the circles grew that told us there was more water than we expected.
The discovery is a surprise. It means that the composition of Jupiter is different from the Sun. It threatens to overturn everything scientists think they know about Jupiter's formation. A new theory is needed. In 17 months, Galileo will arrive and analyze Jupiter's chemistry firsthand. Only then can the team solve the mystery. One year after the comet SL9 strikes Jupiter, Galileo is on its final approach. There's a lot at stake. Scientists now know Jupiter may have 10 times more water than previously thought. If so, they may need to find a whole new explanation for how this strange world formed. Galileo's first task will be to directly measure the chemistry of Jupiter's atmosphere, including the amount of water. Galileo will release a small probe into Jupiter's clouds. The probe will also measure the wind speeds and temperatures at different depths to try and explain why the weather is so violent, as well as answering the big question: is Jupiter a long-lost cousin of the Sun, or something else entirely? As the probe dives into Jupiter's atmosphere, scientists are convinced they'll find the layer of water vapor the comet revealed, giving vital clues to the planet's creation.
And I even announced a prediction at a scientific meeting, offering to bet anyone in the audience $10 that the probe would find more than a certain amount of water.
But instead of water, the probe drifts through thin, wispy gases. It has flown into a downdraft, a dry gap in the clouds. Where is the water they were expecting to find? Jupiter must have both dry areas and wet spots, it's not what they expect.
What they discovered was that Jupiter has some long-term weather patterns, spots that move around that they didn't really realize were there before.
The Galileo team holds their breath. The probe dives deeper, but still there is almost no evidence of water. Less than an hour of data is about to trigger a revolution in our understanding of how the solar system formed. The probe does detect a high proportion of heavier elements like argon, krypton, carbon, and nitrogen. It finds levels 2 to 3 times higher than found in the Sun. These elements only condense at extremely low temperatures, lower than the temperature found at Jupiter's present position.
We learned that the atmosphere of Jupiter has chemical constituents that came in with very cold material from the outer solar system.
For astronomers, the discovery is a bombshell. The presence of these elements means Jupiter must have formed in a different way than the Sun.
This little probe, in one felt swoop, showed us that all of our ideas of how planets were formed were wrong. We didn't understand how the planets were made, and we didn't understand the early solar system.
The small probe's discoveries shocked the scientific community. Could the giant planet have formed further out in the solar system, where it's colder, then migrated into its current position? Or did comets or asteroids bring the heavy elements and water to it? After 58 minutes, and before the answers become clear, the probe falls silent, burning up in Jupiter's inner atmosphere. The probe has given scientists some remarkable insights into Jupiter, its atmosphere, and how it formed. But the big question goes unanswered. In 2011, a new mission, Juno, will attempt to find the answer. It will fly closer to Jupiter and gather more information than ever before. When Galileo's small probe plunged through Jupiter's atmosphere, it hit a dry spot. Just how much water Jupiter holds is still a mystery. Juno will take a different approach. Using the latest microwave technology, a radiometer, it will scan for water around the entire planet. Scientists hope that finding the missing data will finally solve the mystery of how Jupiter was formed.
What we're really after with Juno is the ingredients. From the ingredients of Jupiter, we're going to figure out the recipe. And that's what's going to tell us how planets are made.
With the probe having completed its work, it's now time for Galileo, 130,000 miles above Jupiter, to turn its attention to another long-standing mystery, the planet's weather. How can storms 3 times the size of Earth get so big and last for over 300 years? Jupiter's weather is a maelstrom of swirling clouds, lightning storms, and massive hurricane-like vortices. For the Galileo team, it's a mystery. On Earth, weather like this is powered by the heat of the sun, but Jupiter is 500 million miles away, so there must be some other source of power. Its most famous feature is the Great Red Spot, a storm whose clouds tower 5 miles above the atmosphere and plunge deep into a chemical soup below.
The red spot is red because of the chemicals that are trapped there in the center of the red spot have been baked and cooked by ultraviolet light and have turned red.
Astronomers have watched the Great Red Spot for at least 300 years. On Earth, even the biggest storms only last about 2 weeks. So how does the biggest storm in the solar system, 3 times wider than the Earth, get enough energy to rage unchecked for centuries? Scientists believe smaller thunderstorms could hold the answer. In order to solve the mystery, they had planned to video the Great Red Spot and other smaller storms in action. Understanding the mechanics of these turbulent weather systems, the Galileo team hoped to reveal the source of their power. With the high-gain antenna out of action, this simple solution won't be possible. The team back at Mission Control need a new approach.
Instead of making long, continuous movies, we made three-step movies. You watch the red spot, you come back a few hours later, you watch it again, and so it's just a three-step movie instead of a continuous movie.
Galileo homes in on a turbulent area of small white spots caused by what they think is convection or rapidly rising air. If these are storms, they will need to find proof. They need to locate another of Jupiter's most extraordinary features. Lightning bolts, 1,000 times more powerful than on Earth. But these are only visible at night.
Jupiter is 11 times bigger than the Earth. It's really big. If you look at this globe, you can see a few intense white-colored spots, small, intense white-colored spots. And when we got around behind Jupiter and looked at the night side, it was those very white-colored spots that had the lightning in them, and no place else. So that identified where the thunderstorms were.
Having identified the thunderstorms, the next step is to find out whether these small white spots can grow into larger ones. Galileo is in the right position at the right time.
There were some white ovals that formed in the 1930s, 3 of them, and they had been around for 60 years when suddenly 2 of them merged.
Galileo watches as 2 of the ovals merge to form a larger, more powerful storm. 2 years later, the 3rd oval also merges, forming one large storm in a belt below the Great Red Spot.
And then it had slowly turned red, so that it resembled the Great Red Spot, but not quite as big.
Nicknamed the Red Spot Junior, observations of its birth may also help to solve the mystery of where these large storms get their energy. Jupiter's storms are cannibalistic. They swallow smaller storms. This is how something as large as the Great Red Spot came into being.
It's like a food chain where the big fish eat the little fish and the little fish eat smaller fish. And the primary harvesters of energy on Jupiter are the little thunderstorms.
This accounts for the source of all the energy, but it doesn't explain why these vast storms last so long. Conditions on Jupiter are so turbulent that the storms should blow themselves apart. On Earth, vortices such as tornadoes soon die out, but on Jupiter, vortices last for years. Jupiter is the fastest spinning planet in the solar system, turning 22 times faster than Earth. Ironically, scientist John Arno thinks this rapid spin explains the stability of Jupiter's storms.
In rapidly rotating systems, vortices can be long-lived. It's very surprising. Normally we would think they'd shred themselves. They never do. What we've learned from these missions is that it's very coherent, is that it's very stable.
When 2 different colored dyes are mixed in a rotating jar of water, the results are startling.
At first, what looks like it's going to be a mess quickly turns out not to be a mess. Instead, we generate 2 large-scale vortices that you'll see are going to be very long-lived and coherent. And this is the idea. In rotating fluid systems, when you try to mix them, instead of just destroying any dye signal or any signal in the fluid, you get large-scale structures, similar to a Great Red Spot.
Galileo has revealed why some storms get so big and last so long. But scientists are still mystified by Jupiter's most distinguishable characteristic, its parallel red, white, and brown stripes. It was assumed that some colors are rising gases and others sinking. But Galileo finds this may not be true. Although its atmosphere is hundreds of miles deep, only the surface layer is visible. Here, high-velocity winds blow in opposite directions, causing these multicolored patterns to be dragged across the surface.
The colored bands are associated with vertical motion, and some of them are mapping out rising motion and some of them mapping out sinking motion. It may be that the rising motion happens at one level and the sinking motion happens at the same bands but at a different level.
They won't find out until the Juno mission in 2011 looks through the top layer of Jupiter's atmosphere to see just how the planet is spinning.
Is it all spinning as one solid body like the Earth does? And what we see on the surface is just a bunch of clouds, a surface meteorological layer? Or is it inside a little bit like an onion, where there's different layers, and each layer is spinning in a different direction and at a different speed? We don't actually know that answer.
Juno will orbit Jupiter 32 times, each lasting 11 days. The orbits will pass over Jupiter's north and south poles, shifting longitude with every flyby to scan a new section of the planet. For the first time, Juno will map Jupiter's entire atmosphere down to a depth of 350 miles. Jupiter's vast weather systems may finally yield their secrets. Scientists now realize that the planet's fast rotation maintains Jupiter's long-lived storms, but more importantly, it also drives Jupiter's most powerful force, its magnetic field.
And we can study that system and compare it with what goes on at Earth and learn a lot that will help us understand Earth as well.
The Earth's magnetic field is generated by the churning motion of molten iron around the core. Jupiter is made of gas, but at its core, the hydrogen is so compressed, it acts like liquid metal.
The magnetic field is created deep down in the planet where the pressures are so great that the hydrogen in Jupiter has become metallic. It actually behaves like a metal. And so it's moving around and currents are being created. And these manifest themselves out into the magnetic field that surrounds the planet.
The metallic hydrogen churning in Jupiter's core creates an incredibly powerful magnetic field around the planet. It stretches across the solar system to Saturn and beyond, holding in its grasp charged particles and gases.
It's enormous, 50 to 100 times Jupiter's size and going across, and the tail is dragged out by the solar wind all the way back to Saturn's orbit.
Jupiter's magnetic field is the largest object in the solar system. If we could see it from Earth with the naked eye, it would appear larger than our moon. It's also strong enough to divert the constant stream of sulfur emitted from the huge volcanoes on Jupiter's closest moon, Io. This material also funnels down toward Jupiter's poles, creating a breathtaking light display. Like Earth, Jupiter has northern and southern lights called auroras. For the first time, Juno will analyze the charged particles and magnetic fields that create these huge displays.
We're flying close, we'll dive underneath the radiation belts and out the other side. And we'll fly through the charged particles that bombard and light up the atmosphere with the northern aurora.
The team hopes the study of Jupiter will yield a better understanding of the dynamic processes that create Earth's own magnetic field. But the Jovian system has other secrets to offer. Its moons are not cold and inactive, but dynamic worlds that may hold the answer to the ultimate question: is there life beyond Earth? The Jovian system is immense. 63 moons orbit the planet, some large enough to be planets in their own right. They are also an enigma. Small planets and moons usually cool faster, So how can these moons be so hot and geologically active now? The answer may also contain a clue to the holy grail of science. Is there life on other worlds? The four largest moons are Ganymede, Callisto, Io, and Europa. Each one is profoundly different and holds incredible surprises.
Where every time Ganymede goes around once, Europa goes around twice, and Io goes around 4 times. It's not a coincidence. These moons have evolved into this wonderful cosmic dance.
Astronomers had expected Jupiter's moons to be cold, dead lumps of rock and ice. What Galileo finds are active, dynamic worlds. First stop, the mysterious Ganymede, the largest moon in the solar system. If it orbited the Sun instead of Jupiter, astronomers would call it a planet. These NASA images show its mountains, valleys, craters, and frozen lava flows. Almost immediately, the team finds something extraordinary. Galileo's magnetometer is picking up unexpected readings.
I was flabbergasted. The evidence right there that there was a magnetic field caused me to say, I don't believe it.
Ganymede is the only moon in the solar system with its own magnetic field. But it's a puzzle. The moon should be frozen solid. If Ganymede's got a magnetic field, it must have a molten core.
People had thought that a body of the size of Ganymede would have cooled off so much in the 4 billion years that the solar system has been around that it would have been solid all the way through. So we had to change our view of the evolution of Ganymede.
The discovery of Ganymede's magnetic field only deepens the mystery of how planets form. Something must have happened in Ganymede's past, something catastrophic enough to have heated up this moon.
Galileo showed us that Ganymede is a fascinating world, one that's gone through a very complex history, a world in its own right.
But as well as detecting Ganymede's normal magnetic field, Galileo finds a second varying field.
That's telling us there's probably also a liquid water ocean within Ganymede.
Scientists suspect this ocean is buried deep beneath the moon's rocky crust. The team is eager to investigate, but Galileo's orbit means it must leave Ganymede and move on. More surprises await. Next, the outermost of Jupiter's 4 largest moons. Callisto has its own mysteries. It's cold and rocky. The oldest and most heavily cratered landscape in the solar system. Its surface is scarred with ancient meteorite impacts. Scientists are perplexed by craters with strange bright rims. It seems dark surface material has slipped away, exposing the lighter material below. Nothing like it has ever been seen on Earth.
So what's the material made of that's slumping down? What's the process that's causing it to slump off? And it certainly proved to be a much more interesting body upon close examination than we ever thought.
Although the surface is a chilly minus 279 degrees Fahrenheit, Galileo's data suggests that just like Ganymede, Callisto can't be frozen solid. It detects a very weak magnetic field, suggesting it too may have an ocean. But the data is confusing. Other instruments aboard Galileo suggest that 125 miles beneath its surface, Callisto consists of a mixture of rock, metal, and ice, right down to its core. It's another mystery. The standard theory of how moons and planets form says that they should heat up when the material they're made of first joins together. The heat should then separate the rock from the ice. Strangely, on Callisto, it hasn't.
That would mean it never got really hot in there. How do you make such a large moon and not have it heat up? We still don't really understand Callisto.
Like so much of the Jovian system, Callisto raises more questions than it answers. We don't know what's going on inside the moon. We don't even know what material covers its surface. The story of Jupiter's next moon is equally bizarre. Io is the same size as our moon and is the closest of Jupiter's 4 large moons. It is the most volcanically active body in the solar system, with over 400 volcanoes, up to 124 miles across.
If you could have a bird's eye view of Io, it would be really extraordinary. You would see these plumes that are hundreds of miles high, these enormous lava flows, and big lava lakes just boiling and bubbling away on the surface that is all really strange and has these colors of pepperoni pizza.
Volcanoes constantly reshape Io's surface. Galileo's pictures are totally different from the ones Voyager sent back some 20 years before. But how can a landscape change so dramatically in such a short space of time? Huge craters seem to come and go. The cause of their disappearance seems to be giant plumes of sulfur-rich gases shooting around 200 miles above the surface.
We concluded that it was the plumes that were depositing fine material on the surface and actually erasing these craters over long periods of time.
But as with Jupiter's other moons, there is a further mystery. This much volcanic activity requires an immense amount of heat. But where does it come from? Io, 500 million miles from the sun, should be too cold. But clearly, it's not. Could the answer be gravity? Jupiter's gravitational field keeps Io in orbit, but as it goes around, it passes on the inside of Jupiter's other moons. Their gravity pulls Io in the opposite direction. That distorts Io's shape. It's the distortion that creates the heat.
As Jupiter's large moons orbit around the planet, they're pulled and pushed and squeezed as they go around in their orbits. And this creates heat, friction, and causes melting within Io of the rock to power its volcanoes.
It raises tides on Io, very much like the moon raises tides on the oceans on Earth. Only on Io, the whole surface goes up by over 300 feet. Can you imagine what it would be like on Earth, like here in Los Angeles, if the crust of the Earth was rising 300 feet?
It's an astonishing discovery. A world shaped by forces so violent, it's pulled apart like taffy. Yet amazing as it sounds, of all Jupiter's moons, Io may not be the strangest. The next moon on Galileo's path, Europa. Its surface is covered in strange geological shapes and parallel tracks that cut across the ice. It's an ice world with an extraordinary secret. Could it harbor the ingredients for life? Images of Jupiter's moon Europa from earlier missions reveal a pinkish-white world. But Galileo finds fewer meteor craters than expected. That means something is erasing the craters after they form. Because Europa's surface is ice, scientists believe water could be welling up from below. This moon is so intriguing, the team wants a better look. But to do so means spending more time at Europa than planned.
The original schedule called for only 3 flybys of the moon Europa, but the evidence was so compelling that it compelled the mission to be extended in length and to go back several more times.
Galileo's first job is to image the moon in greater detail. The question is, how active is Europa's surface? Are the processes that erase impact craters fast or glacially slow? The team begins by assuming the process could take billions of years. That changes fast.
I'm listening to them discussing the age of Europa's surface dropping. Oh, well, maybe it's a couple billion years old. And then the next flyby, well, it might even be 100,000 years old. And then the next flyby, it may be currently active.
While measuring Europa's magnetic field, Galileo uncovers another mystery. As the moon orbits Jupiter, its magnetic field shifts. Europa must have a conductive layer which allows Jupiter's magnetic field to pass through it. There is only one thing that could cause this, and it's a big surprise for the Galileo team.
We were able to interpret these signatures as being produced by a global ocean beneath the surface of the ice.
Scientists believe Europa's ocean is vast. It covers the whole globe to a depth of 100 miles, making it the largest body of liquid water in the solar system. If so, the team must first address a fundamental problem. Europa's surface temperature can reach minus 200 degrees Fahrenheit. Why doesn't such a huge ocean so far from the sun freeze? Astronomers think the answer may be the same one that drives the volcanoes on Io. Jupiter's gravity stretches and compresses the moon, creating heat within. It's the heat that keeps the surface in constant motion. This could also explain some unusual features found on Europa.
Galileo images showed that ridges crisscross the surface of Europa. These are bizarre features that travel across the surface for up to 1,000 kilometers, and typically in pairs. That is, a ridge with a depression in the middle and another ridge. These are bizarre features like nothing we see on the Earth.
At first, these ridges are a puzzle, but researchers soon come up with a solution. Planetary scientist Bob Pappalardo reproduces the effect with ice blocks in the lab.
As Europa is flexed by Jupiter's gravity, its surface bends and cracks and makes fractures through the ice. Well, as it's squeezed and bent, the ice slides back and forth along these fractures. Now this can create heat as these blocks move by one another. And that heat can warm the ice on either side of the block, and that warm ice rises up to form these strange ridges that we see, these tracks that seem to go across the tundra of Europa.
Galileo reveals a world in constant motion, evidence of heat hidden below the ice. Flows of material on the surface are possible evidence of ice volcanoes or geysers. Brown-red stains stretch across the ice where it has cracked open, and salty material from the interior has welled up from below.
We see pits and spots and domes on the surface of Europa that might be related to the rise of blobs of warm ice that move up through the shell, sort of like a lava lamp.
Heat from the interior of the moon may even drive hydrothermal vents in the ocean. On Earth, hydrothermal vents on the seafloor are hotspots for life. Galileo's data also suggests there's carbon dioxide frozen on Europa's surface, possibly welling up from the ocean below. If so, the find is huge, because CO2 is vital for life. Does this mean there's life on Europa?
I'm in the camp that where there's water, there's a very good chance that there's life, and where there's materials for that life to use. And on Europa, we seem to have the materials and we have the water.
If we search and find life within the ocean of Europa, that'll be an enormous leap in understanding whether we're alone in the universe or whether life may be everywhere.
The search for life is an irresistible lure. Scientists are desperate to go back to Europa, and near the end of the next decade, they hope to launch a groundbreaking mission to orbit the moon. The Europa Explorer will take the first steps toward answering the biggest question of all. Is there life on other worlds? It will survey the ice on Europa's surface. As well as analyzing its structure, it will search for spots where we could one day break through to the ocean beneath.
We need to measure the gravity in detail. We need to do radar studies. We need to look at the surface composition. We need to understand the geology. We need to understand that tidal flexing that heats the interior and causes that thick layer of ice to flex with the tidal forces.
The Explorer's main tool is radar. It will give scientists a 3D map of Europa's crust. This will tell them just how thick the icy shell is.
How far beneath the surface the ocean is, if it's a global ocean, how deep it is, how thick the ocean layer is.
These are crucial questions. Once scientists know how thick the ice is, the next step is to work out how to get beneath it, and that will mean a completely new mission. A probe that will not only orbit Europa, but land and explore its subsurface ocean. Endurance is already at work in Antarctica. A robotic submarine. It's the first of a new breed of underwater probes that can also operate under the ice. The aim is to create a vehicle that needs no instructions from home. Endurance must make decisions all by itself.
Every vehicle we've sent to space so far has the ability to talk back to Earth, get commands from Earth, and have people in the loop. This will be a whole new ballgame, and it's something that we're going to be able to test in Antarctica.
Endurance is currently investigating a lake hidden under nearly 15 feet of ice in Antarctica. Perhaps one day, a vehicle like this will search for life on Europa. But first, it has to get through the ice.
That thick ice cover, it takes a lot of energy to melt ice. People don't usually appreciate that, but we'll need some kind of nuclear system that will melt that ice, and it will take weeks, perhaps months, to get through that ice.
We might imagine a lander spacecraft that melts its way all the way down to the ocean and explores what's really down there.
The discovery of life on another world would be one of the greatest finds of all time.
We're not talking about fish or whales or the Loch Ness Monster. We're talking about microbes. Could there be tiny single-celled organisms within the ocean of Europa?
I mean, if you just find bacteria, it would be fascinating. But who knows? You know, maybe there's something more sophisticated, something swimming around. Who knows?
Even the simplest life forms would have profound implications.
If life exists in the ocean of Europa, that would tell us that life probably exists almost anywhere there's a water-rich environment. That would be an amazing discovery.
Jupiter and its moons have already transformed our understanding of our place in the solar system. Now, new missions to Europa may finally prove that life on Earth is not unique. And if there's life on two worlds, then why not on many? Jupiter and its moons may one day give us hope. We will find not just life, but intelligence out among the stars. Diamonds, 4 billion years old, and they still dazzle us. But these rocks aren't just for show anymore. Hidden inside are powers that could change your life.
The future of diamond is very exciting and opens up what many of us have been calling the new diamond age.
To reach that shining future, scientists have to outdo nature and build a better diamond.
The new synthetic diamonds, that's a technology that's going to take us places we've never been before.
It's a dazzling challenge. Can science do the unnatural and make a super diamond? Diamonds are like no other substance. They're 4 times harder than any mineral on the planet. They resist corrosion. The best are completely transparent. And they conduct heat. Some can conduct electricity.
What you have is a material such as diamond that has a fantastic range of unique properties, and it's the combination of these unique properties that makes diamonds special.
If science can harness the powers of these stones, it could revolutionize our lives. From the microchips in our phones to the machines that explore space.
They'd be super durable, they'd last forever. They'd be resistant to heat and cold and the other kinds of extremes.
It's said diamonds are forever, but they aren't. Most contain natural flaws, flaws that can't withstand extreme heat and pressure. To transform technology, science must do something unnatural. Create the ultimate diamond in the lab.
Nature is the guideline, and the question is, can we improve upon it? The race now is to produce a super diamond.
A super diamond would have all the properties of a natural diamond, but could be manufactured in any shape or size. Most of all, they would mimic the properties of the rarest gems, like this one. The Hope Diamond, perhaps the world's most perfect natural diamond. It's kept behind bomb-proof glass in the Smithsonian Institution in Washington, D.C. At 45.5 carats, this gem is over 100 times bigger than the average diamond ring. It's one of the largest and most valuable diamonds ever discovered, worth around $250 million. But that's not all. This gem has some unusual properties that highlight what makes diamonds so special. Jeffrey Post, the curator of the National Gem Collection, is researching this stone. In the lab, he demonstrates a phenomenon that sets the Hope Diamond apart from most others.
We can take an ultraviolet light and we can expose the Hope Diamond to the ultraviolet light, and we'll leave it on for about 10 or 15 seconds. Also notice that one of the white diamonds on the outside fluoresces very bright blue. And so now we're going to turn the room lights off, and I'll turn off the ultraviolet light, and we can see the intense orange glow, the property called phosphorescence.
For years, this glow was attributed to a curse cast over the diamond when it was stolen from an Indian temple centuries ago. But Post isn't superstitious.
So here you've got supposedly a cursed diamond that glows this blood red color. Well, you know, that's a great story in itself. But then the scientist in many of us says, well, why does it do that?
Post and his team investigate using a spectrometer, an instrument that analyzes wavelengths of light. The spectrometer shows that the Hope's distinct hue comes from 2 colors, aqua and red.
3, 2.
The team can now identify 2 chemical elements in the diamond, boron and nitrogen.
Suddenly, now I understand what is going on when this diamond is phosphorescent.
Boron makes the stone blue. When combined with nitrogen, the stone shines red. Chemicals, not a curse, make the Hope glow. It's not the red glow that excites scientists, but the element that makes the Hope blue, boron. Boron does more than color diamonds. it also allows them to conduct electricity.
Blue diamonds, because of the boron present in them, are in fact semiconductors of electricity, which makes them very different than other diamonds that are pure carbon.
Pure white diamonds are electrical insulators. Try to pass a current through them, and nothing happens. But blue boron-rich diamonds, like the Hope, are electrical conductors. The extra atoms of boron interact with the existing diamond atoms, letting an electrical current pass through. But all diamonds, not just blue diamonds, have another useful property. They transfer heat better than any material known. If science could make synthetic diamonds that both conduct electricity and transfer heat, they could revolutionize a critical component of daily life: the semiconductor. Semiconductors are the vital component in nearly every electronic device. In transmitting electricity to the precision control of microchip technology. For the past 50 years, these devices have been made almost exclusively from silicon. But silicon has a major drawback. The more electricity it carries, the hotter it gets. The result? Most silicon chips require complex cooling technology. If they exceed about 300 degrees Fahrenheit, they'll shut down.
One of the huge hurdles that are facing manufacturers is that they have to be able to remove the heat away from these electronic systems. You know, think of your own laptop at home as you're operating it. It gets hot. And so this becomes a big problem. Right now they're using metals mostly to do that. But diamonds, in fact, are much better conductors of heat than metals are.
With the discovery that blue diamonds transfer heat and conduct electricity, scientists can imagine the unimaginable. A world beyond silicon. A world where everything from your cell phone to a spacecraft runs on diamonds. Diamonds can carry 30 times more power than silicon and operate 3 times faster. And they're so efficient at transferring heat, they could run a computer at speeds that would melt a silicon chip. They also resist temperatures over 1,800 degrees Fahrenheit.
To be able to coat electronics with diamond or use pieces of diamond as the heat sinks would certainly offer a whole new direction for the manufacture of even smaller, more powerful electronic devices.
Despite their eye-catching sparkle, diamond's real potential has been overlooked for centuries. The possibilities for technology are almost endless. But there's one problem. Diamonds are rare and expensive. Natural semiconducting diamonds like the Hope are thousands of times more rare. And they don't come in the right shape or size for industrial use. So scientists are trying to create a synthetic super diamond with all the powers of a natural blue diamond, but in a size and shape of our design. To succeed in creating a super diamond, scientists must first discover how nature made hers. And for the answer, they look to the stars. For scientists to create a synthetic superdiamond, they must first get back to basics and investigate the ingredients of a natural diamond. For all their rarity, diamonds are made from one of the most familiar elements on Earth: carbon. carbon is so fundamental, it forms the basis of everything around us. Even we are 18% carbon. It's so common, it's estimated that our planet contains over 100 million billion tons of it. But carbon doesn't originate on Earth. It comes from long ago and far away. A star on the brink of death. A red giant. Astrophysicist Neil deGrasse Tyson studies carbon's dramatic formation.
Well, the universe is born without any carbon. Our sort of birth ingredients are hydrogen and helium and just trace amounts of lithium. So carbon comes later. Carbon is forged in the cores of stars.
This red giant star once looked like our sun. But as it ages, it grows over 1,000 times bigger. Instead of glowing white hot, it glows red as it reaches the end of its life. It's running out of fuel. Its core is now composed almost completely of helium. In its death throes, a nuclear reaction in the core breaks down helium and fuses it together in a new configuration: carbon. Dying red giants are the universe's carbon factories. Eventually, the star explodes in a white-hot flash, so strong that billions of tons of carbon are flung out into the farthest reaches of space.
What happens is the star collapses, and the entire core, in response to this collapse, rebounds and explodes. A titanic explosion we call a supernova. And its guts are scattered everywhere. And it's a spectacle. It's so much of a spectacle that you can see these stars explode halfway across the universe.
In time, the vast cloud of debris from the explosion is pulled into orbit around a new star. As this debris spins, it clumps together. Over millions of years, these clumps grow, and planets begin to form. This is how our solar system and our planet itself was born. And it's why Earth holds the raw ingredient for diamonds, buried deep in huge quantities: carbon. For scientists hoping to create a super diamond, a problem. The form carbon usually takes is weak. Carbon in its most familiar form is graphite. Great for pencils, but far too soft for high-tech products. Bob Hazen, research scientist at Washington, D.C.'s Carnegie Institution, is an expert on carbon and diamond formation.
You know, it's amazing. Diamond and graphite are made out of the same element, carbon, but they're so vastly different. Graphite has these planes of weakness, and you can see how every one of these black dots, the carbon atoms, are connected to 3 other carbon atoms in a triangle. But in diamond, every carbon atom is now connected to 4 adjacent, and this trellis, this network, this lattice. So diamond is strong in every direction. That's the difference.
For scientists hoping to create a super diamond, making it hard will be tough. They have to recreate a diamond's lattice-like structure. To do that, they have to figure out how nature turns basic carbon into a dazzling diamond. Scientists are on a quest to figure out how to make a super diamond. Their search begins here, South Africa, diamond capital of the world. Diamonds were discovered in these rocks in the 19th century. Hundreds of thousands have been mined here, but only recently did scientists learn how they actually formed. Professor Steve Haggerty is an expert on how diamonds are created.
Diamonds were a real mystery in terms of their origin. They were found in clusters. So you found one diamond, and by golly, there would be others to be found as well. So that led to the notion that the process in which the diamonds were brought to the surface was possibly deep.
Diamonds form deep within the Earth in an area called the mantle, the layer between the Earth's crust and its superheated core. Down here, intense pressure changes the molecular structure of carbon by crushing its atoms together and forcing them into a new lattice-like structure. Under extreme pressure and temperatures, carbon becomes diamonds.
The temperatures have to reach about 1500 degrees centigrade and the pressures about 50 kilobars.
That's 2,700 degrees Fahrenheit and the weight of over 4,000 grown men standing on your foot. The journey from a dying star to a diamond mine is almost complete. 100 miles still remain between their source in the mantle and the Earth's surface. Luckily, they're fast-tracked to the surface by a substance called kimberlite.
Kimberlite is a rock, it's the host rock to diamonds. Even though the diamonds do not form in the rock, it's the transporter.
Kimberlite is a volcanic rock that forms deep within the Earth. As it moves to the surface, it creates a carrot-shaped pipe filled with molten rock, mantle fragments, and diamonds. When it breaks through the crust, it erupts in small but violent volcanoes.
I like to think of these as volcanoes of opportunity. These rose, they picked up the diamonds from their safe deposit boxes deep in the earth about 200 kilometers down, and then were explosively erupted.
At the surface, magma builds up a mound of volcanic material that eventually cools and hardens. Hidden within the rock are diamonds, incredibly rare, perfectly formed crystals surrounded by kimberlite. Rarer still are blue boron-rich diamonds, like the Hope. Less than 1 in 100,000 form this way. "4 billion years from a dying star to the Earth's surface. Yet in a matter of days, scientists aim to turn raw carbon into super diamonds."
In order to produce anything of that nature, it would require extraordinarily high temperatures and pressures. It turns out that it's not very easy to transform graphite into diamond.
The attempt began in the 1950s, when General Electric launched Project Superpressure. Their goal, to create the first synthetic diamond. They developed machines to crush graphite at nearly 800,000 pounds per square inch and heat it above 2,500 degrees Fahrenheit, replicating the very forces in the Earth's mantle. It takes 5 years and millions of dollars, but finally, in February 1955, GE announces they've done it. The world's first synthetic industrial diamond. Over 50 years later, just outside Johannesburg, South Africa, a lab called Element 6 continues the quest for synthetic diamonds. Following GE's lead, They synthesize diamonds on a mass scale, not for jewelry, but for heavy industry. Scientist Richard Botkin is a pioneer of industrial diamond research.
We have banks and banks of presses that are capable of producing diamonds in no fewer than 45 minutes. To see such technology room after room is absolutely amazing.
The diamonds they produce start as a highly pure form of graphite powder. It's baked inside a pressure chamber between 2,500 and 3,600 degrees Fahrenheit.
Effectively, you're stacking 20 sedan motor cars on it and heating it between 1,400 and 2,000 degrees Celsius.
The result is a diamond 50% harder than those found in nature. And element 6 can produce handfuls. These diamonds have revolutionized the drilling and mining industries. The friction from drilling into hard rocks, like granite, generates high temperatures that can damage ordinary drills. But diamond tip drills transmit heat away from the drill tip.
Oil and gas drilling benefits immensely from diamonds simply because we can drill faster and deeper with diamonds.
One shortcoming: industrial diamonds are small. The next challenge is to create diamonds large enough to be printed with circuit boards or shaped into other high-tech devices. It's a challenge that the Sarasota, Florida company Gemesis is tackling. Using a special machine, they actually grow large diamonds. They start with a seed, a microscopic diamond, either natural or artificial, and surround it with graphite. It's a delicate process that shows how hard it is to create large diamonds. In charge of the process is Chief Operating Officer Clark McEwen.
We take graphite and we put it along with an actual diamond seed into an environment that emulates what happens within the Earth.
These two forms of carbon, the diamond seed and the graphite, are placed inside the chamber, where they're heated and crushed by a powerful hydraulic press.
As you apply that temperature and pressure, what happens is that graphite turns into individual carbon atoms. And those atoms permeate down and it finds that diamond seed and it attaches to it. It acts as a template.
As the graphite melts, it releases carbon atoms, which crystallize on top of the diamond seed. Molecule by molecule, the diamond grows. What nature does in 4 billion years, they do in 4 days. The result? A large artificial gem, up to 3 times larger than the seed. With this breakthrough, scientists can now consistently make large diamonds. But the real breakthrough that scientists need is yet to come. Gemesis can't grow diamonds in the shapes needed for high-tech use.
We haven't gotten there yet, but we're constantly working on improving the process and making larger and better quality diamonds.
Scientists are trying to create a large diamond with all the properties of a real diamond, but in shapes and sizes not found in nature. From circuit boards to scalpel blades, the uses could be endless. As scientists struggle to perfect the diamond, a clue hurtles toward Earth from an unlikely place. After years of research, scientists discovered how to make gem-sized diamonds. one hurdle remains to making a true super diamond, making them in any shape and size. Science needs a breakthrough, and it comes from space. These strange objects look like burnt stones. They've been found in South America and Central Africa. Tests reveal a surprise. The stones are actually diamonds, black diamonds.
These are two of the famous black diamonds called carbonado because of the similarity to charcoal.
Carbonado has been known for centuries, but how it forms remains a mystery. Only recently has its potential value to science emerged. George Harlow of the American Museum of Natural History is investigating what makes carbonado so special.
Carbonado is a conundrum because it doesn't have the characteristics that we associate with diamonds that formed in the mantle on Earth.
Diamonds originating in Earth's mantle form under immense pressure and high temperature, so they're compact and dense. Not black diamonds. Using a microscope, scientists find they're riddled with holes.
It's got a lot of void space in it. Now, deep within the Earth, the void would have to be filled with something. Well, the something ain't there.
Normal diamonds contain very little void space. As they form deep in the Earth, they're crushed into a single crystal. Carbonado seems to form differently. Unlike normal diamonds, it's composed not of one crystal, but millions, all linked together. Scientists conclude carbonado formed not under high pressure, like normal diamonds, but low pressure. But just where does carbonado come from? Once again, research leads to the last gasp of a dying red giant.
The current theory for the origin and genesis of carbonado is that the small diamonds formed in supernova explosions.
Haggerty believes the vacuum of space explains carbonado's unique structure.
The diamonds were hot, one diamond bashing into the other, and they finally became glued to form a larger diamond.
During its explosive formation, specks of mineral dust are also trapped, making the large diamond appear black. The diamonds are then transported to Earth by a meteorite.
When the meteorite hit, it showered diamonds, so this must have been a truly amazing sight, with carbonado diamonds being liberated from the meteorite on impact.
It's not just the large size of space diamonds that fascinates scientists. Carbonado has another advantage over regular diamonds. Its multi-crystal structure makes it not only larger, but tougher. It's almost impossible to cut. Not so a natural diamond. Although it's one of the hardest materials known, it has its weaknesses.
You know, diamond's incredibly hard, but it can be broken along certain planes. They're called cleavage planes. And it just happens that there's certain directions in diamond where there are fewer strong bonds, and that's the direction the diamond opens.
A natural single crystal diamond will split cleanly where its chemical bonds are weakest. By following this cleavage plane, a gem cutter can split the stone perfectly. For scientists, this weakness in single crystal diamonds is a fatal flaw. Diamonds that might fracture aren't durable enough for high-tech use. The key to making a tough super diamond lies in replicating Carbonado's multi-crystal structure. Their theory of how Carbonado forms in the vacuum of space yields another breakthrough. A whole new way to make diamonds.
The space diamonds have now taught us that, in fact, we don't need pressure at all. This can be done in a vacuum.
Carbonado sets the stage for a new kind of super diamond. One tougher and larger than ever. That can be made into multi-crystal shapes not found in nature. The key is using low pressure to simulate the vacuum of space.
How do you make a diamond in a vacuum when diamond's only stable at high pressure? And the way you do it is by fooling the carbons into being so energetic, so excited, that when you cool them down, they find a more stable configuration. And the first one they find is diamond. And they don't go any farther.
This process is called chemical vapor deposition, CVD for short. It begins with a tiny diamond seed sealed inside a vacuum chamber slightly below atmospheric pressure. The chamber is heated to 3,600 degrees Fahrenheit. Then methane, a carbon-bearing gas, is pumped in. Then hydrogen. The gases are bombarded with microwaves, which agitates them, forcing the hydrogen and methane molecules to collide. This process releases a cloud of carbon atoms that settle on the seed, and gradually, the diamond grows. This was the seed they started with. 24 hours later, it doubles in size. At the U.S. Naval Research Laboratory in Washington, D.C., James Butler is taking this CVD process to the next level. They're growing not single stones, but wafer-thin diamond sheets.
One of the materials we grow starts with a non-diamond material, for example, a silicon wafer, onto which we put a very thin layer of these little diamond seeds. Think about shaking salt onto the kitchen table and having a whole bunch of salt crystals there. And then we put them in the CVD environment and they will grow. And as they grow together, they bump into each other and they become this mass. So it's all diamond, but with many different grains of different orientations.
Each diamond crystal bonds to another to form a mesh of crystals across the wafer, less than a 50th of an inch thick. They can be made up to 8 inches wide. The shape of the template determines the shape of the diamond sheet. Perfect for making a wafer to replicate silicon. They're much tougher than natural diamonds. They conduct electricity and resist extreme heat. These are true super diamonds. Super diamonds have been filmed with image intensifiers that show how much more efficient diamonds are at conducting heat than the copper traditionally used in electronic components. The left plate is made of synthetic diamond. On the right, copper. The two plates are placed in ice and attached to a thermal image intensifier, which records heat as it travels through an object. As the diamond plate on the left shows, it conducts heat faster than copper, up to 5 times faster. It's this unparalleled quality that puts the super in super diamond. Scientists are excited. For the first time, they have a material that could challenge the domination of silicon. Microchips made from diamond wafers can run electronic devices at higher speeds and with more power without overheating. Faster, smaller, and more efficient. Razor-thin computers, long-lasting cell phones, and picture-perfect TV screens.
I think the future of diamond is very exciting. Particularly, I think CVD diamond opens up what many of us have been calling the new diamond age.
Electronics are only the beginning. Today, scientists can make diamonds in shapes and sizes for uses that could revolutionize tomorrow. Researchers at the Carnegie Institution in Washington are trying to solve some of science's biggest mysteries. From how compressed gas can conduct electricity to how microscopic life can survive in extreme conditions. These investigations need extremely high pressures, which they create using a powerful vise called a diamond anvil cell. It squeezes an object between two diamond tips, creating a tiny environment of high pressure between them. It can recreate forces as extreme as pressure in the center of the Earth. For the Carnegie team's experiments, this wasn't extreme enough. But when they pushed the pressure higher, they hit a snag. The diamond shattered. Russ Hemley, director of the geophysical lab, decided to upgrade the anvil by making an ultra-hard super diamond.
Well, our group has been very interested in using diamond for high-pressure experiments for many, many years. And we basically needed to take this to the next level. We needed better diamond, stronger diamond, larger diamond that could be provided by Mother Earth or from conventional processes.
To create his super diamond, Hemley used a version of the CVD method to speed up the growth rate. The team then exposed the crystals to a high-pressure, high-temperature treatment to further harden them. The result? Another leap forward for super diamonds. The diamond not only grew many times faster, it also grew bigger. 15 carats. In just 6 days, they'd created a stone 1/3 the size and 50% stronger than the Hope Diamond. A gem that took nature billions of years to forge. The new super diamond was so tough, it broke Hemley's hardness gauge. When used in the diamond anvil, this new super diamond proved the breakthrough he needed.
This can produce pressures that are millions of times the pressures found at the surface of our planet.
Now, he can simulate forces so extreme they've never been studied before. Like those deep in the Earth's mantle, where pressures reach up to 1,300 kilobars. That's nearly 20 million pounds per square inch. This improved instrument lets Hemley study some of our biggest questions, like is there life in outer space? Hemley's team takes 2 common strains of bacteria, including E. coli. They place them in a liquid and crank up the super diamond anvil. The liquid turns into a dense form of ice. Under the intense pressure, most of the bacteria are destroyed. But incredibly, 1% survive. If bacteria can survive these harsh conditions, maybe life exists in outer space, perhaps on other planets. Thanks to superdiamonds created under low pressure, diamonds will reshape the future. Superdiamonds will change communications everywhere, especially on the battlefield. In constant use and battered by the elements, equipment like radios often break down in the harsh conditions of combat. But imagine if they were made of superdiamonds. Already, they can be shaped into tiny sound transmitters called nanoresonators, making vital radios and computers more robust and efficient. They can vibrate up to 100 billion times per second to create the highest quality sound yet achieved. Yet, they're tough as nails. All this from a diamond 1,000 times smaller than the width of a human hair. It's not just soldiers who will benefit. Diamond resonators will eventually be used in everyday devices like cell phones, allowing longer talk time and crystal clear reception. The same sparkle that attracts us to diamond jewelry reveals another of its secrets, its clarity.
It's transparent to light. It slows down light that passes through it.
As light enters a diamond, the dense carbon structure slows it down to less than half its normal speed. As it reflects inside the stone, the light appears to hang around longer.
You can actually force light to completely internally reflect and come out at some other angle. That's why diamonds look radiant, because light comes in from one direction, comes out another. It makes you think it's generating its own light, but it's not. All it did was redistribute the light coming in from other angles. It's remarkable.
Now you know why diamonds sparkle. The unique optical clarity of diamond, the perfect material for high-tech optical uses. Diamond is transparent across a huge spectrum of light, from ultraviolet to infrared. It's the only substance through which light passes virtually unaltered. From super diamonds, NASA can make super hard, super clear windows. The possibilities for super diamonds are endless. Soon, you may find a diamond everywhere, from your desk to your galaxy.
The future of diamond, we're just seeing the very beginning of it, and I mean the stars are the limit when it comes to what we're going to be able to do with diamond in the future.
Nature took billions of years to perfect the diamond. Now, we make super diamonds in days. Tougher, bigger, and better.
The new synthetic diamonds, that's a technology that's going to take us places we've never been before. It's going to take science in new directions. It's going to allow us to do things we could never do before. So the natural diamond, we treasure that as an object. The synthetic diamond, that will give us knowledge.
Like steel, transistors, and silicon, synthetic diamonds could revolutionize life. Welcome to the age of super diamonds. Venus, Earth's evil twin. Its clouds made of battery acid. At 900 degrees, its surface hot enough to melt lead.
Venus is pretty much like the biblical vision of hell today.
This may be the most hostile real estate in the solar system. Yet billions of years ago, Venus looked a lot like Earth. Why it changed, nobody knows. new probe is on a mission to find out. What turned Venus from a promising Eden into an infernal wasteland? And is Earth destined to end up like Venus? November 9th, 2005. A Russian Soyuz rocket launches from Kazakhstan, carrying a tiny European spacecraft called Venus Express. Its mission, to travel the 250 million miles to Venus and find out why the planet evolved so differently from Earth. For centuries, Venus's surface remained an enigma, obscured by layers of dense clouds. Because Venus is closer to the Sun than Earth, scientists assumed it would be hot and humid. Some even imagined a tropical paradise. The perfect hothouse for life.
Venus should be about the same temperature as the Earth. And that's what we thought back in the 50s and early 60s. We thought Venus should be like Miami, Florida.
What was really going on beneath the clouds? In the 1960s and 70s, while NASA explored Mars, the Soviet Union launched a probe to Venus. Codenamed Venera, the craft beamed back the first images of the planet's surface. Not a tropical paradise, but a hostile desert. Lots of dust and no water. Venus resembles its twin Earth in many ways. Similar in size and composition, they were probably formed from the same cloud of gas over 4 billion years ago. But unlike Earth, 85% of its surface is made up of extinct volcanoes and solidified lava. The clouds are composed of deadly sulfuric acid. Atmospheric pressure is 90 times greater than on Earth, enough to crush a car. But the biggest surprise is temperature. The atmosphere is nearly all carbon dioxide. As on Earth, this gas acts like glass in a greenhouse, admitting light, but trapping heat. On Earth, increasing levels of carbon dioxide are raising temperatures a few degrees. But on Venus, the greenhouse effect has pushed temperatures through the ceiling to levels hot enough to melt lead.
We get there to find out that it's 900 degrees Fahrenheit, and it was very shocking.
The surface is so hot, rocks glow in the dark. Venus would disorient a visitor from Earth. Under permanent cloud cover, you'd lose your bearings. No stars, no sun, no shadows. To find out how these two identical twins, Venus and Earth, grew to be so different, Venus Express carries state-of-the-art instruments designed to unlock the planet's secrets. But the spacecraft's first challenge is just getting there in one piece. 5 months and 250 million miles later, the spacecraft nears Venus, and the most dangerous stage. To achieve orbit will take perfect speed and timing.
Space is never really safe. There's always something that can go wrong, and you have to kind of provide for contingencies for that.
Too fast, and Venus Express will fly off into endless space. Too slow, and the planet's gravitational pull will bring it crashing to the surface.
The actual day of arrival, you have about an hour and a half that it's really kind of tricky. You want to make sure that you hit the right spot relative to Venus and that you're bending around Venus the right way.
To get into orbit, Venus Express must reduce speed by 3,000 miles an hour. April 11th, 2006. The engine fires to slow down the craft. For 10 minutes, Venus Express vanishes behind the planet. If it fails to achieve orbit, it's lost. No second chances. A 4-year mission hangs on hitting the brakes just right.
The most critical maneuver is happening out of sight and out of sound from the Earth. So it's a very harrowing time because you do lose communications for 10 minutes and everybody's on pins and needles to see what happens.
At 9:57 a.m., Venus Express transmits a signal to Earth. The spacecraft's pioneering orbit begins. A multi-million-dollar quest to unlock Venus's secrets. But first, it has to get closer. On an elliptical course around the planet's poles, the craft drops down from 40,000 miles above the surface to just 155 miles. Now, the work begins. The technology on board is a quantum leap forward from the last mission to Venus in 1990. Before, a probe couldn't analyze Venus's surface without landing. All the probes had a short life, crushed by the pressure, melted by the heat, and corroded by the acid. With this mission, scientists have found a way to study the surface without landing and keep their probes safe. Venus Express views the planet using infrared, a wavelength not visible to the human eye. Unlike visible light, the infrared can penetrate areas of cloud that are less dense, allowing the probe to peer through the clouds to the clear atmosphere below. Now, for the first time, scientists can reveal Venus in 3D from the ground up.
With Venus, when you look with the visible eye, you're limited to the very top 1% of the atmosphere. The upper regions, you see these hazes. When you get the ability to look with the infrared light, it allows you to pierce right through all these hazes and see down much lower into the atmosphere. In fact, you can go to the surface.
From 155 miles up, scientists will exploit these infrared windows to map the surface in detail never before seen. Their map will document exactly how Venus and Earth differ. Then, they hope to find out why. Despite decades of exploration, our sister planet can still surprise us. And soon, Venus Express makes a stunning discovery. A spacecraft orbits Venus on a mission to solve a mystery. Venus should be like Earth. But billions of years ago, our twin went its own way and evolved into the burning rock it is today. While studying the outer edge of the atmosphere, Venus Express discovers the first clue to what went wrong. It detects particles escaping into space, mainly helium, hydrogen, and oxygen. Hydrogen and oxygen make water. For years, scientists debated whether Venus's atmosphere held any water. Some argued if early Earth had water, so did Venus. Perhaps enough to form an ocean covering 90% of the planet. Yet Venus Express detects only a small amount of water vapor in the atmosphere. If you condensed all that vapor onto the whole planet, it would create a layer of water barely an inch deep. If Venus once had a vast ocean, what happened to it? Most scientists once thought it simply boiled away. But as Venus Express orbits the planet, scientists are forming a new theory. They believe the culprit is still the sun, but the cause is more than simple evaporation. The sun sustains life on Earth. It also blasts out a constant stream of deadly charged particles. They race out at speeds of up to 1,800,000 miles an hour. It's called the solar wind, and it can devastate unprotected planets. Surrounding Earth is a magnetic field that safeguards our atmosphere. This field is formed by movement in our iron core as the planet spins. But Venus has no magnetic field. Scientists believe it may rotate too slowly to generate one. The rotation is so slow, a day here lasts almost 2/3 of an Earth year. On Earth, one rotation takes 24 hours. On Venus, 243 days.
Well, without a magnetic field like Earth's, Venus is much more vulnerable to being affected by the solar wind and by energy in the upper atmosphere, stripping the atmosphere off into space.
Scientists now believe a combination of evaporation and solar wind strip the planet of its moisture. Venus is closer to the sun than we are, therefore hotter. Its primeval seas evaporated into the atmosphere. That water vapor might still be trapped in the clouds, if not for the solar wind.
The oceans ultimately boil off, and then when you have all that water as vapor in the atmosphere, it's very vulnerable to being broken up by ultraviolet sunlight into hydrogen and oxygen, and then the hydrogen escapes into space, and there you have it. After a few billion years, you've lost your oceans.
The solar wind smashes into the atmosphere, ripping the molecules from the clouds. Over billions of years, the water is lost in space. The oxygen and hydrogen detected in the atmosphere are the last drops of those ancient oceans. Loss of water turned Venus from a warm, wet planet to a burning rock. The atmosphere changed too, from water vapor to carbon dioxide. Ancient volcanoes released trillions of tons of CO2 and set off a chain reaction, a runaway greenhouse effect, leading to global warming gone mad.
The energy for both climate and weather on planets all comes from sunlight. So now imagine that this is sunlight heading towards the surface of a planet. And on a planet like Earth, where there's not much atmosphere, as represented by these atmospheric molecules here in blue, most of the sunlight will miss the atmosphere and just make it to the surface. And occasionally you'll have sunlight scattering off an atmospheric molecule. But for the most part, you just have these yellow rays of sunlight reflecting off the surface. Now, let's set up again and look at what happens on Venus. And I'm putting much more gas in the atmosphere because now we're simulating Venus, which has 100 times as thick an atmosphere as Earth. Okay, so here's our thick Venusian atmosphere. Here we are back out in space, and let's see what happens to the sunlight in this much thicker atmosphere on Venus. And you'll see maybe a very occasional ray of sunlight hits the surface, but in almost all cases, it gets absorbed in the atmosphere.
The trapped sunlight heats up Venus's atmosphere, and any sunlight that reaches the surface worsens the situation.
So here we are on Venus, our hot surface radiating infrared. And is it making it out into space? Generally, no. Not only is it getting absorbed into the atmosphere, but some of it is bouncing back to the surface. And so on Venus, the infrared radiation is trapped by the thick atmosphere, and the surface and the atmosphere end up heating up.
The process resembles what's happening on Earth, but on Venus, it's out of control. Earth's twin is now the hottest planet in our solar system, even hotter than Mercury, the planet closest to the Sun. Venus is the poster child for climate catastrophe, devastating global warming, and a cosmic hellhole. If Earth were nearer to the Sun, it would look like Venus.
The major difference between Earth and Venus in terms of the evolution of the planets is all about Venus being closer to the Sun. We think that they formed kind of as identical twins, and then it's a different sort of experience of growing up in slightly different neighborhoods closer to the Sun and farther from the Sun that led to this huge divergence we see today.
Life on Earth may be a lucky break, but in the end, we share the same fate.
If you think of the long-term future of the Earth, Earth will go the direction of Venus because the Sun is heating up. And I'm not talking about on a short time scale. If we think about billions of years in the future, really, cosmological timescales, then Earth is destined to end up like Venus.
Scientists long guessed Venus was once like Earth. Venus Express has shown how it evolved into a barren world. More revelations lie beneath the clouds. On the surface, the clouds look calm. But when the spacecraft switches on its infrared thermal imaging spectrometer, its images show how the scene transforms. Violent storms rip across the planet. At the poles, monster cyclones churn the atmosphere. Storm systems that make Earth's worst weather look like a breeze. As scientists study this mysterious planet, they make a startling observation. While Venus rotates slowly, its atmospheric winds travel fast. Venus Express observes winds circling the planet in a mere 4 Earth days. That's 60 times faster than the planet's rotation speed. Scientists call this superrotation. If Earth were like Venus, winds would whip around the planet in just 30 minutes. A speed of 50,000 miles per hour.
When you think about the rotation of the Earth, you know, you've got the rotation rate of the solid planet, 24 hours, and then the atmosphere sort of going along for the ride. But with Venus, it's almost as if the atmosphere doesn't really care what the solid surface is doing. It's got a mind of its own and is rotating much faster than the solid surface.
On Earth, wind speed nearly matches rotation speed. So why do Venus's winds travel so much faster than the planet spins? The answer lies in the clouds. On Venus, the cloud layer is up to 12 miles thick. So thick, only a small amount of solar energy reaches the surface. Much of this energy is retained in the upper clouds, 40 miles above the surface. This energy starts the clouds moving at breakneck speeds. Because Venus is closer to the Sun than Earth, the greater the solar energy in its clouds, and the greater the wind speeds. Winds rare on Earth, over 200 miles an hour, are typical on Venus. Venus Express is equipped to solve a riddle found by an earlier mission. A vortex at Venus's North Pole, similar to vortices on Earth. We call them hurricanes. On Earth, they form when warm, moist air from the ocean is heated by the sun and rises to form clouds. As more energy enters the system, the clouds start to spin, creating a hurricane. But Venus has no warm oceans for fuel. So what powers its hurricanes? Venus Express swings down to the southern hemisphere for a closer look. What it finds blows scientists away. A vast hurricane-like vortex, 1,200 miles wide and 13 miles deep. 4 times larger than the largest hurricane on Earth. Not one, but 2 rotating eyes. Scientists believe the cause of the vortices is not only super-fast winds, it's the very motion of the planet.
A huge vortex is caused by all the air flowing in from the equator, and then it has to sink somewhere, which causes this enormous vortex, which is some 2,000 kilometers across.
Wilson believes air from the equator flows to the poles, where it's sucked down to form the vortex. But this air doesn't move in a straight line. The planet's rotation deflects its motion. He suggests this process, called the Coriolis effect, produces the giant vortices.
Let's explain the Coriolis effect using this rotating table. It's the same for a rotating planet. If I let this ball roll across the table, you'll see that it runs in a straight line. And that's because you, the observer, are stationary. You're not rotating with the table. Whereas if, on the other hand, we switch to a camera angle or another observer who's rotating with the planet, this ball will appear to travel in a curved trajectory. So if the observer is rotating with the planet, then it appears that objects experience a force to the right. And this works not only for balls, but also for parcels of air in the atmosphere. If the air at Venus is heated at the equator and moves towards the poles, it's then bent towards the right if it's in the southern hemisphere, or towards the left if it's in the northern hemisphere.
As the winds move toward the poles, the Coriolis effect makes them spin, which creates the vortex. Wilson's theory seems logical. Vortices also occur at Earth's poles. But while Earth's polar vortex is relatively stable, the double-eyed monster on Venus is an ever-shifting whirlwind. To find out what makes the vortex so chaotic, recreate it. Wilson uses water to simulate Venus's atmosphere.
We've got the rotating atmosphere simulated by the rotating tank, and then we've got this thin ring here which spins at a different speed, faster than the rest of the atmosphere. And what we find is that the flow in this region is unstable, it sort of oscillates in and out. And we think that's quite representative of what happens around the edges of the polar vortex on Venus.
When Wilson adds dye, his simulation reveals the shifting shapes at the edge of the vortex. These chaotic winds show the power of Venus's atmosphere. But vortices aren't the only bizarre weather. On June 9th, 2006, Venus Express discovers an eerie phenomenon. The spacecraft detects an intermittent disturbance that sounds like a whistle. A brief, low-frequency electromagnetic burst. This is the actual recording. To anyone else, baffling. But to the mission team, a revelation. The signature of lightning. UCLA's Professor Christopher Russell has long believed lightning occurs on Venus. The spacecraft's discovery presents a riddle. On Earth, water drives thunderstorms. Warm, moist air collides with cold air. Water droplets and ice crystals rub together, creating positive and negative charges. The electrical buildup discharges as lightning. Venus's atmosphere has little water. Most of it has been stripped away by the solar wind. So what else could produce lightning? Thanks to data from Venus Express, a controversial theory gathers new weight. Russell's candidate for the cause of lightning? Clouds of sulfuric acid. On Earth, sulfuric acid clouds form when sulfur dioxide is released from volcanoes and mixes with water vapor. The same thing happens on Venus. 2 decades ago, Project Magellan, the first spacecraft to map Venus, discovered widespread evidence of a volcanic past. Over eons, volcanoes released trillions of tons of sulfur dioxide. Some remained as a gas. The rest mixed with water vapor to form sulfuric acid clouds. The speeding winds energize these acid clouds and create ideal conditions for lightning.
We think now that it's sulfuric acid clouds and Venus's winds, and the winds can then provide the energy source in the cloud for the charge separation.
Sulfuric acid does on Venus what water does on Earth. Acid drops rub together and create positive and negative charges.
I was looking for lightning and looking for the proof that it really existed, and to find it is like a personal victory.
The discovery of lightning is electrifying. Lightning is an ingredient of life. An even greater shock was in store. The hellish planet might not be dead. Eons ago, Venus's volcanoes spewed out vast clouds of sulfur. But today, tests show the level of sulfur is fluctuating. Since volcanoes discharge lots of sulfur only when they erupt, the fluctuations mean one thing. The volcanoes on Venus must still be active. Scientists have found active volcanoes in only a few places besides Earth. In 2007, the New Horizons probe captured an eruption on Io, one of Jupiter's moons. To find active volcanoes in the inner solar system is big news. It means Venus may not be a dead rock, but a living planet. Venus Express takes a closer look. The probe exploits the infrared windows to peer through the clouds. Below, mountains and valleys, smooth plains, impact craters, and flat-top features like pancakes, all made of lava. 85% of Venus's surface is paved with lava. Why so much puzzled scientists. To understand Venus's vast lava fields, scientists look to its calmer twin. Earth's crust is made up of interlocking tectonic plates that drift over its liquid mantle. Most of our planet's volcanic activity is found where these plates move together or pull apart, allowing heat from the core to escape. No mission has ever found evidence of plate tectonics on Venus. Its crust is solid. Without plate tectonics to cool Venus, scientists suggest heat from the core built till it couldn't be contained. Then virtually the whole planet erupted, releasing so much lava, it recycled the crust and resurfaced the planet.
This is a demonstration of the Venus resurfacing. We're going to demonstrate with some pudding in a pan over a hot plate. And this heat from the hot plate represents radioactive heat from the inside of Venus. And here we're seeing the first signs of the interior heating the crust on the surface. And that crust is stagnant. It's not moving, it's keeping the heat inside. And perhaps at this moment, the surface might even crack in some places, and the molten material, the molten rock under the crust, would erupt and flow out onto the surface, covering up all the craters and all the mountains. And at this point, we can see several small volcanic eruptions along those fissures.
Scientists date the resurfacing to 500 million years ago. A slow process that took tens of millions of years. This cataclysmic series of eruptions released trillions of tons of sulfur dioxide and carbon dioxide, replenishing what the solar wind removed. Yet surveys of Venus reveal not all the planet was resurfaced. Rocks in the highlands are much older than the lava covering most of the planet. They offer a clue to conditions in the distant past. Kevin Baines discovered these rocks weren't born on dry land.
On Venus, most of the rocks are basalts. They're made out of volcanoes spewing out their lava. But we have found a very interesting result in the last few months. That is, the highlands are special. On the highlands, the tall mountains of Venus, we're finding evidence of rocks that were created in the presence of water, as if billions of years ago they were formed perhaps in an ocean, and then geologic processes have risen them up since then.
The rocks provide hard proof that Venus once had oceans, which raises a provocative question. On Earth, life began in the oceans. The other ingredient to kickstart life is lightning. And lightning occurs on Venus. If Venus had water and lightning, did it once have life? Scientists have plenty of proof that Venus and Earth were once twins, and that Venus had two of the ingredients of life: water and lightning.
Lightning is important because it's something that produces exotic species. For example, nitrogen and oxygen combined to produce nitrogen oxides, which are important for life and important for producing chemicals that can't be produced any other way in a planetary environment.
With water and the means to kickstart evolution, perhaps Venus once had life, and maybe still does. The first clues arrive from Venus Express. 155 miles above the surface, a camera is switched to ultraviolet. Unlike infrared, the shorter wavelength of UV is scattered by Venus's cloud layer, enabling the scientists to explore the upper regions of the atmosphere. Their images reveal intriguing dark markings where more UV is being absorbed. This shows that something besides sulfuric acid is trapping sunlight. The mission team calls the dark areas absorption patches.
There's been great interest in the ultraviolet absorbers on Venus. They absorb about half of the sunlight that's hitting the planet. They're in the clouds of Venus, and it's been suggested that they might be associated with life forms.
Life forms like microbes living in hurricane-force winds and sulfuric acid clouds, using UV light in some weird photosynthesis. But what kind of life could survive such conditions? Biologist Lynn Rothschild studies organisms that live in extreme environments. She has discovered microbes called extremophiles thriving in some of the harshest conditions on Earth, like Yellowstone National Park. With the highest concentration of thermal springs in the world, it opens a window into how life might survive on Venus.
What you see behind me is really ground zero for where people started to understand organisms that could live in extremely acidic conditions. Before that, people thought conditions like lemon juice would be totally outside the realm of where a living organism could be.
These geysers, powered by volcanoes, mimic conditions on Venus: hot and acidic.
This stream is just phenomenal. It's about pH 3. It's about 40 degrees centigrade. Little hotter than warm to the touch. Actually, it's fairly warm to the touch. What you see in here is almost a pure culture of some red algae. I know it looks green, but they are actually red algae that don't have a red pigment.
Extremophiles like these can survive in battery acid and temperatures above boiling point. These organisms have evolved to survive not only the heat and the acid, but levels of other chemicals that would kill most life.
These particular organisms, Cyanidium, are really neat because not only do they live at low pH and in warm temperatures, and they photosynthesize, but they've been shown to be able to survive in pure CO2, pure carbon dioxide. Even Venus doesn't have as high a carbon dioxide level as that.
The organisms show life can survive hot, acidic carbon dioxide-rich environments, like Venus. If life can survive in Yellowstone, why not on Venus? Scientists believe the surface itself is too savage. Temperatures reach 900 degrees, and the pressure is bone-crushing. But not in the clouds. 30 miles up, temperatures reach only 176 degrees, much closer to the kind of heat microbes endure on Earth. Could life have begun in Venus's ancient oceans? When the water evaporated, the microbes may have gone with it. Here, in the cooler acidic clouds, they could survive. But how can life exist without water?
There is water vapor up in the clouds in Venus, and we have some indication that organisms on the Earth, for example, lichens, can use water vapor as their source of water. So that's pretty encouraging for life in the clouds, at least in terms of having water available.
To see if life exists in moist, acidic clouds, Rothschild collects air samples above a hot spring. The acidic steam mimics the clouds of Venus.
Oh, I can see a little green on the mouth here. That's encouraging. Maybe there really is something in there.
Analysis shows microbes can exist in hot, acidic steam, suggesting life may survive in Venus's clouds. To further test the theory, Lynn sends organisms high into the atmosphere. She's launched a whole spectrum of microbes. Some to over 100,000 feet. A zone where temperature and pressure drop so low, most life would die.
Okay. Now let's hope we put enough in it.
Many of her subjects survived. Some researchers have even found organisms that can reproduce high up in the atmosphere.
The clouds on Venus are continuous and long-lived. So you can imagine creatures that live in the clouds and reproduce in the clouds and even seed other cloud particles. And they're not going to last forever because they're going to fall out, but as long as they last long enough to reproduce themselves, then you could have a self-sustaining colony of life in the clouds.
Research shows life in hot, acidic clouds is theoretically possible. Perhaps microbes live in the clouds of Venus, hidden in those strange dark patches. Venus Express has traveled 87 million miles around the planet and completed 100 weeks of collecting data. It proved that Venus once looked like Earth. A habitable climate, vast oceans, perhaps even life. But too near the sun, Venus was doomed. Earth blossomed, Venus burned. Yet even here, life may thrive. Maybe tucked in blankets of clouds. We may have to wait years for the secret to be revealed. But someday, another mission to Venus may find the holy grail of space. Life beyond our world.
Planet Earth, 4.5 billion years old. A solid ball of rock weighing 6 trillion tons. We are on a quest to destroy it. Using cutting-edge physics and planetary science, we will explore what could destroy our planet completely. A black hole?
It might seem harmless, but its gravity is strong enough to destroy the entire planet Earth.
A collision with the sun?
And before you know it, the Earth is falling into a fiery plummet.
A huge antimatter bomb?
Poof, okay, at a huge annihilation.
A giant rock from space?
You wouldn't want to be standing here 50,000 years ago.
Or perhaps a swarm of self-replicating robots.
It's been a nightmare of sci-fi.
These ideas may sound like science fiction, but they're all grounded in proven scientific fact. Our planet is seriously tough. It has survived everything a hostile universe could throw at it for 4.5 billion years. Yet in the past few decades, we have developed technologies so powerful that some people fear we could literally destroy the Earth. It's time to find out if they're right. 6 top scientists are about to reveal what it would really take to destroy an entire planet. Our first candidate is a black hole, the greatest destructive force in the universe. A black hole is what's left when a giant star collapses in on itself. The result? Gravity so strong that nothing can escape, not even light. Soon, we may be able to create black holes right here on Earth. Physicists use huge particle accelerators to try to recreate what happened after the Big Bang. But when they smash particles together, they also risk creating a black hole. Think of a black hole as Niagara Falls, and the water going over like space getting sucked in. This unfortunate kayaker has gotten too close. Just like a star getting too close to a black hole. Dr. Phil Plait, astronomer and author.
The water going over the lip of the waterfall is just like space itself falling into a black hole. If you're kayaking, no matter how fast you paddle, once you go over that lip, you're going down. That's the point of no return. And it's the same thing with a black hole. No matter how fast you try to get out, it's going to take you down.
The gravity in a black hole is fundamentally different from the gravity we experience in normal life. Normal gravity you can escape from, at least in theory. Cosmologist and golfer Professor Lawrence Krauss.
It's commonly said that what goes up must come down, but that's not always the case. For example, if I hit this golf ball here and I hit it well, it would go fairly far, but it would still come back down to Earth. If I hit it harder, it would go further and still come back down. But if I hit it with a speed of 5 miles per second, it would escape from the Earth's gravitational field.
But for the ball to escape from a black hole, it would have to move faster than the speed of light, and that is simply not possible. What goes into a black hole, planets, or even stars, never comes out. Our small planet wouldn't stand a chance. For anyone looking for a way to destroy the Earth, black holes are a good place to start. The trouble is, there are none close by enough to do the job. Unless we make one. That's where the atom smashers come in. With a lot of math and a gigantic machine, physicists can now generate atom-sized explosions that may be powerful enough to create microscopic black holes. They are trying to study the Big Bang. The force of the impacts recreates the particles that made up the universe in its earliest moments. Some of those particles may create microscopic black holes. That doesn't mean our planet is doomed. In theory, black holes this small would just evaporate like tiny soap bubbles. To destroy this, you need something bigger.
Black holes come in all sorts of different sizes. For example, at the center of our galaxy, there's a black hole of 1 million solar masses. If you took the mass of our sun and compressed it down to be a black hole, it would be the size of a large American city like Phoenix here. On the other hand, if you took something like this mountain here, which is maybe 1 million tons, and made it a black hole, it would be smaller than the size of a single atomic nucleus.
Somewhere along that scale, black holes get powerful enough to cause serious damage. To destroy the Earth, it turns out you need a black hole that weighs about the same as the Earth. The Earth is 8,000 miles across. But a black hole weighing that much would be the size of a marble. Professor Clifford Johnson, physicist.
Here I have a marble-sized black hole. It might seem harmless, but its gravity is strong enough to destroy the entire planet Earth. What would eventually happen is that it'll start sucking things in, slowly at first, and then it will grow in size. It will grow and grow and grow until it swallows the whole Earth.
To imagine what that marble would do to the Earth, picture what it does to a physicist.
The gravity is much stronger on one side of an object closer to the black hole than it is on the other side of an object, producing an effect that's called spaghettification, as that object is stretched out and pulled apart as it falls into the black hole.
A big enough black hole could do this to our whole planet. There's no way even the most powerful atom smasher could make a black hole this big. To destroy the Earth, we need to find one ready-made. Astronomers think there are 10 million or so black holes in our galaxy. If one of them strayed into our neighborhood, it could rip our planet to pieces. Earthbound telescopes may not even detect it. Humans would only know it was approaching when its immense gravity triggers huge floods and earthquakes. As it plunges into our atmosphere, the black hole acts like a vacuum cleaner, sucking with a force over 1,500 times Earth's gravity. Then it begins to distort the shape of the whole planet. Earth's surface stretches and tears apart. Finally, the hole hits and flies straight on in, heating and vaporizing matter as it goes. It starts to orbit the Earth, inside the planet itself, all the time devouring everything in its path. Gradually, the orbit slows. The black hole spirals down into the Earth's core. Eventually, it eats the entire planet. All that's left is the black hole itself. It's a devastating end for planet Earth. But fortunately for us, it's unlikely ever to happen.
If you want to destroy a planet, a black hole is a great way to do it. But the problem is, it depends on the kind of black hole. A microscopic black hole would just pass right through the Earth, and it really wouldn't do that much damage. A black hole with the mass of the Earth would be about the size of a marble, and that would do a considerable amount of damage passing through the Earth, but again, it might not destroy the planet. If you want to do the job right, you need a stellar mass black hole, something with about 3 times the mass of the Sun. That thing would come in and it would tear the Earth apart and gobble down the pieces, and it would be game over. The problem is, we don't know how to make any of these black holes. Technologically, we just can't do it. And with a naturally existing one, we don't know how to move them. So there's got to be a better way.
So if black holes don't work, time for a new approach. One surefire way to destroy the Earth is to change its distance from the Sun. Move the planet closer and it bakes. Move it out and we freeze, sending us into another ice age. Scientists have recently begun to realize that moving a whole planet might actually be possible. In fact, we use the same principle to slingshot space probes round the solar system. Planet Earth could be just a few well-placed flybys away from a fiery death. What would it take to incinerate an entire planet? Answer: a nuclear furnace nearly 1 million miles across. It sounds crazy, but the truth is this will happen. It's just a matter of time.
As the sun gets older and older, it's going to actually get brighter and brighter. And within about 2 billion years, the Earth will be in an uninhabitable zone. It'll be like Venus. There'll be a runaway greenhouse effect. All the water on Earth will be destroyed, and the surface temperature will be about 1,000 degrees.
Eventually, the sun will swell and scorch the Earth, unless we somehow move the Earth away from the sun to save it.
Alternatively, if you were sufficiently evil, I suppose, you could imagine doing exactly the opposite. Harnessing sufficiently large objects to transfer gravitational energy to kick the Earth's orbit closer to the sun.
Easy to say, not so easy to do. The Earth weighs in at 6 trillion tons. Pushing something that big is quite a challenge. But there is a way. It's called gravity assist. Space probe engineers use gravity assists all the time. Take Saturn's Cassini-Huygens probe. It's the size of a school bus, one of the biggest probes ever built. To build up enough speed to fling the probe out to Saturn, it had to swing by Venus twice and Earth once. Each flyby stole energy from the planet and added it to the probe. The probe got a lot faster by altering the planet's course just a little.
The name of the game, we take a rock about a mile or two across and we move it so that it just passes the Earth the right way, and it'll steal energy away from the Earth. The asteroid will go flying off and the Earth will move in toward the Sun. But we shouldn't just waste the asteroid when we can recycle it. If we're clever, we can take the asteroid and have it go toward the planet Jupiter. And then if we pass Jupiter in just the right way, it'll take that extra energy it stole from the Earth, give it to Jupiter, and then fall back toward the Earth. And if we aim everything just right, we get a conveyor belt of energy. We steal it from the Earth, give it to Jupiter, and then come right back. And in fact, we can use hundreds or even thousands of asteroids this way, continuously stealing Earth's energy and dumping it toward Jupiter. And before you know it, the Earth is falling into a fiery plummet.
First, you need to catch an asteroid. It's as big as a mountain, and it's traveling around 10 miles a second. Next, you need to attach rockets and boost the asteroid onto the perfect course. Next, repeat, thousands and thousands of times. Very slowly, over thousands of years, the Earth will fall towards the Sun. Right now, we're just over 90 million miles away. By 70 million, the Earth is a superheated desert like Venus. Then things start to get really bad.
As the Earth slowly spirals into the Sun, a series of events unfolds which unfortunately spells doom for our planet. As the Earth approaches the Sun, the atmosphere heats up and blows off, and the oceans boil, basically turning the Earth into a giant comet. But there's worse to come. As the Earth gets closer to the Sun's gravity pulls on the near side of the Earth more than it pulls on the far side, and the Earth stretches like putty. At some point, it gets close enough to the Sun that the Sun's gravity can overwhelm the Earth's gravity, and it shatters, pulverizes our planet.
The Earth is dead, but its ghost could remain, a faint ring of material around the Sun. Peter Schultz, planetary impact geologist.
If the Earth or any object gets too close to another object like the Sun, eventually the tides will rip it apart. As that happens, it would simply be broken into many small pieces that would then encircle the Sun as if it were a ring.
The Sun would resemble Saturn with its own faint ring of rocks and dust. A fiery death and a ghostly remnant. If you want to destroy a planet, this could be the way to go.
A great way to destroy the Earth is to drop it into the Sun, let it plummet to a fiery death. And we can do this. All you need to do is to pass enough asteroids near the Earth in succession to gravitationally drop it into the Sun. And we have that technology. We know how to move asteroids. It's just a matter of getting them on a precise enough orbit to be able to do it.
Maneuvering billion-ton chunks of rock with pinpoint precision at hundreds of miles a minute is quite a stretch. Not to mention the amount of time it would take to capture enough asteroids. We've tried to crush it and burn it. It's time for another plan. An antimatter bomb. Physicists have been searching for over a century for a theory that unites our understanding of the large-scale universe, planets, galaxies, and stars, with what we know of the subatomic world, electrons, protons, and quarks. Their theories are bringing to light some pretty destructive phenomena. One of them could be a world killer. Antimatter. Theorized in the 1920s, detected in the 30s. Now we can create antimatter in modern particle colliders. And the base ingredient for the biggest explosion possible. Antimatter is the most explosive substance ever found. Pound for pound, it's far more powerful than even a hydrogen bomb. But antimatter is hard stuff to find. Everything we see around us, out to the most distant galaxies, is matter, created 13 billion years ago in the Big Bang. It created antimatter too. They look similar. In fact, they are entirely opposite. Put them together, and they wipe each other out. Cosmologist Lawrence Krauss.
Now I have a proton here, and anti-Krauss over there has an antiproton. And when we bring them together, we're going to make an incredible explosion. Okay, let's annihilate.
This is what happened to all the antimatter created in the Big Bang. It annihilated. If we want to use some for a bomb, we need to make it ourselves. Making antimatter is a bit like firing a gun at a target.
If I shoot a gun at a paper target, the paper that flies out of the target is like matter, and the hole that's left behind is the antimatter. It takes energy to create a matter-antimatter particle pair. In the shooting range analogy, the bullet provided the energy.
In reality, the gun is a particle accelerator, like the one at CERN in Switzerland. Fire protons in a giant tube, steer them around with powerful magnets, use the same magnets to accelerate the protons to near the speed of light, then slam the beam into a block of metal. For every million protons that hit, you get one antiproton. It's as if Plate's handgun only left a hole once in every million shots.
In an accelerator, you only get one particle-antiparticle pair out of every million collisions or so. And so it's really hard to find that one antimatter particle floating around. It's a lot like coming to Niagara Falls and trying to get that one particle out of all the mist. And that's why it's so hard to create antimatter on a large scale.
Assuming we can obtain enough antimatter, the next challenge is to make it into a bomb. Nothing is more unstable than an antimatter bomb. You have to find a way to hold the antimatter without it touching any ordinary matter. If it does, it will explode.
So I have a bunch of antimatter above my hand here. Well, it better not touch my hand, because if it does, poof, okay, at a huge annihilation. But worse, it can't interact with the air around it, because the air is made of matter. And again, you'd get an incredible explosion.
Researchers need a special container to study antimatter. And this is it, a penning trap. Powerful magnets suspend the antimatter in a vacuum.
So if I want to store this antimatter, what I have to do is somehow keep it levitated above my hand, which means I'd have to produce huge magnetic fields in just the right way to keep the charged particles in the antimatter from touching my hand. But I'd also have to store it in an incredibly high vacuum, because any air in the container would again cause an explosion. And so the energies and technology required to produce those magnetic fields, keep that ultra-high vacuum, would mean that you wouldn't have a small object. You'd have to have surrounded with massive amounts of machinery.
Yet for all that trouble, an antimatter bomb isn't just theory. We can make antimatter, we can capture it, and we can store it. But where do we plant it for maximum effect? If we want to destroy the whole planet, the bomb has to go off near the Earth's core. That's nearly 4,000 miles straight down, further away than London from DC. Right now, that's impossible. The deepest man-made borehole stops at just 7.5 miles. But what if we could? So far, mankind has managed to create a grand total of 20 nanograms of antimatter. That's 100 million times lighter than a dime in your pocket. So the bomb is going to be too small even to see.
200 feet away in this test range in Arizona, we have the explosive equivalent of TNT. So let's see how big of a bang that makes. Wow.
20 nanograms of antimatter makes quite a blast, but it's way short. To destroy planet Earth, we would need 2.5 trillion tons of the stuff. That's a bomb the size of Mount Everest, at the bottom of a hole 4,000 miles deep. If it were possible, the result would split the Earth into thousands of pieces. With a powerful enough bomb, the pieces would fly out into space and are lost. With a slightly weaker bomb, the pieces fall back under the force of their own gravity, collapsing into a molten ball. An eerie echo of Earth's creation 4.5 billion years ago. It could happen, in theory, but there are a few technical details to iron out first.
So what's the matter with antimatter? Well, if you're trying to destroy the Earth, it'll work, it'll do the job. The problem is you need about the energy that the sun puts out in an entire week. So it's a huge amount, and we just don't have the technology to create that right now.
At the present rate of production, making the bomb would take more than the age of the universe.
The other problem is getting it to the Earth. How do you do that? Well, you'd have to get it to the center of the Earth, and that means digging a hole several miles across and 4,000 miles deep. So in the end, don't think antimatter is probably the most efficient way of destroying the planet.
So, as a way of destroying the Earth, maybe antimatter has some problems. But we know the next approach works, because it already happened once before in Earth's ancient past. Space is a dangerous place. It's full of debris. Rocks the size of pebbles, up to rocks near the size of a planet. There are impact craters everywhere, including our moon. These asteroids can hit us as well. An asteroid wiped out the dinosaurs. Maybe a bigger asteroid could destroy the planet entirely. Meteor Crater, Arizona. Almost a mile across, nearly 600 feet deep. Today, science can reconstruct what happened here thousands of years ago. Dr. Dan Durda, planetary scientist.
You wouldn't want to be standing here 50,000 years ago. This iron meteorite, about the size of a small office building or so, it's made out of stainless steel from space. It's about to strike the desert with an impact energy of somewhere between 1 and 10 megatons. And it's that energy that's going to excavate and open up this crater behind me, which is nearly a mile across.
The impact ultimately devastated an area the size of New York City, with 600 times the power of the Hiroshima bomb. And that was small. 65 million years ago, a real monster struck. It was 6 miles across. Sat on the ground, it would outtop Everest by half a mile. The crater was over 100 miles wide. The impact wiped out the dinosaurs and destroyed most of life on Earth. An even bigger space rock could destroy the planet. We're already developing technologies to protect against future impacts. Ironically, you could use those same technologies to make an impact happen. One approach is to hover a space probe near the asteroid. The probe's mass generates a tiny gravitational pull on the rock. Over time, that can change the asteroid's course enough to miss the Earth, or to guarantee a hit. Another protection technology that we could use is a technique called solar sublimation. This diverts an asteroid or comet using nothing more than sunlight. To demonstrate the effect, Durda starts by building a homemade comet.
Some fraction of near-Earth objects are comets, so let's examine what comets are made of. Let's actually make a comet.
Take some soil, add dry ice, then water, and some chocolate.
We'll put in a few percent of organic material into our comet. And of course, in the outermost solar system, there's a little bit of ammonia here and there. We'll let that be represented by this ammonia cleaner. Let's see if we can pack this up and make ourselves a little comet nucleus.
A magnifying lens completes the apparatus.
If one were to actually focus the light from the sun onto the surface, one could cause some of that water to vaporize away. And just like on this comet nucleus, the jetting action of those evaporating gases act a little bit like little artificial rocket motors attached to the object. And over time, they really do cause it to be pushed slightly off course.
The power of sunlight alone is enough to divert a space rock onto a collision course with Earth. But solar sublimation may not be effective on an object big enough to pulverize our planet. To destroy the Earth, our space missile needs to be big. Like Mars big. We know this for certain Because it's happened before. 4.5 billion years ago, a rock the size of Mars struck the Earth a glancing blow. The impact debris created the Moon. If it had hit head-on, none of us would be here. We've come here to the vertical gun range at NASA Ames in California for proof. This 12-foot gun fires beads up to 4 miles per second, 6 times faster than a rifle bullet. Professor Peter Schultz, a planetary impact geologist, uses the gun to simulate a Mars-sized object, represented by this small projectile, hitting our planet head-on. The Space Environment Chamber is ready. Schultz makes his final adjustments. But will our scale model Earth break apart completely?
That hurt. That really hurt. Look at this thing, this is worse than a science fiction movie. That's just glorious disaster. There's nothing left.
A head-on strike, destruction guaranteed.
So the things that destroy an object is going to be a combination of the size of the object, the speed of the object, and the angle. The lower the angle, the less likely it'll completely bust it apart. So to really destroy the Earth, you need something that's humongous and needs to hit straight on.
Now we know what it takes to use an impact to destroy planet Earth. Asteroids and comets are just too small. We need to move something the size of a planet onto a collision course. That's a level of technology we won't be reaching anytime soon.
Now, we can move asteroids around and we can move comets around, but those are only a few miles across. The problem here is that we need something really big. Mars is about 1/3 of the size of the Earth, and even that hitting the Earth won't destroy it. We would need something almost as big as the Earth itself, something like Venus. And even then, we just don't have the technology to be able to move something that big with that kind of precision to aim it at the Earth and blow it up.
Destroying the Earth with a space rock just isn't gonna happen. Perhaps the killer punch won't come from space, but from right here on Earth. Genetics, robotics, nanotechnology. Researchers hope machines will lead us to a brave new world. Already, robots can learn, build other robots, and cooperate with each other. It could be the beginning of a new age. It could also be the beginning of the end. Right now, we can only build robots that work with humans in control. But science is working towards machines that can think for themselves and even reproduce. Robots that can make copies of themselves without human control could one day take over the world. Hod Lipson, professor of robotics. Lipson is a pioneer in robot replication.
If this robot could make another robot identical to itself, and then those 2 robots can make 4 robots and so forth, these robots could fill up a space such as this here fairly quickly.
Once the first replicate is made, there's no stopping the process. But first, we've got to make them. At Cornell's robotics lab, Lipson and his team already make robots that learn, robots that build, and robots that build themselves. This is the world's first self-replicating robot. Supply it with building blocks and it assembles them to make a copy of itself. It needs Lipson and his lab techs to keep it stocked with plastic cubes. So this robot is pretty benign. To destroy the Earth, we need to develop robots that use smaller blocks and eventually individual atoms.
We've been trying to make robots made of much tinier cubes on the order of 0.5 millimeter, and you can barely see them. There's about 10 of them in this container here. We're trying to get these very small units to combine together, and the smaller they get, the faster and more easy it is to replicate.
Lipson thinks that advances in robotics will revolutionize design and manufacture. But where there's progress, there's also danger. In theory, nano-sized machines could start to replicate out of control. Self-replicating nanomachines could, in theory, destroy all life on Earth. To destroy the planet itself, we need something more. To reproduce, a robot needs energy and raw materials. In other words, food. The more food there is, the more copies our robots can make. And the biggest source of food on the planet is the planet itself.
The ultimate kind of self-replicating process is something that's inspired by nature. So if we can have a machine that can essentially self-replicate using resources in the environment, food and energy, then that would be a pretty big achievement.
And the biggest natural resource on Earth is rock. Design a self-replicating robot that feeds on rock, and it has 6 trillion tons of food right under its feet. Some living creatures already use rock. Rock-feeding bacteria live in the Earth's crust, even several miles deep. But nature's rock eaters are good for the planet. They help form soil and keep life ticking.
There's a whole suite of rock-eating bacteria that we've now uncovered on the Earth, which will go and chew up and eat and use the materials in the rocks for their sources of energy and for the sources of compounds they use to build other biologic molecules. There are literally biologic organisms that do just this, eat rock.
Rock-eating, self-replicating robots. But they've got to be smart. They need to cooperate. Professor Alan Winfield, roboticist in charge of the Symbrian project, to design robots that swarm like insects.
Symbrian is a 5-year project to try and build a swarm of self-assembling robots. Perhaps as many as 30 or 40 will physically join and then behave and act as a single organism. The big challenge is going to be how to get the robots to first of all decide what to be: a foot bot, or a knee bot, or a sensor bot, or a brain bot, and then work cooperatively so that, for instance, the organism can stand up and walk.
We can already make robots that reproduce. We can make robots that cooperate. Put them together, and at last we may have our planet killer. Here's the math. Say each robot takes 1 day to replicate. Then after a single month, you have over 1 billion robots. After a year, you have trillions. Earth is covered with machines that do nothing but gobble rock. In the end, no more rock, just a huge ball of self-replicating machines.
Now, what are robots made of? Well, iron, magnesium, aluminum, and silicon. The same thing the Earth is made of. And so all you have to do is create one of these self-replicating robots and let it out into the wild. It'll make a zillion copies of itself, and they will consume the Earth, and eventually, there'll be nothing left.
Success at last? Perhaps not. In our quest to destroy the planet, we've tried devouring it, incinerating it, pulverizing it, blowing it up, and breaking it down. Planet Earth is a proven survivor. It has taken everything the universe can throw at it for 4.5 billion years. And one thing is certain: we're still here.